The claim is the proposition shows what it says. The tautology and the contradiction show that they say nothing. The tautology has no truth conditions, for it is unconditionally true, and the contradiction is on no condition true. Tautology and contradiction are without sense. They are like the point from which two arrows go out in opposite directions. So our little picture here is you have some point and you have an arrow going out to the right and an arrow going out to the left. And the thought is, well, you can't really ascribe any direction to that point. It's, it's torn between. So that's our little picture metaphor. And then concrete example is, I find this, example particularly compelling. So when I find out that it rains or it does not rain, which is a tautology, it's either raining or it's not raining. The claim is, I don't know anything about the weather. I don't learn anything about the weather when I'm told it's either raining or it's not raining. So that's in some sense, an argument for the meaninglessness of these tautologies and contradictions. And then, so you might also have a question about what's the interpretation of entailment. If we wanted to give like a philosophical gloss on entailment, what might we say? And so here the view is, if a proposition follows from another, then the latter says more than the former less than the latter. So basically, if I have some proposition, 5, I have some proposition 5, and this logically entails some claim P, the thought is phi says more than P. Get that right. The proposition follows from another, then maybe I screwed up. The proposition follows from another, then the latter says more than the former. Oh, no, sorry, I had it backwards, So see, these things are very confusing. So the claim is that P says more than 5. So P is in some way more specific than 5, saying more. And now you're like, okay, what's one way that you might be able to connect this with contradictions? Contradictions entail everything. So if I have, occasionally we'll use a symbol for a contradiction, which is called bottom, or falsum. Bottom, falsum, or even just sometimes false. So this thing, which is like a turnstile that turned, 90 degrees, or a T upside down. So a contradiction logically entails any proposition, so any phi member of the well-formed formulas of substantial logic. So there's a sense in which every claim that's not a contradiction is saying something more than a contradiction. And that seems intuitive, right? So also you'll remember that if you have any phi of well-formed formula, it will entail a tautology. So again, there's a sense in which the tautology says the least about anything. Tautology is like the most vacuous thing you could say. It's pretty vacuous to say it's either raining or not raining.
Wouldn't that say that the tautology says the most, though?
Oh shit, you're right, that would say that the tautology says the most. Yeah, and this is kind of like, so you get into puzzles, right? I mean, I'm not saying this is coherent text, So now we've gone into this puzzle, which is, okay, the claim was, if a proposition follows from another, then the latter says more than the former less than the latter. Tautologies, I think what Wittgenstein does, we'll come back to you, Selena. I think what Wittgenstein does is, Wittgenstein is denying that tautologies are propositions. So he wants to say that they are meaningless. And so he wants to say this claim about the saying more thing applies to everything that's not a contradiction and not a tautology. And then we would avoid this problem. Yes, Linda?
I was wondering, is it not, so maybe I'm like super confused, but I thought it was the other way around, because if I think something like, if I have $10 in my pocket, then I have at least $5 in my pocket. in that case, at least $5 in my pocket is P. And $10
Yeah,
is
no, I think, I had it, I just got tripped up. No, I had it right the
yeah, I
first
think
time.
so.
Yeah.
And now
Sorry, guys. No, it's this thing, using ladder and former is very confusing.
I
So,
think, yeah, it's
so it
better
really
than-
is, so the sentence, so for proposition 5, the way to really get into the psychology of a student is, did you look at the extended weekend as an opportunity for rest or as an opportunity to get caught up on work? Raise your hand if you're in the rest category. Raise your hand if you're in the caught up in work category. Yeah, I have to be honest, right? That's the mentality that I would be in. It might have been the mentality that I actually wasn't, we might say. I went to a party on Friday, that was fun. And then I graded trees, which was not fun. Boo, trees. We love trees until we have to grade trees, That's what we might say.
My flatmate flew to Amsterdam and back, and I asked her what hotel she's staying in, and she said she's gonna just sleep on the plane. And I was like, how on earth do you think this is possible? Being an international flight makes me want to stay in there for 3 days.
But presumably your roommate was in Amsterdam overnight one day, right? So had to stay somewhere.
I mean,
There's really cheap hostels, I guess.
she stayed with a friend, but they went out partying and all that, so.
Yeah, I guess that's one way to avoid it for a hotel. Cool. You guys have any questions for you, sir? Cool. All right. Oh yeah, one thing I should remind you of, which I'll write on the board, actually, we have a midterm 2 weeks from now. So 2 weeks out from midterm. And it'll cover the stuff we get through the end of next week, which will be natural deduction versus intentional logic. And then on the Monday, there won't be any new material. We'll just do review and practice problems and stuff. And that's a day where, if you're thinking to come to class, that could be ripe for insider information, right? Because we'll be prepping for the midterm, I'm the one writing the midterm, so I have a lot of information. You might get some information. So I'd recommend coming to class that day for sure. And so it shouldn't, I don't think it'll be too bad. And right now I'm thinking it'll probably be a mixed part of it on Carnap, which will become available at 9:35 or 9:30 or whatever on that Wednesday. I think it's the 27th of October. And then part of it will be written. But I can't require you to bring a computer to class. So if you want to take the whole thing written, then you can. But if you do the Carnap version, it's like the Carnap thing would probably have some checking features, but then that might not be fair for the people on paper. We'll see what happens. Does anybody think right now they wouldn't be able to bring a laptop to class for the midterm? Okay, maybe I'll email and see if anybody can do it. Because it's definitely, I think, if the Carnap thing, you might get some checking. That's a bonus to you. It's just, it's cleaner in a lot of ways. But trees would have to be on paper, and there'll probably be at least 2 proof questions of some kind. Those would be on paper if you want, or if you wanted to type it, I'll type it. Any questions about that? It'll obviously be open book since you guys have your laptops and stuff. So I couldn't require. I'm not going to do the respond this lockdown browser thing. That seems insane. So, all right. So we're doing the metalogics today. This is, strap in, because this is a lot of stuff to do in one day. Probably we could have spaced this out over 2 days, but there's really only 2 ideas in the whole thing. The 2 ideas are soundness and completeness. So there's really only 2 patterns of thought you have to get used to. It's a lot of information. We're patterned. So we're going to do soundness. We'll just start over, even though we started on this last week, and we'll move briskly. And then we'll talk about how to test alternative rules in systems for soundness. Then we'll move to completeness, and this will be relevant for second homework problems back with Bauer construction. And then we'll figure out how to test alternative rules for completeness. And really, it's these are the two big ideas, the whole thing. We're just going to emphasize this over and over again. When you're doing soundness reasoning, there's a notion that you're reasoning from the top of the tree to the bottom of the tree. That's soundness. Soundness is top down. And when you do completeness, it's the reverse. Completeness in the proof and in the problems, you're reasoning from the bottom up. And that's really only two things you have to remember, but of course there's a lot of details. So we will jump. If you're reading these on your own, you can read big picture stuff, but we'll just jump right into soundness. Is this guy live? Come to live? Let's see. Oh yeah, gotta do full screen, gets me every time. All right, so this is our definition of soundness, which you probably want to memorize. You probably just want to have this in RAM. That if you have a single turnstile in a system, then you get a double turnstile. So if you can derive some conclusion, prove some conclusion in your system, then those premises semantically entail that conclusion. So this is derivability, provability, pure syntax. Double turnstile is semantics. So we're going to prove soundness via the contrapositive. So if it's not the case that an argument is semantically valid, then it's not the case that you can derive that conclusion from those premises in the system. So these two things are logically equivalent, so if we prove the contrapositive, we've proved soundness. And it's just easier to prove the contrapositive. So, we unpack the definitions. This is the thing we'll get to assume throughout our proof. We'll get to assume throughout our proof we're dealing with some arbitrary argument that is not semantically valid, and that just means it's not the case that the set of premises gamma entails the conclusion theta. So there's some truth value assignment where gamma is true and theta is false. And so right now you can say immediately, which we'll say again probably in a couple slides, there's some truth value assignment where that makes gamma true and makes not theta true. Not theta is going to be in our root, and so there's going to be some truth value assignment that satisfies our root. And that's the thing that we're going to use in our whole soundness proof. So we're starting from the top, we're going to have a truth value assignment that satisfies the root. We're going to use that truth value assignment to show that there has to be an open branch. And that'll be this notion. There has to be an open branch in the tree. So on this truth value assignment, not theta is true, so gamma union not theta is consistent. This is our root's consistent, i.e. it's satisfiable. This is the thing we get to assume in our proof. Now, the thing we're trying to prove, the consequent, is that it's not the case that the argument from gamma to theta is tree valid. Now, what does it mean to be tree valid? It means that there is at least one tree that has the right root that closes. So we're saying it's never the case that a tree with the given root closes. That's the thing we're trying to prove. So it's not the case that there exists a tree with this root that possesses all closed branches. So equivalently, any tree that has this root has to have an open branch. And if you completed every sentence in it, if you resolved every sentence that's resolvable, you'd have to have at least one complete open branch. So this is what we're trying to prove, assuming that the argument is semantically invalid. Logically, this is not the same as saying the argument's tree invalid, because a tree invalid argument technically just requires the existence of a single tree that has a complete open branch. And we're trying to show that any tree with this root has a complete open branch. We're trying to show it's not the case that the argument is tree valid. Any questions about this stuff? Cool. All right, so we assume that gamma does not semantically entail theta, so we're assuming that the root is satisfiable. So we have this truth value assignment, guaranteed to exist, we'll call it I, that makes the premises true and makes not theta true. And we need to show that any tree with this root has a complete open branch. So equivalently, this is the way you could put it. I guess this is the way the book puts it, because the book does everything just in terms of consistency rather than valid arguments. So equivalently, we're showing if you have a consistent root, a satisfiable root, then any tree that has that root has a complete open branch. Yes, Luna?
Just a quick question. What is the U?
Oh, sorry, yeah, the U just means union. So if you have two sets, so we have some gamma, which is the set, let's say two premises, it could be, some arbitrary number that's finite. Gamma union not theta is just smushing these two sets together into one set. So, if that makes sense. Cool. Yeah, sorry, I technically should have defined that in the slides. Whoops. All right, so yeah, whenever the root's satisfiable, the tree will not close. So some facts about our interpretation truth value assignment I that we'll make use of. I makes theta false and makes everything in gamma true. And since it's a truth value assignment, it has to assign either true, exclusive, or false. So one or the other, but not both, to every atomic sentence letter that appears in the sentences in the root. Because that's what truth value assignments do. Basically, they make a choice of true or false, 1 or 0, for every atomic sentence. So therefore, due to the recursive structure of SL, any well-formed formula that's built from these atomic sentences, its truth value will be determined by our truth value assignment I. So for any such well-formed formula psi, I is going to make psi true if and only if it makes not psi false. So we'll take advantage of these facts. Any questions about these facts of value assignments? All right. So we're just going to introduce some definitions to streamline our proof. You don't have to do this. It just makes things shorter to say. So we'll call a tree good if its root contains the arbitrary premises and arbitrary conclusion of acetone, the negation of that conclusion. So it's good if it's this, so we'll call this thing good. So good tree. That's this for the root. And remember, each sentence is on its own line in the tree. And we're going to say that a branch in a good tree is an I branch if every well-formed formula on it is I true, i.e. true according to I. So I'll write that down just so we remember it later on. I branch, every sentence on the branch, true. Cool. So this is a key thing to note. So remember, we're trying to show that there's always at least one complete open branch. Note that each I branch is open since an interpretation can't make any sentence true and its negation true. It just can't do that. It would contradict the fact that it's a truth value assignment. So given that we're going to show that every sentence on the branch is true according to I, it's going to follow there's never a sentence and its negation on the branch on an I branch. And so every I branch will be open. And that's what we want to show. So proof plan, we're going to show that every good tree has an I branch. And this is going to include all the good trees that we've resolved every sentence, all the completed good trees. And so for those guys, there'll always have to be at least one complete open branch. And that's what we want to show. We want to show that it's not the case that this thing is ever tree valid, i.e. it's not the case that all branches close. So that means it's always the case that there's at least one complete open branch. And remember, so we're reasoning from the top down here. We're starting with the root, starting with the truth value assignment that satisfies the root, and we are generating a complete open branch. All right, so we'll do the setup for induction, but we'll plow through this because it's a little tedious. So the trees have this recursive structure. We got 9 rules that we can use to resolve sentences. And we could do induction over the number of nodes, or we could do it over the number of times we apply a rule. So our base case will be the case with 1 node, and the root, is an honorary node. So our base case is just the root. And then our induction hypothesis will assume that every good tree with n many nodes where n is less than some k has an I branch. So we'll assume that we've got an I branch, i.e. an open branch, up until at least the kth node, where that kth node is down, down in the tree. So we're basically assuming, this was our tree structure. We're assuming at node 1, we're good, at node 2, at node n, and then we get the sum node k that we're going to work with guys are in our induction hypothesis. And so we're assuming that this is an I branch. So this is I branch. And then we're going to show that no matter how we extend node n to node n plus 1, will stay in an I branch. It will remain the case that the new sentences we add from resolving are also I true according to I. And then we'll have completed our induction. So that's our induction step, show that an arbitrary good tree with k nodes also has an I branch. So base case, this is chill. We got our one node, and this just is the root. And the root, as we defined the interpretation I, the root is just true on I. We defined I that way. We chose I such that it satisfies the root. So of course the root's an I branch. Every sentence on it is true according to I. Any questions about this? Cool. All right, so then we consider an arbitrary good tree, which we will call Theodore. And Theodore has k nodes. The names are little mnemonics for us. We care about our trees, and so we want to name our trees. So there has to be some good tree Theo, where Theo has less than k nodes, such that Theodore results from applying one of our 9 STD rules to Theo. So Theodore is generated by an STD from Theo. And we'll call this rule Ruby. So Ruby's got to be one of our 9 tree rules. So basically, this guy here, in our induction hypothesis, this is Theo. And when we extend Theo, we get, node k, and we're calling this whole thing Theodore. So the tree that grows is Theodore. And Theodore, is bigger than Theo. So that's our little knot, right? We're pretty clever here. All right, so since Theo is in the scope of the induction hypothesis, Theo has to have at least one I branch. So Theo's got to have at least one, and we'll call that I branch Ida. So, Theo could have tons of, this could be, lots of things could be going on in Theo, but there's got to be at least one complete, not complete necessarily, but there has to be at least one open branch in Theo that you could call Ida. And now there's a question of where does Theodore come from? Does Theodore come from extending Ida or extending some other branch? So in case A, the rule Ruby extends some other open branch than Ida. Maybe Theodore has multiple open branches and Ruby extends not Ida, but some other one. Well, then Theodore would still have I branch Ida. And so Theodore would still be good. It'd still have an I branch. So this is like a trivial case, not very interesting. But the book misses this case. So this is a good lesson in why you want to set up induction properly, at least if you're writing a textbook, I guess, because otherwise you could miss a case, and that's not good, right? This is a logic class. There can be no gaps in logical space. So case B is the interesting one. And this is where Ruby extends our open branch Ida into some branchlets, applies the rules. There might just be one branchlet because some of the rules just, carry on the same branch, but many rules introduce, multiple branches like the disjunction rules. So we need to show that for any of our 9 rules, at least one of the branchlets remains an I branch. At least one of them remains an I branch. So, questions about this structure? Cool. All right, so another way of putting case B, we're showing the following. If we have some good tree Theo that has an I branch, then so do all the trees that can be built from it by applying a single tree rule. All the possible Theodores from all the possible Rubies. Equivalently, each of our 9 rules preserves the property of having at least one I branch, which again, a branch that satisfies the root. And I guess this should really be a stronger statement. It should be a branch such that every sentence on it is true according to interpretation I. So that's where this is. I is bad. I should change that. All right. So the book basically just begins here at case B, and we've just tediously justified why it's okay. Jump right to case B. So we pat ourselves on the back. So what the book is doing is basically just what we did when we were lazy with SL. We said, oh, SL has a recursive structure. And so whenever you want to prove something about SL using induction, you can just assume that you're at some, complex sentence in the induction step that decomposes into a phi and psi that have the property, and then show that however you combine phi and psi using the connectives, the more complex sentence has the property. The book is basically doing an analogous thing for trees. So, all right. So basically, at this point, you have 9 subcases, and we're not going to do that because we got things to do, places to see. We got to get the completeness and stuff, And I really have no idea how long this sort of thing takes. So if we run out of time, well, that's going to suck, right? So we're just, I think, going to do 2 subcases just to show how this sort of thing goes. And this is often the case, as you guys have seen with these induction proofs on recursive structures. Once you understand the sub of the proof and how to do 1 subcase or 2 subcases, you've basically covered everything, and the rest of them are just the same style of reasoning with a slight change in detail, but you know what to do, and it's not that interesting. So we're going to consider the case where our rule Ruby is double negation, and we're going to suppose that Theo's I branch ida contains not psi, and we're going to imagine that Ruby extends ida to some longer branch Idaho by adding psi, so that's just our rule. Notice how Idaho is longer than Idaho. Whoa, whoa, whoa. Very clever. So we're assuming, because we're in the scope of the induction hypothesis, Ida's in the scope of the induction hypothesis, that not psi is true according to I, because Ida is an I branch. And so therefore, we know, psi has to be true according to I, because if psi was false according to I, well then, not psi would also be false according to I, which would be a contradiction. So, yeah, there's many ways you could say that. So, if it were otherwise, then not psi would be I true, but then not psi would be I false. That would contradict our assumption that Ida is an I branch. And so Idaho is also an I branch, because the only thing additional that we've added to form Idaho is psi that we got from applying our rule, and we just showed that psi is also true according to I. And so Theodore, our slightly longer tree, still has an I branch. And so we've just done our induction step for this case. Any questions about this? And the key thing, as I'll emphasize many times as we proceed, is we're reasoning from the top down. We started with an interpretation that satisfied the thing that was up top, not psi. And then we showed that the thing we added psi also had to be true, according to psi. All right, so our beloved Theodore has an I branch. So a slightly more interesting case, negated conjunction. So imagine that our Theo, at some point, it's got our root up here. These are the roots, and then lots of stuff can happen. But at some point, at some node n that's less than k, we hit not phi and psi. This is node n, let's say. And the cool thing about our, induction proof is this is why we're doing complete induction. There could be lots of stuff after this too. We could be up at node n plus 5, but then when we get to node k, which is greater than n plus 5, we say at node k I'm going to resolve the thing at node n. Because remember, you don't have to resolve things in the order they appear in the tree. So at node k, we're like, yep, I haven't resolved not phi and psi yet. I'm going to resolve that. And so we apply the rule. And this is a branching rule, or a splitting rule. And we get not phi on one side and not psi on the other. And we justify this by writing node n, which really, we need the sentence number, but whatever it is. We'll just say it's introduce something. The sentence number of node n and our rule, which is not conjunction. All right, so at this point, and the thing we're assuming is that at this point it's Theo, and Theo's in the scope of the induction hypothesis. So this branch Ida is an I branch, everything on it is true according to I, and we just have to show that at least one of our new branchlets is true as well according to I. Because if at least one of them is true, then whichever one it is, that new thing, now if it's not phi, that longer thing will be our new I branch. And it'll have to be an open branch because of that key fact we said about interpretations. They just can't make a sentence and its negation true in a single interpretation. So our rule Ruby extends Ida by splitting her into a branchlet with not psi, with not phi and with not psi. And by assumption, we're assuming that the thing we're resolving is true according to our interpretation I. And so therefore, it just can't be the case that I assigns 0 to both not phi and not psi. Because if it did, it'd have to assign 1 to both phi and psi, and hence it would assign 0 to not phi and psi. So if our interpretation made both not phi and not psi false, it'd have to make this earlier thing that we're resolving false. But that just contradicts our assumption, because we're assuming that the negation of phi and psi is true, according to interpretation I. So we get to conclude, interpretation I has to make at least one of not phi or not psi true. It could make both, but it's got to do at least one. That's what we care about. So at least one of our two new branchlets has to be an I branch. Yeah, Henry?
For this, could you just say like sorry. Could you just say like by De Morgan's law for this one?
So yeah, so it is true that basically, and you can help yourself to semantics in these proofs. So in these proofs, you get to help yourself to logical equivalencies, and the proofs rely on that. So basically, as Henry notes, what we're noting in our proof is that the thing that we're resolving is logically equivalent to negation of phi or the negation of psi. So we're using this in our proof, at least implicitly. We're saying, yeah, not phi and psi is logically equivalent to not phi or not psi. So if this thing is true, then this sentence, not phi or not psi, has to be true. And so, therefore, at least one of these has to be true. And yeah, as we'll see, definitely when we get into the test for these, basically, whenever you're looking at these branches, you can think about the branches as being semantically equivalent to the disjunction of the things on the branch. So this branch, splitting thing, basically is not phi or not psi, and you can think about it that way. Cool. All right, so Theodore has to have an I branch, at least one, or so we should. Could at this point have, multiple ones, but we just need this one. All right, so we've done two cases, and now we're going to see how to test alternative rules for sounds, where we're using the same style of reasoning. We're imagining, what if we had some, different rules in our system beyond our 9 rules that are legal, and would they preserve sounds? So we'll call our modified system something like STD star. And in the simplest case, you're just swapping out one of your 9 rules for some other rule for one of the connectives or negated connective. And we get to ask, would our system STD star be sound still? And then later we'll ask, will it STD star still be complete? And these are two styles of questions that you have on the homework assignment. Probably the midterm will have a question like this, because it's a good way to test comprehension of the proof without asking you to read you cases in the proof where all the cases in the proof are in the book. So, that wouldn't be a good test of comprehension. So this is our heuristic for soundless reasoning. The thing to have in your head to start is we're reasoning from the top down. And what we're doing is considering an arbitrary truth value assignment that satisfies the sentence being resolved. So some truth value assignment that makes the sentence at the top of, true, the thing we're breaking down, and then we ask whether this truth value assignment, whatever it is, has to guarantee that at least one node below is satisfied. So this is our heuristic check. So if the answer is yes, then the rule does in fact preserve soundness, because we'd be able to extend our proof just like we did over here. And so we would, there'd still be at least one open branch. If the answer is no, so if there's some truth value assignment that makes the sentence being resolved true, that doesn't make at least one of the branches true, doesn't satisfy at least one of the nodes that were created, then it's going to be possible to construct a counterexample. And at this point, you have to construct a counterexample. So the thing you might forget to do is you might just do the heuristic reasoning. You might see that the answer is no, and you might stop there, and you might say, yep, this thing breaks down. So you can't stop there. You have to construct a counterexample. You must construct a counterexample. And that's just, the fact of maybe we're endorsing some norm on rigor in mathematics where if a counterexample can be constructed, we say, you ought to construct it, show me the money. That's basically what we're doing. If you were really high on non-constructive mathematics, you might say, this is bullshit, man. P or not P. I showed that, this thing's going to break soundness, and so there has to be a counterexample, and I'm done. And I'm going to say that, as the authority figure in this classroom, I don't like that norm, and I'm endorsing something closer to a constructivist norm. So if you can get a counterexample, you got to get a counterexample. Those are the rules that we're playing by. All right, so other things about the counterexample, it has to have concrete sentences of SL, not metavariables. So you have to use actual SL sentences from the real SL. So further heuristic reasoning about truth value assignments is insufficient to disprove them. So for a counterexample to soundness, what you have to do, and so this can, require a little bit of ingenuity sometimes. Normally it's not complicated, but you do have to think a bit, and there's, an infinite number of ways you could go. It's a lot of choices. Our search space is reasonably unconstrained, and so we're like, But so to try to structure your search, what you need to find is a satisfiable root, a consistent set of sentences. Just like in our proof, we started with a consistent set of sentences. And then you apply the modified rule in the tree, and you can use other rules that have already been shown to preserve soundness, because then we can trust that those guys aren't going to be the issue of soundness breaks. It'll be our bad rule. And then you show that the tree closes. Because remember in our proof, we were showing there was always at least one open branch. So in the counterexample, you show it's not the case that there's at least one open branch. So you show the tree closes, and that's counterexample. So, some rationale for why these counterexamples work. If we have soundness, then whenever we can derive theta from gamma, then we have semantic entailment. So a counterexample is just a case where you have a tree valid argument. And remember, tree valid means the tree closes. The tree with root gamma union not theta closes. So tree valid, but you don't have semantic entailment. So in our counterexample, we're starting out in a case where we don't have semantic entailment, but we're showing that it closes. And that's just a counterexample to the definition of soundness. So when we write gamma does not semantically entail theta, gamma, slash double ternstile theta, we're just saying that this root is consistent. And then we're going to show that the tree closes. So another way to put this for why the counterexamples work is to say, well, if the system were sound, if the system of the modified rule were sound, then whenever we had a tree that closed, it would correspond to a semantically valid argument. So if you can come up with a case where the tree closes, but the argument is semantically invalid, then you have a counterexample. Any questions about these concepts? It's really, again, it's just like, it's a lot to hold in your head, but everything's obvious from the definition. So if you get hung up, just write down the definitions of everything and think about what counterexamples mean. Counterexamples to an if-then statement just means the antecedent is true, but the consequence is false. That's all we're doing. All right, so we'll look at two rules, and I think we're not doing great on time, so we'll have to move briskly, perhaps, so we can get to completeness. So this is, some random rule. We'll call it liberal conditional, and what liberal conditional does is it branches an if-then statement into the negation of the antecedent and the disjunction of the antecedent and the consequent. And so you're, imagine you're on an exam, you're confronted with liberal conditional, and the question is, does this thing preserve soundness? And we're in exam mode, so we're stressed out. And we're like, what do I do? And so you just remember, soundness, reason from the top down, at least heuristically. Once you figure out the answer, then you'll be confident how to proceed. So we use our heuristic, and then it's yes, we'll extend the proof. If it's no, we go into counterexample mode. So just heuristically, we're like, okay, top down. We're going to imagine that if I then psi is true on some truth value assignment, and as we noted already, you can help yourself to semantic reasoning in this. So basically, whenever you're in these little proofs and you're seeing conditional statements, typically it helps to think about these in terms of not phi or psi. So remember, an if-then statement is logically equivalent to the negation of the antecedent disjoined with the consequent. So if not psi is true, this thing's got to be true. If psi is true, this thing's got to be true, or both. So we're like, all right, imagine that we had a truth value assignment that made not phi or psi true. Then we think, okay, well, it would have to either make not phi true, in which case this sentence, would be satisfied, and so the left branch would be satisfied, or the arbitrary interpretation would have to make psi true, in which case, psi or phi would also be true, and so the right branch would be satisfied. So basically what we just said is, no matter what truth value assignment makes this thing true at the top, if you have an arbitrary one that makes it true, it has to either make the left branch true or the right branch true. And so we've just seen, okay, this preserves soundness from our little heuristic. And now at this point you go into, a brief argument which is really similar that would just formally extend the proof. And they're not that long, but now you're confident. You're confident that that's the thing to do with this guy, is to formally extend the proof in this case. Questions about that? Cool. All right, and then here's another one. On the far right of our column, we have conservative biconditional. And conservative biconditional just blows up the other branch that the normal biconditional rule creates. So remember, normal biconditional, it branches into a phi psi node, and normally there's a not phi, not psi node. And here, we've been conservative. We've blown that up. And so we want to know, does this thing preserve soundness? So I'll give you some moments to yourself to just think through this. Feel free to write some stuff out. Try to apply the heuristic. I'll make sure that I've accounted for the people in this room by finding their name tags. All right, so Isaac, Henry, Michelle, Selena, got you guys. Is anybody else not have a name tag? We are good. I am present. I'll put my name tag up. What's funny is, if some people who haven't come to this class came in, they actually might not know my name. They might. It's just easy to look at people's emails and not actually remember their name. All right. Raise your hand if you think this thing preserves soundness. Raise your hand if you think it breaks soundness. Cool. Raise your hand if you're not sure. Now you're sure. We said cool after we affirmed it. All right. So this one breaks soundness, and easy way to look at this is phi, if and only if psi is logically equivalent to phi and psi, or not phi and not psi. So whenever the biconditional is true, it means that two things agree on their truth values, and so either they're both true or they're both false. And so this is what our normal biconditional rule is saying. And so now we're just like, all right, some arbitrary truth value assignment that makes the top sentence true, well, it's not guaranteed to make phi and psi true, because it could be the case that it makes not phi and not psi true, in which case phi and psi would be false. And so we're not guaranteed to have at least one open branch. We're not guaranteed to be able to extend, our tree such that, given that this thing was an open branch, that this remains an open branch. And so we have a failure. And so now again, we don't stop. We think, okay, I gotta make a counterexample. So we're gonna have to have a concrete counterexample to soundness with using conservative biconditional, using actual sentences of SL. All right, so for the sake of time, I'll just blow through. We did liberal conditional. And so formally, the way we'd extend our proof of liberal conditional, we would assume the sentence we're resolving is true according to interpretation I. We would note that, okay, I has to assign 0 to phi or 1 to psi, or both. And you could use false and true rather than 0 and 1 if you prefer. I prefer to say false and true. And so in the first case, I would assign true to not phi, satisfy the left branch. In the second case, I would make psi or phi true, so it also satisfy the right branch. So either way, it's the key thing. Either way, I satisfies the new sentences on at least one branch. And when we get to completeness, you'll see the at least gets swapped to an every. And when you reason from the bottom up, you have to show that the thing you're trying to show works for every branch. So that's a key difference between the two. Soundness, top down, you're showing there's at least one branch that satisfies the property. From the bottom up, with completeness, it's going to be no matter which branch you were in some sense coming from in reverse, the property would have to propagate upwards. So we have to conclude liberal conditional does not break soundness. And now with considered biconditional, we do our heuristic reasoning, which we just did. And then we're like, okay, counterexample. And so, there's a lot of ways you could go. Here's one, this might be one of the simplest counterexamples you could come up with. So we're in STD dagger. We've replaced our normal biconditional rule with conservative biconditional. Consider the sentence P if and only if P. And the negation of the conclusion is not P. So in this case, the argument we're considering is P if and only if P. We're wondering, question mark, STD dagger, does this let us derive P? And so we put the negation of the conclusion in the root. That's another thing you're liable to forget, especially if you're stressed out in an exam. Remember, negation of the conclusion. And so then we just apply the considered biconditional. So we cite line 1, we write C, if and only if, and the rule just ends up being P and P. And we notice, okay, this thing closes. So we're like, oh, okay, so this thing is tree valid in STD dagger. But now we're like, is this thing semantically valid? Question. And this is just a question, is there any truth value assignment that makes the premise true, but the conclusion false? And we're like, yeah, let P be false, so assign 0 to P. So if we had false under P, be false on both sides of the biconditional, so the biconditional would be true, but the conclusion would be false, and so we do not have semantic entailment. It's not a logically valid argument. From P if and only if P, you cannot conclude P. You could conclude P or not P, but you can't conclude P. Concluding P or not P is not very informative, because that is tautology. So P if and only if P is not semantically entailed P, because another way to put it is P if only if P and not P is consistent. And again, that's what for the counterexample, the reason we chose this, we knew we needed to have a root that's consistent. We needed the root to be satisfiable to get a counterexample. And in the good case, whenever you have a consistent root, you would have at least one complete open branch. Here we have a closed tree, and so we're like, damn, that's counterexample sounds. Any questions about this? Cool. All right. Great. We did soundness, and and I guess we have 30 minutes for completeness, and it's going to be the same thing, but in reverse. So that's the thing to keep in mind is this is a lot of details, but you get down this pattern of reasoning, and then there's just a second pattern of reasoning where everything just moves from the bottom up. And if you get hung up on things, just memorize the definitions of soundness and completeness, hold them in your head, memorize the contrapositives, how to move back and forth between if-then statement and its contrapositive, and that's basically what we're doing. The notions of tree validity and consistent root, satisfying root. All right, so let's go. So in order to prove completeness, trying to show this if-then statement, now it's double turnstile, signal turnstile. Whenever you have a semantically valid argument, there's some tree that is tree valid. There's at least one tree that has the root gamma union not theta that closes. So one way to think about this intuitively is that we have fully covered our semantic notions by our syntactic rules. We wrote down enough rules, and it basically means that whenever you could have used a truth table, you're now guaranteed for there to be a tree that does the work that the truth table would have done. So you're guaranteed to have a tree for any semantic question, a tree that answers that semantic question. That's basically what completeness is telling you. So again, we're going to prove the contrapositive because it's easier. We'll use induction because we love induction. So our contrapositive, we flip the antecedent and consequent, and we negate them both. So if it's not the case that the argument is tree valid, then it's not the case that the argument is semantically valid. That's what we're trying to show. So we see we're going to get to assume that the argument is not tree valid, so we're going to get to assume that whenever we have this root, gamma union not theta, there's going to be a complete open branch. So whereas before we were trying to show that there has to end up being a complete open branch, now we get to assume at the start that there's a complete open branch. And we're going to use that complete open branch to prove that the argument has to be semantically invalid. So we're going to use the complete open branch basically to construct a truth value assignment such that the premises are true, but the conclusion is false. So if the argument is not tree valid, then it's not semantically valid. That's what we want to show. So now we're like, we just recall what the definitions of these words mean to keep going. So not tree valid means that every tree that has root gamma union negated conclusion remains open, so it never closes even after you resolve every sentence. And we're going to call this open branch Oprah. We love Oprah. You get a branch, we all get branches. So, O for short. O for, those of you who are doing rigorous mathematics that is serious, where we don't have funny names for our terms. So we're going to use Oprah to define some truth value assignment I that makes true every sentence that is on the branch. That's what we're going to use our complete open branch to do. This is the key idea of this proof, whereas before we used a truth value assignment to construct a complete open branch, here we use a complete open branch to construct a truth value assignment. So it's just the reverse of the previous proof idea. So in particular, this truth value assignment that we're constructing, it's going to make true the sentences in the root, and so it's going to show that the sentences in the root are consistent. So it's going to show that gamma union not theta is consistent, and that just means that the argument is semantically invalid. So this interpretation I that we construct, that we're going to show has to exist, it's going to make gamma true and not theta true, i.e. it's going to make the conclusion false, but the premise is true, and that is just a counterexample to semantic validity. And that's what we want to show. We want to show that assuming that we have a tree that never closes, assuming that there is no tree valid, argument here, that also there's some truth value assignment that makes the premises true and makes the conclusion false. And that'll prove completeness. If it's not the case that we have tree validity, then it's not the case that we have semantic validity. That's the contrapositive, which is equivalent to if we have double turnstile, then we get signal turnstile. All right, any questions about this? Proof by D. Awesome. All right, so we consider some arbitrary argument that has some premise set gamma that's finite and some putative conclusion theta. We don't say anything special about these guys. We construct a tree that has this root, gamma not theta. And now we're going to assume that the argument's not tree valid. That's our antecedent of the contrapositive completeness. Assume it's not tree valid. And so every such tree is open, has some opera, and it would extend to a complete open tree if you resolved every sentence. So there has to be at least one complete open branch O. And note that O has to end with atomic sentences or negations of these in the last node, because the only things that can't be resolved further in our tree system are atomic sentences or their negations. Any other kind of sentence can be resolved. So at the very end of our tree, we're going to have those kinds of things. So we see from this, we could do induction starting from the bottom of our tree and working up. And that's one way you could set this up. So if you, and I don't recommend it, if you want to do question 4 on the problem set, which is set up the induction precisely for completeness. This is one proof idea you could do. That works. I wrote it out in the solutions, which you'll eventually see, and it does work. But yeah, it kind of sucks. And so initially I thought we would do this in class, but it's just not worth it, I think, to do it. But it, maybe you think it's a fun exercise. If you want to do question 4, I really recommend answer question 3 as well. It's the only case where, normally if it's choose one or the other, I'll only grade the first one you write down. But I just think you're almost bound to screw up on setting up the completeness proof. There's just so many ways to screw up. I thought about it for like half a day, and as I was like making coffee, I'd be like, shit, I missed the case. Nope, I missed that. So it's just like, it's the kind of thing where you think, oh, this is going to be super easy, but then actually, it's more complicated than it seems. So answer question 3. Don't answer question 4 unless you just want to, try it out for funsies. All right, so yeah, at this point we'd have to figure out what are we doing induction over. We'd have to handle a base case. We'd have to do induction hypothesis. We have to prove that we then use the induction hypothesis in the induction step. So this is an optional homework question. We're just going to go casually, and it'll be clear what we're doing still that we're doing induction. So we're using Oprah to construct this truth value assignment I. And remember, our goal here is I is going to have to satisfy the root, and so that'll show the root's consistent. It'll show the argument is semantically invalid. So since Oprah is assumed to be open, we know right off the bat that there's no sentence and its negation ever appear on Oprah. And this is a key fact. Key fact about complete open branches, you never have a sentence and its negation. And so because of this fact, we can define some truth value assignment I as follows. We're going to say I assigns false 0 to an atomic sentence if and only if the negation of that sentence appears by itself on a node. So this is our definition of I, and we're guaranteed to be allowed to do this because we know Oprah's open, and so we know that there's never an atomic sentence and its negation on the branch, so we can consistently introduce an interpretation this way. And so, what this entails is that I is going to assign true to every atomic sentence that appears by itself on the node. So, for any atomic sentence that appears anywhere on the tree, if that atomic sentence ends up being by itself negated, then you assign false to that atomic sentence so that not that thing is true. Or if the atomic sentence is really by itself, ultimately, then you assign it true. So we see, okay, we're constructing I. At this point, we could say the interpretation I makes true every atomic sentence or its negation, the negation of that thing that appears on the branch. So again, we're just going in reverse of what we were doing with the soundness proof. All right, so now we consider an arbitrary sentence delta that is on Oprah, and our goal is to show that delta has to be assigned true by interpretation I. Now, since delta, is an arbitrary one, if we can show that it's assigned true by I, well then the sentences in the root, they're also deltas. And so we'll have shown all the sentences in the root have to be assigned true by I, and then we'll have shown the root is satisfied. So that's the, this is why this works. So if delta is an atomic sentence or a negated atomic sentence, then we've already handled it by the definition of our interpretation. It has to be true by definition of I. Otherwise, there have to exist some well-formed formula alpha and beta that compose delta according to our recursive definition of SL sentences. So this proof, it's more complicated because we're simultaneously doing induction on both the SL recursive structure and the tree recursive structure, and we're using them in parallel. And that's why it's more complicated to set it up precisely. Because you could, if you wanted to, have two induction indices running around. I don't recommend setting up that way, you don't have to, but you could. So we know, delta has to decompose into some smaller alpha and beta if delta is not an atomic sentence or indicated one. All right, so since OPRA is complete, delta has to be resolved according to one of our 9 tree rules, and this leads to sentences on the child nodes. And one of these child nodes has to lie on OPRA because, OPRA is a complete branch, and so whatever branch OPRA's got to get at least one of the child nodes on it, no matter how you're resolving things. So, are there any questions about this? All right, cool. So, by our induction hypothesis, which we haven't stated, but it's kind of, it's basically, we're assuming that the property holds for everything below delta, and now we're going to show that it has to hold as well for delta. So we're assuming everything that's below delta in the tree is made true according to I, and now we're showing that delta, which is higher up in the tree, also has to be true according to I. And then given this, and so this is the key thing, whereas before it was, soundness, it was at least one of the branchlets. Now we have to show no matter which child node we're starting with on the bottom, no matter where we've come from below, delta would have to be true according to the truth value assignment I. Okay. So once we've done our 9 subcases, or more, based on how you set up the induction, in one way of setting up the induction, you have 15 subcases. So once we've handled all the subcases, completed our heroic quest, then we could conclude that the interpretation I makes delta true, delta was arbitrary sentence on OPRA, and so we'll have shown that I makes each sentence on the root true. And so we'll have shown that the root's satisfiable, and that just means that this argument that from gamma to theta is invalid semantically. We'll show that. And that's what we wanted to show, and so basically we've used our complete open branch OPRA, which we're assuming exists to define some truth value assignment that makes the premises true. So this is our macro picture. And at this point, it's just the work is in the subcases. We just got to show for each of our 9 rules that no matter which child node is assumed to be satisfied by I, the sentence that is resolved would also have to be satisfied by I. So reasoning from the bottom up. All right. So reasoning from the sentences below, back up the tree, and we need to show that for each child node, if the interpretation satisfies it, then the interpretation makes the resolved sentence delta true. So maybe, I'll draw a little picture just to make this a little bit more clear. So imagine that we were at some node K, where now this is higher up in our tree. And this node K has got delta. And just to be concrete, I guess, imagine that delta was like fireside. And, there'd be tons of stuff in between, lots of node ends, so this could be node N, and then somewhere down here, this was like node N minus 5, we'll do N minus 3. So on node N minus 3, we hit a branch. So we branched, and we had 5 side. So I really want node N minus 3 down here. So this is node N minus 3. So we're imagining we resolved sentence delta, which ended up being of the form fireside. We resolved it down at node N minus 3. And there could be lots of stuff, going on after these branches as well. bottoming out in some node, final node on our complete open branch. And we don't, at this point, we don't know which one of these is the complete open branch. We just know that there has to be at least one complete open branch, and that's Oprah. And Oprah is, complete. So either this thing is Oprah, or the thing on the right is Oprah. We don't know which one. But what we do know is that whichever one is Oprah, is such that the interpretation I makes true every sentence that's on it. So we either know at this point that, either our interpretation I makes the sentence phi true, or I makes psi true. And it could be both, but we just don't know which one, and so we have to show no matter which, it has to be the case that I also makes the sentence we're resolving true. So basically, in this case, our induction hypothesis includes everything below node K. Everything below node K that's on Oprah, whatever is on Oprah, we don't know, has the property that it's true according to I. And then given that, we show that the higher up node K is also true according to I. And then since K is an arbitrary higher up node and delta is an arbitrary higher up sentence, this would also include, the root stuff. So what's weird about this is just our node 1 is down at the bottom, and we're doing induction up like this. So it's these indices we've just indexed in reverse. And this way of looking at it. Cool. So that's why I have to show for each child node, because we don't know which one of these child nodes is on Oprah. So we have to show no matter which one's on Oprah, the sentence we're resolving is true. So again, this is going to lead to our heuristic. We're basically showing that either one of the child node's sentences entails the sentence that's being resolved. That's basically what we're showing. Whereas before we were showing with soundness that the sentence we're resolving entailed at least one of the child nodes. Here we're showing that each child node entails the sentence we're resolving. All right, and there's 9 cases to consider, coming from our 9-tree rules. So here's double negation. So here, maybe I should have a K here, keep it for our proof idea. So delta is not phi. Somewhere along we've resolved not phi and phi. Here we know, okay, there's only one child node. So if we have some interpretation I that makes phi true, we just have to show that that interpretation would make not phi true. So by the induction hypothesis, everything that's below this node M has, is true according to I, and so by assumption, phi is true. And so, therefore, it's like obvious. I mean, it's hard to figure out what else to say, right? I has to assign true to not phi. If it didn't assign true to not phi, then it would assign false to phi, and that would contradict our induction hypothesis. So the interpretation I satisfies delta, and we've completed this subcase. So it's super chill. A lot of the subcases are pretty chill. So we move on to another one. So this one is more interesting because it's a branching case. So with negated conjunction, we need to show that each of the child nodes is such that if it's true, then the sentence being resolved is true. So exactly one of the child nodes is going to be on Oprah, but we don't know which one. So we have to show that interpretation I would satisfy delta either way. So if it's the case that, case A, if it's the case that not phi lies on Oprah, then the interpretation I has to make not phi true by the induction hypothesis. And so it'd have to make phi false. And if it makes phi false, then it makes this conjunction false. And we're looking at the negation of the conjunction, so it'd have to make the sentence up top true. So making phi and psi false, and therefore making delta true. So again, in these proofs, we're totally using semantic reasoning, because we're just reasoning about truth value sentence. Any questions about this proof argument? All right, and then case B, if it's not psi that lies on Oprah, then you just do the same style of reasoning. It's going to be exactly the same thing, mutatis mutandis. And so now we've completed another subcase. And so either way, interpretation I satisfies delta. So you could do negated disjunction. And I think, yeah, we got 11 minutes. I think we're going to get through it, guys. Oh, wait, no, we end at 10:55, right? We have 14 minutes. We might have time to spare. That's great. All right, cool. So we can slow down a bit. I know it's a lot to get through. When I do this in the future, it's not going to be at MIT. We're going to spend at least a week on this stuff. You guys are getting this in 1 day. So thanks for bearing with me. All right, so negated disjunction, delta, sentence delta is not phi or psi, and here we only have one child node. And so we're assuming that we have some interpretation I that makes this node true, satisfies the node. To satisfy the node just means to make all the sentences on the node true. So if you have an interpretation that satisfies this node, then it has to make not phi true, and it has to make not psi true. So by the induction hypothesis, I makes both of the children, well-formed formula true, and so it has to make false both phi and psi. Now, if phi is false and if psi is false, then this disjunction is false. And so then the negation of the disjunction is true. So interpretation I makes phi or psi false, so it has to make true, not phi or psi, and so it satisfies delta, which is what we want to show. So we just did another subcase. So you could, we just did 3. There's 6 more to do. They're in the book. You could do them. They're super chill. It's the same style of reasoning. If you get how to do these 3 cases, then you can do, any other case. Cool. This was important. Key fact about our complete open tree. So this matters for homework question 2. Homework question 2 will use the following fact. And this is the key thing here is in homework question 2, you explicitly appeal to soundness, the definition of soundness. From a single turnstile, you get a double turnstile. You do not explicitly appeal to the definition of completeness. Instead, you appeal to this fact. This is the fact that you will cite in your proof. Unless you're really creative and you come up with some other proof idea that I think is possible, right? So complete open tree has at least one complete open branch. Complete open branch never has both a sentence phi and its negation not phi. And it's really this fact is what we used along with some other thing that we'll define on the next slide, a notion of partially complete system. So the key fact is in green. So this is the key fact you can help yourself to on the homework where I modified question 2 to just assume that your system is sound and complete. And then you definitely have this fact at your disposal. You don't have to worry about any logic chopping. So our construction above shows us that whenever we have a complete open branch, we can make true every sentence that's on that branch with the root. It's basically what we just showed. We showed, given that your system satisfies this property of being partially complete, which totally applies for a complete system is also partially complete, then you can construct some truth value assignment I that makes true every sentence that's on a complete open branch. So basically, given a complete open branch, there exists some truth value assignment that makes every sentence on that branch true. That's the key fact that you will use. So upshot, if you have an argument that's tree invalid, that means that there's at least one complete open branch. It should be branch has at least one complete open. Complete open tree is true as well. So yeah. So if an argument is tree invalid, that means there's at least one complete open tree. That complete open tree would have to have at least one complete open branch. And then you could apply this fact to say, based on that complete open branch, there has to be some truth value assignment that satisfies the root. And so basically what this fact is letting you conclude is, if you have an argument that's tree invalid, you get to conclude the argument is semantically invalid. And remember, tree invalidity is technically a different definition than tree validity. And the way to put it is, recall that when we define tree validity and tree invalidity, it wasn't based on the definitions the case that they were mutually exclusive. It seemed logically possible that there could be an argument that was both tree valid and tree invalid. And basically, what we're able to show using this fact is if your system is sound, and if this fact obtains in your system, then whenever you have a tree invalid argument, it has to be not tree valid. So whenever you have a tree invalid argument, it's also not tree valid. So you'll never end up with an argument that's both tree valid and tree invalid. And the proof idea for the homework, the hints on the homework, is basically, imagine you have an argument that's tree invalid. Then you could, you'd say, okay, there's at least one tree that is complete and open. So there's at least one complete open branch. And using that branch, we can make the root, we satisfy the root, and that means there's at least one truth value assignment that shows that the premises do not entail the conclusion. Now, this thing just is the antecedent and the contrapositive of soundness. Remember, soundness, contrapositive, sound contra, is that if you don't have a double turnstile, then you don't have tree validity. So we will have shown from this construction fact that the antecedent is true here. So if this thing, if we don't have semantic entailment, then we don't have tree validity. And so basically we'll have shown if the argument's tree invalid, then it can't be tree valid. And that just entails you can't have an argument that's both tree invalid and tree valid. So that's basically, the homework question 2. So it's super chill. Homework questions 1 and 2, super chill. 3 is chill. And then you choose 5 or 6. And they are these examples of testing alternative rules. And that, just apply the method that's in the slides. And the final method we'll get to in the last 10 minutes for completeness. So, so if the system were sound, then you could conclude that the argument's not true valid. All right, so what does it mean for a system to be partially complete? It just means that, so for the rules that you're using, the sentences on each child node entail the sentence being resolved. So if you had any system, could be more general than the system we're working with, could have fewer rules, for instance. If it were the case that each of the child nodes, when it's satisfied, the sentence being resolved is satisfied, you could say that system is partially complete. And it would have this property that you could construct truth value assignments that make true every sentence on a complete open branch. So if you were working just with 3 tree rules for negation, ampersand, and negated conjunction, it would be partially complete in this sense, and our construction fact would apply to it. So that's there's a sense in which we could weaken one of the assumptions in the homework question, but it's probably not that interesting to work through it. So you just assume that your system's complete, and then clearly this construction fact, which is in green, clearly you can use this. Cool. All right. So testing alternative rules completeness, and then we have accomplished all our tasks for the day. Oh man, mental workout. So we again begin with your heuristic, just so that you can always find your way when you're confronted with a problem and disoriented and stressed out. And so this is our heuristic. Ask whether, ask not what your country can do for you, but what you can do for your country. Ask whether each child node below individually entails the sentence that is being resolved, the sentence up top. So starting from the bottom, do we have entailment no matter where we started from? And if the answer is yes, then the rule preserves completeness, and we proceed to extend our completeness proof for this case, where we reason in terms of arbitrary truth value assignments that satisfy each child node, and we show that no matter what, no matter which child node, was the one that was on the complete open branch, the sentence delta also has to be satisfied by that interpretation. If the answer is no, then we have to counterexample rule, and we proceed to counterexample, and again we have just general criteria for what these counterexamples, the form they have to take. So to show that completeness fails, it is necessary to give a concrete counterexample that has these actual SL sentences, and the thing to look for now is an unsatisfiable root. So you want to find a root that a set of sentences that are inconsistent, a set of sentences where there's no truth value assignment that makes true all those sentences. You want to put those bad boys in your root. And then you apply the modified rule in the tree, and again, you can use other rules that have been shown already to preserve completeness, so any of the other good rules in our system that we haven't swapped out. And then you show that there's a complete open branch. So you show that the tree does not close. And the key thing here, if you're liable to forget to do, is it has to be a complete open branch. So on at least that branch, you have to have resolved every sentence. Every sentence on the branch must have been resolved. Cool. And then this will be a counterexample to completeness. So we're like, well, why is this a counterexample? Why does this recipe work? So recall our definitions. Completeness is saying whenever you have double turnstile, you get signal turnstile. And so a counterexample would be a case where you have semantic entailment, but you don't have tree validity. And to not have tree validity means the tree is not closed. And to have semantic entailment, means that gamma union not theta is unsatisfiable. It can't be the case that the premises are true and the conclusion is false. That's what semantic entailment means. So gamma double turnstile theta means gamma union not theta is inconsistent, i.e. unsatisfiable. So that's why in our counterexamples we're looking for an unsatisfiable root. And this thing means it's not the case that the argument's tree valid. Now this is where it gets a little complicated, and I was a little concerned about this myself, because the book just does these counterexamples, but it doesn't really justify why they work. And by constructing a single complete open tree, you're not showing that it's not the case the argument is tree valid, because that's a claim about all trees. To show this, you have to reason arbitrarily about any possible tree with the given root, and that would suck, right? It wouldn't be like a single counterexample. So the reason the counterexample method works is from the completeness proof, we know that if the system were complete, then we could use any complete open branch to construct a tree static that satisfies the root. But we're working with a root that's unsatisfiable. So if the system were complete, we'd have a contradiction. We'd be able to construct something that we've shown can't exist. And so it's, basically, if we get a complete open tree, if we show this argument's tree invalid, which does just require the existence of a single tree, then we will have counterexample completeness, basically by a reductio argument. So that's why this method of counterexamples works. And because this is a reductio, you might think, oh, damn it, this isn't as constructed as we hoped, and that is maybe a bit of a bummer. But isn't life a bummer often? So we have our two rules again, and we can do the same question but now with completeness. So do these preserve completeness, or do they break them? If they break them, you do a counterexample. So again, we're on an exam, we're bewildered, we're like, shit, what do I do? You've already done soundness at this point, and so now we go from the bottom up. So we did the top down, now we do the bottom up, and we're just asking, is it the case that each child node, if it's satisfied, if it's made true according to some interpretation, then the sentence up top also has to be true. That's what we're asking. So if not phi is true, then is it the case that not phi or psi has to be true? And we're like, yeah, that'd be good, right? Yeah. So, but I'm pretty sure. Am I having a brain fart? It does seem true. If not phi is true, then that would entail if phi is psi, right? And if psi is true, then that would entail if phi is psi. So this one would also reserve completeness, but I feel. Oh, this is where. Oh yeah, that's all right. So this is really you can get tripped up. So be careful. So if this branch is fine, this branch doesn't fail the thing about it. But psi or phi, so if psi is true, then this would be true. But imagine psi is false and phi is true. Then this child node would still be true, but the thing up top would not be entailed. So, I had a brain fart, you guys had a brain fart, so be careful. So this thing does not preserve completeness, because there's a way to make this child node true that doesn't make the sentence being resolved true. And so once we've noticed that, we would then proceed to a counterexample of concrete sentences, where again, we're looking for an unsatisfiable root on a tree that is complete and open, That's our criteria for a counterexample. So, here's one that works. Ton of ways you could do it. Notice that, we have, in this case, 3 sentences in the root. There's probably a way to do it with 2 sentences. But basically, the intuitive thought here is something like, we're used to modus ponens reasoning, if P then Q. So the argument here is P, the antecedent, if P then Q, and then the conclusion is Q. So in the tree, we put not Q. And, we're used to this being a semantically valid argument. It is the case that if P then Q, P semantically entails Q. So this is just, semantic truth. But with our bizarre rule of liberal conditional, we just showed with liberal conditional, this is a tree invalid argument. Because this is a complete open branch. We applied liberal conditional, and we saw, okay, the left branch closes, but Q or P. Now remember, this is where you have to remember to resolve this. This is not yet resolved. You need a complete open branch, something you're liable to forget to do. I forgot to do that when I made the slide, and I was like, shit, I need to resolve that sentence. You encounter a problem, you gotta resolve the problem. We are problem solvers. So Q or P, and then we notice, okay, this rightmost branch, this is open, it's complete, so this is tree invalid, so this is a counterexample, and again, the thought here is, if STD star were complete, then from this complete open branch, you could get a truth value assignment that would satisfy the root, but the root's unsatisfiable, we know that, and so this STD star system can't be so cool. And then, you're liable to forget to complete your open branch. So we'll end here, and the reasoning for this guy is pretty chill. This child node, if it's true, has to entail the sentence above. So conservative biconditional preserves completeness, and you would just extend it. So you guys should be set up for success on the homework. I have office hours right now for an hour, and Friday 1:30 to 2:30. The homework's due at 10 p.m. on Friday. 10 p.m. Friday. If you guys, since you guys are in class, if you have any issues with that, just feel free to get in touch with me. And I will comment upon your situation. You came here today and you sat through this pretty intense lecture, so thank you. Okay, so when we're looking at this Baller property, we think, okay, base case, atomic sentences are obviously contingent. There's some truth value assignment that makes an atomic sentence true, some truth value assignment makes it false, therefore, an atomic sentence can be true or false, and so it's contingent. In the induction step, you consider these 2 arbitrary sentences, assume each of them is Baller. Now, if you're going to form not phi, and if phi is, has a binary connective, then of course not phi would have a binary connective. So that is easy. Otherwise, phi is contingent, and then not phi would also be contingent, because whenever phi is true, not phi is false. Whenever phi is false, not phi is true. So not phi would be contingent. And then in the remaining 4 steps, you're adding a binary connective. That's how you're forming the bigger sentence, and so obviously that would contain a binary connective. And so those are all the cases, and that's the proof. And so, you should be able to write that out. So this is just written out in more detail, blah, blah. And so the induction step, so you can just say, we're going to use our lazy SL schema, consider 2 arbitrary well-formed formulas phi and psi that have the property, i.e. that are Baller, show that any way of forming a more complex formula from these 2 also has the property applying, the recursion clause of our definition of SL. So here, in this case, really the interesting one is the negation clause, and the other ones are trivial. And in the negation clause, you have to consider these two cases. Okay, well, what if phi is contingent? Blah, blah, blah. What if phi has a binary connective? Blah, blah, blah. And in both cases, you see that not phi is going to be baller, either because phi is contingent, so not phi is contingent, or because phi has a binary connective, so not phi has a binary connective. And then in the remaining 4 cases, you just get to say, well, okay, we're combining phi and psi with the binary connective. Obviously, the resulting thing has a binary connective. Okay, so every sentence is baller, and then you just get to conclude your proof by noting, well, okay, if you have a well-formed formula that doesn't have a binary connective, it's still baller, because everything's baller. We're living in a baller world, and I'm a baller girl, we might say. So it has to be contingent, and that's the end of the proof. Just don't forget on the exam to do this last part. And then here's a mega hint. Oh no, we didn't get to the mega hint yet. There will be a mega hint for the actual exam problem. If you wanted to, of course, you could, do non-lazy induction and just do complete induction over string length. And so if you wanted to, set it up this way, you're totally welcome to. It's just going to, take a little bit more time. So then your induction hypothesis, you'd say, assume every SL sentence of string length n, where n is greater than or equal to 1 and less than k as the property, show that any arbitrary sentence of length k is baller. And then you'd say in the induction step, consider an arbitrary sentence delta of length k. Then, by the recursive definition of the SL sentences, there must exist these shorter phi and psi such that delta equals one of these 5 combinations. So you could totally say this if you wanted to. It's just going to take more words. I think you have enough time to do that. You guys don't rush on this test. You're going to have plenty of time. So just slow down and debrief, relax. Then you would just do the same thing we just did. Cool. But the key thing is you can use the lazy induction schema for SL. You cannot use the lazy induction schema for the palindrome question. For the palindrome question, I want you to explicitly write the induction hypothesis as if you're doing complete induction and be explicit about that. All right, so here's a mega hint for the actual question. So on the actual question, it's going to be a property about conditionals. And really the only part of the proof that isn't super obvious is the clause involving the conditional. That's the one that's going to take a little bit more thought. And so if you get stuck on thinking through that on the midterm, you'll have this slide. Just remember this fact, that if you have you can cite this fact. If you have a conditional, if P then Q, then if there is some truth value assignment that satisfies the consequent, that truth value assignment satisfies the conditional, regardless of what that interpretation assigns to P. So basically what this is telling you is, if you knew that your consequent Q wasn't a contradiction, so if you knew Q wasn't a contradiction, then you basically know there has to be some truth value assignment that satisfies Q. And if your goal was to show that if P then Q is not a contradiction, you'd just be able to say, well, I know that the consequence is not a contradiction. That just means there's some truth value assignment that satisfies it. And whenever the consequent is satisfied, so is the conditional if P then Q, regardless of what P is. So the thing that I think some people are going to screw up on the midterm of this question is they're going to be talking about both the truth value assignments of P and Q in this case, and then things could just get a bit screwed up. So this is the relevant thing. All right, any questions about induction? Cool. If any questions pop up later, then feel free to raise them. All right, so trees. So there's going to be at least one tree question. And this, I think, is something, you probably don't want to type this on the test. Everything else you probably could type. I'm probably going to make a little Canvas text box submission for those of you who would much prefer to type your answers. The trees, it's not going to make sense like the typeset of tree on a test. So you're probably going to answer all these on paper. Old school way. So just some key definitions. Something is a tree contradiction if there's a tree that starts with that sentence and it has only closed branches. So remember that. Tree tautology, something's a tree tautology if there's a tree that starts with its negation and has only closed branches. You gotta remember the negation of the thing. Okay. So those are two definitions, and then we also have the definitions of tree valid and tree invalid. And so this is using trees to test whether an argument or not is deductively valid. So you have some argument that is some premises, some set of premises, and a conclusion. And the thing to always do is you construct a tree with the following root. So you have all the sentences that are your premises, each on their own line with its own number. And then you have the negation of the conclusion. So don't forget to negate the conclusion. Negate the conclusion. Have that in RAM. And then you apply the tree rules until either every single branch closes, in which case you get to conclude the argument's tree valid, and then because our system is sound and we have this completeness fact, you get to conclude that it is a deductively valid argument. Now for that, you just need soundness, And then if instead you had at least one complete open branch, then you would get to say the argument is tree invalid. This is an invalid argument because our system is sound and complete. Questions about this? Cool. Remember, it's very explicit. Remember, add the premises to the root, add the negation, resolve the sentences until either every branch closes. If a branch closes, remember to draw the little X and cite the line numbers of the sentence and its negation. That show that the thing closes. Remember to do that. Or you have a complete open branch, you write the little up arrow, and you only have a complete open branch if you've resolved every sentence. That's what it means for a branch to be complete, that every sentence has been resolved. And then don't forget to justify each new node. Branch closes whenever you have a sentence and its negation. They don't have to be atomic sentences, just any sentence and its negation. Just like in our indirect proofs for the negation, intro, negation, elimination. It'd be any psi and not psi. Or, and the subproof. Alright, so same for tautologies, blah, blah, blah. Some things that you're liable to forget on the exams will be stressed out and rushing. So just remember to slow down. Remember to number each line. So each horizontal row of sentences gets its own number. Remember to justify each of the child nodes by citing the line number of the sentence that you're resolving, and then list the rule that you're following. And then remember to justify the closed branches by drawing this little X symbol and cite the line numbers of the two sentences, the negation and the unnegated sentence. Another thing you're liable to do, don't apply any semantic equivalencies. Don't take advantage of any logical equivalencies in the trees. The trees are purely syntactic. So for instance, if you're resolving the sentence not D or E, then this is going to end up being not D stacked on top of E. So in our little tree, over in tree land, so we have this guy on some line M, not D or E, and then some stuff could happen, and then on some line S and S plus 1, we would write not D and not E, and we would cite line M, and this is not or rule, so the negated disjunction. The key thing is you have to write not D here. You can't immediately write D, because that would be to basically implicitly do the double negation rule. And now if I wanted to write D, I'd have to on some later line cite line S and say that I use the not rule. Any questions on that? Yeah.
What are the line numbers? So if you have multiple things in the same line, it's still one.
Yeah, still one. Yeah, totally. Yeah. So that it's the line numbers. They're basically just tracking horizontal rows. So if you're writing on a line paper, and it's basically every single line of your line paper that has a sentence on it would get a line number. Yeah. And it's with the justification steps. If you end up having two trees where there are equal line numbers that justify by different rules, you could just introduce a new justification column if you wanted to. So that's, you're at liberty to do that. But typically, you can often just keep all the justifications in the right. But it's not going to be an insane tree or anything. Again, I'm not out to get you guys, so. All right, so yeah, the tree metalogic stuff, the testing alternative rules. So this is stuff, I feel like I'm going to flag some stuff to write down on like a cheat sheet. Some of this you might want to have like right in front of you, maybe on like, if you have one of these tree rule things, you can even just write this on the back of your tree rule stuff so that it's right in front of you. You don't have to be, stressed out looking around for strategy to follow in like the counterexamples, for instance. So remember our soundness definition. Something sound if from single turn style we get to conclude double turn style, and it's complete if from double turn style we get to conclude single turn style. So basically, if we can go from semantic entailment to deductive entailment, then it's complete. And then, these are equivalent contrapositives, blah, blah, blah. We use those in the proofs. So yeah, remember when we wrote this gamma / single turn style theta, this meant it's not the case that the argument from gamma to theta is tree valid. And so this just means it's not the case that there is some root that has premises gamma and final sentence in the root not theta that has all closed branches. Blah, blah, blah. So yeah, there's going to be some question about a modified system where we swap out one rule for some other rule, and then we'll call that, STD star, some name. And then you guys will be asked, is the modified system sound? Is the modified system complete? And so there's just a series of steps to go through, and it's these steps I probably have written out in front of you, are easily accessible so that if you had it totally memorized, then great. But it's it's easy to mix up because you got to do one thing for soundness, do another thing for completeness. You might be stressed out and mix them up. There was one time in elementary school where I had to memorize the regions of the U.S. and the regions of Pennsylvania. And I had them all right, the geographic regions. I had them all right. And then, in a moment of exam insanity, I swapped them. So I labeled the regions of the U.S. with the regions of PA and vice versa. That's the kind of thing you could do with soundness and completeness. And it's just a mad bummer because you go from getting everything right to getting everything wrong. So just from, inverting. Don't do that. All right, so yeah, cheat sheet. I have the steps for checking whether a modified rule preserves soundness and likewise for completeness. And then on your little note to yourself, note how to formally extend the proof for soundness, how to formally extend it for completeness, if that's what you have to do. And likewise, note what you have to do for a counterexample. Note the form that a counterexample has to take in order to have one for soundness or a counterexample to completeness. And yeah, so you probably want to just have this right in front of you. If you're scrambling for it, you'll probably still be fine. But why not be chill? Just have it right there. So you can always start out with a little heuristic argument. And this is what I like to do this because I think it's just easier before you get into let me do the formal extension thing, let me do the counterexample, just to know what the answer is. Often it's just helpful just to be able to figure out what is the answer. So the heuristic for soundness checking is you reason from the top down, you consider some arbitrary truth value assignment that satisfies the sentence at the parent node, and then you just ask, is it the case that at least one child node is satisfied? And that's the key thing, is at least one. And if that is the case, then your rule preserves soundness, and you would proceed to formally extend the proof. And if the answer was no, then you'd be like, oh shit, this thing is not sound anymore, and now I need to construct a counterexample, and now I need to know the form that a counterexample takes to soundness. So this is something you probably want to write on your little sheet, because you need a concrete counterexample with concrete sentences of SL. And so this is what you need for a counterexample of soundness. You need to have a root that is consistent. So your root has to be a set of consistent sentences. It could just be one sentence. Often, these counterexamples, you only need one or two. sentences. So you need those sentences in the root to be semantically consistent with each other, i.e. there's some truth value assignment that makes them both true, or if there's just one sentence makes them true. And then you have to apply your modified rule, and you can use other rules as well that we've already shown don't mess with soundness. And your goal is to show that the tree closes, show that there's no complete open branches. So this is what you need to do for a counterexample of soundness. So again, you're liable to just not remember this stuff when you're stressed out in RAM. So I would just have it in front of you. Okay, for a counterexample for soundness, I'm going to need a consistent set of sentences. It might just be one. I need to apply the rule, and I need to show that it closes. So then you end up constructing a little tree. Any questions about this? Cool. And then, you can think about why this works. We're just saying that when the tree closes, we have a tree valid argument, but the fact that the root is satisfiable in this case just means that we don't have semantic entailment, because the not have semantic entailment just means that gamma is consistent with the negation of the conclusion, and that's what's going on in your root. Cool. All right, and then same for checking completeness. Here we have this heuristic of bottom-up reasoning. And so to figure out just, if you want to know the answer, is this thing going to preserve completeness, you just consider each child node on its own, and for each child node on its own, you consider a truth value assignment that satisfies the sentences in that child node, and then you ask, is the sentence in the parent node, is that also going to be satisfied? And you do that for each of the child nodes, reasoning from the bottom up. So if the answer is yes, then the rule preserves completeness, and you would formally extend your proof. And if the answer is no, then you'd say, okay, I'm going to need a counterexample to completeness, and that has, some other form. So the counterexample for completeness is you need now an unsatisfiable root, and you need to show that the tree has a complete open branch. So that's why I have this stuff written out, because this is what you could screw up if you find out that your rule is going to break soundness, but if you construct a counterexample like this, it's not going to make any sense. So you would only use a counterexample like this if you find out your rule is going to break completeness. Okay. And you can justify why that works, but we don't really care. It's going to be just one of your points. All right, so a common mistake, if you're doing the counterexample for completeness, you might forget to complete your tree. Okay. So we had these two examples, and to make the goal less abstract, we'll just talk through the conservative biconditional example. So here's our alternate rule. We've replaced the normal if and only if rule with this one that just has one of the branches. Normally we have another branch over here that have a not fine and not sign. And so we ask, okay, is this thing sound? So basically, our mentality on the exam is like, you're confronted with a rule you've never seen before, and you're panicking, and the first thing you want to find out is just, okay, is this thing, sound or not? So you think, okay, reason from the top down. We consider something that satisfies the top. That would mean that it assigns the same truth values to phi and psi, either both true or both false. Would that entail that it makes phi and psi true? And we're like, no. Because it could make not phi and not psi true, in which case it wouldn't make phi and psi true. So we're like, okay, this thing's not sound. And now we're thinking, I'm going to need a counterexample of soundness. And have in front of you, what it means to have a counterexample of soundness, and you'll go about constructing one. And then you're like, okay, is this thing going to preserve completeness? We reason from the bottom up, and we say, any interpretation that satisfies the bottom makes true both sentences on the bottom, so it makes true phi and psi. And now we ask, does the truth of phi and psi, if whenever phi and psi is true, does that mean that phi if and only if psi is true? And we're like, yeah. Because if phi and psi is true, then individually phi must be true and psi must be true, so they have the same truth value, and this thing's true whenever the two things on the left and right have the same truth value. So heuristically, we think, yeah, completeness is reserved, but we need to formally extend the argument, which is pretty similar to what I just said verbally. So, okay. So it's all written down, what we just talked about. So when you reason the top down, you get to help yourself now to what this thing's logically equivalent to, because we're reasoning ultimately in terms of truth values. So we see it's equivalent to this disjunction. We see the bottom is equivalent to phi inside. We notice that this disjunction does not entail this single disjunct, because this thing could be true in virtue of the right disjunct being true. So we got to make a counterexample, and now we're like, what is the counterexample to soundness? It's you need a consistent root that closes. Consistent root on a tree that closes. So here is a simple one with two sentences. We have a premise, P if and only P. We have a conclusion, so negation of conclusion, not P. And we apply our conservative biconditional rule. That gives us a P and a P, and this closes by lines 2 and 3. And so we have a tree that closes with a satisfiable root, and so this thing is tree valid in our modified system, but it's not, the argument's not semantically valid. So it's the counterexample to sounds. Any questions about this? Cool. All right, and then, so you could write a little justification about this to explain your tree. I recommend, explaining your tree at least a little bit. You're trying to communicate understanding to the grader. So explain a little bit why this, why your counterexample is the counterexample. Okay, and then to extend the proof, we only have one child node, so we just need to figure out, do the sentences on the child node entail the sentence up top. So formally we say basically something like, since there's only one child node, we know that phi and psi are lying on a complete open branch that we're assuming exists. Remember, in the proof of completeness, we assume from the start there's some complete open branch, and our goal is to use that complete open branch to construct a truth value assignment that satisfies every sentence that's on that complete open branch, which we call over. We love over. So here, we have one child node, so phi and psi have to be on this open branch. So phi and psi have to be assigned true by the interpretation that we're using over to construct. And we just ask, is it the case that the parent node also would have to be assigned true? So phi reduction hypothesis, phi and psi are true according to I, and hence, if phi and only psi also has to be true, you could say another sentence to justify this because phi and psi have the same truth value, maybe they're both true, so this thing's true. And that's what you have to show. Now, if you had multiple child nodes, you would just do the same kind of argument for each one. So basically, all you're saying in this formal extension is, something like, consider the left child node. If there's an interpretation I that satisfies the sentences, then show that interpretation has to satisfy the parent node, and then you get to say, okay, so in this case, our parent node sentence would be true on this interpretation, if it were the thing on, if this were the open branch that we were considering. Now, in the next case, if instead it's the right child node that's on the open branch, then we'll have some other interpretation I prime that satisfies its sentences. Show that in that case as well. The parent node would also have to be satisfied by that interpretation I prime. If there were a third child node, you just do the same thing. So, any questions about this? Cool. All right, we're crushing it. So I think we're through we're through the written portion of the midterm. So that's the written portion. And in terms of exam strategy, I feel like possibly it could make sense to do the Carnap portion first, which could be faster, and then you'll just feel like you have way more time for the written portion. Slow down your thinking with the written portion. Because the Carnap portion I did, honestly, in like 11 minutes. So the Carnap one you could do fast. Again, I recommend you take your time. And the written portion took me like 25 minutes. So if you were really going to, be totally cool, calm, collected, you think you could easily, spend like 20 minutes on the Carnap portion and 50 minutes on the written portion. and then you still have 10 minutes to spare. So again, the key thing, don't rush. I really don't think you guys are going to have to rush if you know what you're dealing on all these kinds of problems. All right, so for the translation stuff, I uploaded to Canvas a nice table of listing what the words correspond to in connectives. So if you really get stuck, you could pull up this table from Canvas. We'll talk through some of the cases. The key ones to have in RAM, well, I guess I won't spoil it. We'll leave it on the slides. But yeah, so this is a handy table. You're not going to see any words that really go beyond these. So if you really got stuck, you could pull this table up. Okay. So unless, which, as we've talked about, it's not really natural. I'm not sure what's happening in English. So just translate it as or. So here's an example. I am not going to not vote in the midterms unless a meteor destroys my polling place and the city of Cambridge does not give me an alternative location. So you guys will be given the symbolization key, so you won't have to come up with, what should I represent as atomic sentences? You'll be given that. It's honestly like half the battle. So you're starting, effectively with a handicap, which is great. So try to write this one out, to test your comprehension. I'm using vote so capital V for one of the atomic sentences. I'm using capital E for another atomic sentence, destroys, and then I'm using capital A for another atomic sentence. So see if you can schematize this one. We love logic. I guess so that one of the sentences on the midterm will probably be a little bit of a mouthful, so I'll give you, I'll write it out for you guys so that when you see it, you will be used to it. Because, again, it's like part of taking the test is just you're encountering strange information, right? So one of the sentences on the test will be this one. The exam, there will be sentences that involve the independent clause, I fully and completely accept myself. And this will be schematized by A. So one thing to note about this, and this will itself probably be an exam question, could we break this one down further into more basic atomic sentences? What would our more basic atomic sentences be? Somebody want to say it? Yeah, Marcus.
You have I fully accept myself, and then I completely accept myself.
Great. I'm glad you feel the way about yourself, Marcus. The way Marcus feels about himself is the way that each of us should feel about ourselves. So this one could be broken down further, but just to prevent, having another sentence running around on the exam, this will be schematized as a single sentence. And you guys will have the symbolization key, but basically, I'm using this convention to help you not screw up. If you see a capitalized word in a sentence, normally that's a mnemonic that capital letter is the sentence letter. So just to have that. All right, so this one, I am not going to not vote in the midterms. We think, okay, this is a double negation. It's not the case that I vote, so that's a not V. Then we have an unless, so we think or. And the punctuation they basically help you get parentheses. So we're thinking whatever comes after this punctuation is going to be together in some kind of parenthesis. So we're going to have or, parenthesis, capital D, ampersand, A. That's our thing. So not B, or, parenthesis, D, and not A. So similarly, if you saw something like a semicolon on a question, the semicolon will typically indicate that whatever comes after the semicolon is going to be, in its own parentheses. Just like a totally separate thought. All right, any questions about this one? I really hope this doesn't happen. I'd like to vote in my neighborhood library. All right, so provided that lonely if and given, these all flip the order of the antecedent consequence. So this is something you're really liable to screw up on these translation exercises. Slow down, take your time. If you see Q provided at P, you have to remember the P is the antecedent, the Q is the consequent. So you do not want to write if Q then P, that'll be wrong. You're going to have to remember to flip the order in your schematization. Likewise, if you have a lonely if, and if all by itself. So if you have Q if P, then that is schematized as well as if P then Q. You got to flip the order. And same for a given P. So Q given P is if P then Q. So each of these three flip the order. So memorize that or have that, easily accessible, something that totally people are going to screw it up. But not you guys. Some of you might still screw it up. It's okay. It's hard to follow. So now only if is different. If you have only if, then the order is preserved. So if you have P only if Q, then there's if P then Q. And so, in these questions, you're going to have these things running around together. So you're going to have to keep it straight. The lonely if versus the only if. So you probably just want to have this memorized or written in your immediate cheat sheet. Right? Again, it's open note and stuff, but some stuff could make sense to have just written out right in front of you, readily accessible. So in this case, words preserved. And a way to remember this one is if someone says P only if Q, they're really saying if not Q, then not P, and that is the contrapositive of the conditional. And as we've talked about a lot, a conditional is logically equivalent to its contrapositive. So if not Q, then not P just is if P then Q. So that's why P only if Q gets translated as if P then Q. Cool. So just in case gets translated as if and only if. This is one we might not have talked about before. And just in case we hadn't talked about it before, I thought I would mention it now. So here's an example. I will do well in this class just in case I do not party every night. So try to schematize this. This one's chill rate. Probably do it in the mind's eye. I'll write up another sentence to have in RAM on our thing. I think this isn't one of the midterm sentences. There is sentence E. I am enough. You can tell this is going to be a therapeutic midterm. You're going to read this midterm, and the midterm's going to be telling you to feel better about yourself. And you're just like, wow, what a nice midterm. Most midterms make you feel worse about yourself, but not this one. The moral of this midterm is, you should fully accept yourself. That's the moral of the exam. We're not going to prove that. It's in natural logic. I don't know. That's not a theorem. Maybe we could define a property of radical acceptance, right, and prove that every SL sentence radically accepts itself. It's a thing you can do syntactically, right? All right. So I will do well in this class just in case I do not party. So we have capital W, so W, if and only if not P. So as of this one, W if and only if not P. Any questions about this? Cool. All right, so we have although and but, and although and but are translated as and. So this is something that, you might just not think about that often, but it's true. So if you have something like this, although I meditate every day, I remain an anxious person, but I hope to overcome this in the future. We have an although, and we have a but. So try to schematize this one. All right, so we have capital M. This although is basically telling you, okay, we're conjoining with something else, namely I remain an anxious person, A, and then this but is and, so capital H, I hope to overcome this in the future. And you could use different parentheses here, and it would be the same. You could have M, open paren, A, ampersand H, close paren, be equal. Cool, all right, so truth table stuff. So there'll be some truth table questions and, some definitions to have in mind, which presumably you've memorized at this point. If you're going to use a truth table to prove an argument's valid, you have to complete the entire truth table. Because you have to show that there's no truth value assignment that makes all the premises true while the conclusion's false. You have to show there's no counterexample to validity. And that requires the full truth table. So, if the conclusion was a tautology, then of course there would never be a counterexample, because the conclusion would never be false. You can only have a counterexample on a row of the truth table where the conclusion is false. So if you instead, find out, if you realize your argument's invalid, then you only need a single truth value assignment that is the counterexample to validity. So you just need a single TVA that makes the premises true, but makes the conclusion false. And that's enough to solve the problem. And you don't, in this case, have to do the whole truth table, and Carnap will let you enter the relevant counterexample truth value assignment. And so let's just show what that looks like in Carnap, so that you guys have that in mind in case it proves relevant. But again, if you're uncomfortable with that, you can always do the full truth table. So if you're killing time, you can do the full truth table. I don't know what would happen if you entered the right answer for the counterexample validity, but then made a stupid mistake in your truth table. I don't know what Carnap would do, but presumably I would see both. I don't know. We might find out. So here is a problem, and this is, I uploaded to Carnap all the problem set questions in a way that you can have full checking on them. So problem sets 1, 2, and 6. If you want to practice any problem and have the checking mode, you can open up this page. It's linked on Canvas as well. And you can just practice, if your heart's content. So, all right, so we have this thing, and we want to know, are these equivalent? And it can always help. You could just blindly attack. You can think semantically to get your bearings. And we think, okay, what does it mean for if A then B to be false? It means A is true and B is false. And so whenever this thing's false, its negation's true. So its negation is true whenever we have A being true and B being false. And now we're like, okay, well that's totally different from not A, not B. So we think these are definitely inequivalent. So there's going to be some truth value that shows they're not the same. And we think, okay, what if we made A true and B false? Then this thing will be false, and so this thing will be true. And over here, we'll have not A will be false, and so the ampersand will be false. So here we have, they disagree on the truth values. This is our main connected for this one. It's not. This ampersand is our main connected over here. And so what Carnap will do, you don't want to complete the whole thing, you can just enter the truth value assignment that is the counterexample. And the syntax for this is you use capital T's, capital F's, no spaces, have to be capital letters, not allowed spaces, and you write them in the order that the atomic sentences appear, left or right in the table. So that's the key thing. It has to be entered in this left to right order. So here are counterexamples, the second row. So the counterexample is capital T, capital F. So that's what I enter into Carnap, capital T, capital F. Any questions about this syntax? So for instance, if there were like, 5 atomic sentences, then you'd be entering 5 things, and then I hit enter or OK, and here, because we're in the checking mode, Carnap is nice and tells me success and turns my thing green. You guys aren't going to have any checking in the Carnap portion. It's all going to be no green, no green lights. So you could submit incorrect work. It's not going to tell you it's incorrect. So I can't remember what it tells you in that case. I think it's just, maybe it asks you like, are you really sure you want to do this kind of thing? Like, are you really sure that this is counterexample? And then you commit, right? You say yeah. So that's our syntax for counterexamples to validity. And then same thing so this was counterexamples to equivalence. And then you can do the same thing for counterexamples to validity. So here, here's a case of an argument. We're wondering, is this argument valid? And again, you could do the entire truth table to see, am I going to hit some row where the premises are true and the conclusion is false? Or you could just, reason through this bad boy and say, well, you only get a counterexample if you make W false. So we're immediately focusing on cases where the conclusion is false, and that's just assigning false to W. We want to see, can we make the premises true? We'd have to assign A true, and we'd have to assign Y false. What would happen to these guys then? A and Y would have different truth values, and so the negation of the biconditional would be true. And so, we're like, yeah, there's totally an assignment that is a counterexample. And the row that we just talked about was this one, the second one, where A was true, W, we want W false, yeah. So, this one, I guess the one we just talked about. A was true, W was false, the conclusion is false, and Y was false. And Y being false made not Y true, and it also made not Y just in case A true. So rather than fill out the whole table, we could just go type in TFF and just double check that that's the order. You're following the order here, AWY, and then you commit. And here we're told, great, we did it. But again, you could do the full table if you want. And remember, you'll have submit buttons in Carnap. Don't forget to press submit at the end. I'll try to remind you guys about that as well. So cool. So that's the table stuff. Blah, and then the last part is the natural deduction. And again, they're not going to be insane natural deduction. There's going to be probably just 2. And I think you can do each one in 10 lines or less, around 10 lines. So if you're doing like insane stuff, if you're like over 15 lines, you've probably gone off the rails or you've adopted a needlessly complicated proof strategy. So the rules to definitely have, in memory or to practice, used on it before. No disjunction elimination, no conditional introduction, how to use it. This is a subproof rule. And then know the negation, intro, negation, elimination rules. Understand the syntax for starting a subproof. You tab in, you write :AS. And for the rules that cite a subproof, remember that you have to use a hyphen when you are in the justification, part, and you're citing the subproof. You have to hyphen the line numbers, at the start of the subproof and the end of the subproof, even if the subproof itself is only 2 lines long. You still have to use hyphen because you're citing the entire subproof. So you'll want to know how to use conditional introduction. And the basic strategy here is if you're presented with a conditional as your conclusion, then you're thinking, okay, I'm going to need to construct a conditional. My last, rule is probably going to be conditional intro. So you're going to need to start a subproof somewhere that has the antecedent of that conditional. And then from the antecedent and whatever other premises you have, your goal is to get the consequent of the conditional as the last line of your subproof. Then you can apply the conditional intro rule, pop out of the subproof with your conditional. So that is, a key thing to do. Follow those steps. If you want to practice the natural deduction stuff, a lot of the homework problems involve conditional intro. I practice, some of those. And then with the negation rules, don't forget you need the sentence psi and not psi under the assumption line in your subproof. So even if you're going to do negation intro, let's say you had some stuff going on, and then you tabbed in for a subproof starting with Q, and you assumed this :AS, you assumed it for negation intro, and imagine you're happily going along, and you get not Q from some stuff. Now, there's a strong temptation to say, oh, I have Q and I have not Q, so I can pop out immediately from the negation intro. You have to follow the syntactic form. You need both Q and not Q to be within the subproof under it, so you're going to have to repeat this. So if this was some line S, you have to cite a : cite S, and then write rule R to get the Q and not Q under it. They can be, the Q and not Q can be in any order. It turns out Carnap's fussy that if they're separated by subproof, it doesn't recognize that form, but I, a human, recognize it, so I would not take points off for that. But Carnap gets finicky about it. But I will take at least a point off if you don't reiterate this Q. So remember to do that. And then you can pop out your subproof and you can introduce the negation not Q, and you cite the whole thing. So starting on line S, -N, and the rule negation intro. That would be our form. Questions about this? Cool. All right, so that's what I just said about Carnap. Okay, and I think, all right, so that's the end. So yeah, and on our little, on our little practice stuff, you have all the problems are in the checking mode. So I'm trying to think which ones are good to practice. I feel like, yeah, 6.4, that's a good example. The conditional intro, these are good examples. So like 6.5, that's a good one. And the disjunction, yeah, so know how to do disjunction elimination, so 6.7, that's a good one to work through. And then you definitely want to know how to do negation intro and or negation elimination. So I would say, yeah, 6.10. 6.10 is a good one for practicing that. The 6.10 illustrates how often you can, have nested subproofs. So for instance, if you had a problem that was like the conclusion's a conditional, then you think your initial subproof is going to be for a conditional intro. But then, within that subproof, you might have to do one of the negation rules. You would then tab in again, and you'd be doing another subproof. You'd get, the thing you wanted from the negation rule, and then that might be, close to what you want to conclude your initial conditional intro rule. So you want to, be comfortable with nested subproofs. But again, none of these are going to be super long, so nothing super insane. If you want to do an insane one, you could do 6.14, which has 3 proofs, 3 subproofs. But yeah, there won't be anything like this on the test. So yeah, that's basically everything. You guys should be in great shape. I wouldn't stress. If you know what we talked about today, I think you should be told. And I have office hours now until like 12:30 or so. Cool. And again, if you don't get an email from me with these slides, send me an email because that means I screwed up somehow. So I will email you the slides. And remember to fully, completely accept yourselves, or else the midterm will be unhappy with you. Rationality to the accuracy. And so if you did think that a large part of the meaning of life was to be a rational nation, and you would be aiming for accuracy, being accurate about which arguments are valid, that falls under the scope of accuracy. All right, so here's our problem. We can handle connectives, but we can't really handle these quantifiers that are existent for all. And so whenever we encounter sentences that we couldn't break them down further with these connectives. We just ended up giving them their own, sentence letter. So something like everyone is a hero also just has to get its own sentence letter. Same if no one's a hero, all heroes wear capes. And so there's, tons of logical structure in these sentences that central logic just, does not respect. So our goal with quantifier logic is to introduce basically additional connectives. You can think about the quantifiers that we'll talk about as just being another kind of connective. And we're going to take SL and we're just going to enrich it. So we're still going to have everything that we had in SL, everything we know and love or hate, and we'll just have more. And then, we'll have precise truth conditions for this stuff. We won't really have something like truth tables. And that's why when we do 2 weeks from now, natural deduction for predicate logic, that'll be really powerful because that will be our easiest way of checking whether an argument is valid. Whereas, sentential logic, we have truth tables, we can do that. We won't really have something like that. We could do trees in quantifier logic, but we're not for the sake of time. But I guess if you really want to learn trees for quantifier logic, you could read it in the book. We're not going to do that stuff. We're just going to go straight to natural deduction for quantifiers, because that's what our metalogic proofs are about. And it's the more interesting metalogic proofs with the natural deduction systems. So yeah, we're going to augment our natural deduction, SND to something QND. And we're getting a lot of power. We're really only adding, technically, we're really only adding one symbol, because you can define the other quantifier in terms of, a given quantifier. So we're just adding basically one connector to central logic, and we get all this additional expressive power. So we have Greta is a hero, and then second premise, Greta does not wear a cape. And we can conclude not all heroes wear capes. Again, this seems to be a valid argument form, and so we would like to respect its validity within our formal language. And so we have to somehow connect, the Greta here in premise 1 and premise 2, whereas again, in sentential logic, this would just be some sentence G. This would be something like, not C, but not C, it wouldn't reference the Greta. So we want something like a name. We want names for things. And then we also, want to connect hero up here with the hero down here. And so we want something like properties. Being a hero is a property, so we want to have some vocabulary that lets us talk about properties as well. And then we're still going to have our connectives from before. And so basically for the names, we'll have something like constants. And then for the properties, we'll have something called predicates. And so this is additional stuff we're throwing in on top of the quantifiers. So we'll start with names, because this is probably the most intuitive thing to understand. We name things all the time, right? That's what we're naming agents. We're just going around pointing and naming things. So we're specifically focused on names that refer to a single specific thing. So whenever there is a name of something, it will always reference, possibly in some hypothetical scenario, some specific thing. So we couldn't have a name like chalk. Chalk wouldn't be a name because it wouldn't be clear which of these we're referring to. We could say something like, let's talk about all the chalk sticks in this bin, and I'll call this one Bob. And then this would be Bob. And then we could talk meaningfully about Bob and ascribe various properties of Bob, namely, Bob is shorter than, what's another name for somebody not in this class? Anybody got a funny name? Charlie? Oh, let's do Chad, right? Everybody makes fun of Chad. There's no Chads in this class. So we would say Bob is shorter than Chad. And this is something that we can now meaningfully say. And that's basically what we're doing. The homework problems are just often hypothetical scenarios with names. Although I think one of them actually is based on some solar system stuff. And so that's names of real things, a bonus. But it doesn't have to be names of real things. You could imagine, specific things and you're naming those specific things. So something like hero, this is a property, or rock, being a rock, also a property. Those are not names, they're not constants. And the book calls these things singular terms. So if you really wanted to write singular terms, you could write that, but names, constants seems easier to say. So yeah, specific object, and then later on, we will focus on expressions like these, which are called definite descriptions. So I can say meaningfully to you guys, the President of the United States is sometimes made fun of by people calling him Brandon. And this is a meaningful expression because when I said the President of the USA, I'm referring to Joe Biden. Now, Joe Biden is a name in this initial sense that, refers to a specific thing. This also refers to in a context, this refers to a specific single thing. And we'll basically use our quantifier logic, I think 3 weeks from now, week 11, and we'll talk about definite descriptions. Although it turns out, as I probably mentioned, the theory we'll give, which is from the early 1900s, has been supplanted by the linguists. The linguists have supplanted a lot of the things that we're doing in quantifier logic. So today we'll talk a bit about pronouns, I think, and it's very controversial how to treat pronouns. And we'll be doing classical semantics, and there's a whole other research program in linguistics that, I guess, it makes things a lot richer and gets at what we're really doing with our language. So we're not, again, it's like in this class we're giving a model of a language, it's a formal language, it's not necessarily our actual natural language. Linguists are often trying to get at what we're actually doing with our language, whereas here in Logic Land, we're happy often with an idealized theory. We say this is a fruitful idealization that gets at some dominant features of the way that agents like us talk, and that apply to other formal artificial languages, then that's great. And so it's not as though what we're doing is in conflict with the linguists. We just have different aims, we might say. And that's really, I think, a lot of life, when you encounter people and they're doing something and you think to yourself, why the hell is anybody working on that? I don't know if you guys have ever had this experience. You meet somebody and you find out what they're researching, and in the moment you have to be like, oh, that's really cool. But in the back of your mind, you're like, why the hell is anybody doing this? Often the answer is, they just have different aims than you. And you can criticize those aims, but often what they're doing makes perfect sense, relative to those aims. So, many of you, if you found out what my research is about, you might be like, what the hell is going on? And if I said to you, hey, my aim is to feel less troubled about a certain kind of, expression or mode of thought, you might say, all right, well, I feel bad for you, you're troubled like that, but I guess this is what it takes, So, all right, so, this is a key thing, very important thing, notationally, super important. We will always symbolize the names with lowercase letters from the letter A running to the letter V. And this is super important for Carnap. If in Carnap you try to input a capital letter for what's supposed to be a name, it's not going to accept it. So it's not going to work. So remember our our sentences, well-formed formula of SL are capital letters. And names are lowercase. And so you might, wonder, well, what are we going to do with the remaining letters of our 26-letter alphabet system? And so W, X, Y, and Z, they're going to be variables. And that's very important. W, X, Y, and Z are variables. Any questions so far? Cool. All right. This is my little name. What is this a joke on? MIT 2022. Really though, there's some other place where a date appears in this thing, and I realized in LaTeX you can input a command \year, and it updates the date, and it occurred to me in kind of a depressing way. I was like, oh shit, next time I do logic, this is going to auto-update, this year. And you're like, part of that's a little creepy, right? You're like, I don't know how many times I'm going to do this in my life, right? What if I'm like, year like 2050 and it's still the same, It's a little weird, right? So we try not to think about that. All right, so now we can go to predicates, and predicates are just names of properties. And properties, we really mean a whole bunch of things. So we mean properties that don't involve any relations to something like this piece of chalk is white. And we also mean things that involve relations, such as, let's call the chalk, this piece of chalk, I guess Haggy, because it's Haggeromo. So Haggy is between Bob and Chad. And so betweenness is, in an extended sense, a property. So you might naturally call it like a relation. Betweenness is a triadic property. It's a property that takes in 3 names. It says Y is between X and Z. Here I said Haggy is between Bob and Chad. So all of these things, like predicates that take n many names or variables, we're just going to call them predicates. Even though I think, most intuitively, you think of a predicate as a name for a property, you think of a property as like a monadic thing. Well, we're using property in a pretty broad sense. So Greta's the hero. The relevant predicate here is blank is the hero. So the property of being hero, and it's really this like schema. It says, I give you a blank space where you can put anything. You can put in any name, you can put in any variable. So this little x here is a variable. We're basically saying something, some x is a hero. If we say Greta admires Autumn, now this is a 2-place property. It involves 2 people, somebody who's admiring somebody else, and so it has 2 blanks. So blank x admires blank y, so this is the relation of x admiring y. So in our quantifier logic system, we again symbolize the predicates using uppercase letters. So initially you think, oh, isn't this going to lead to some conflict with our capital letters in SL? And what's going to happen is we're going to have notation that contextually always distinguishes a sentence letter of SL from a predicate. So predicates will also be capital letters. But you're never going to see a predicate all on its own. A predicate will always be immediately followed by a lowercase letter, either by a name or variable. So in use, we had some predicates such as H, where the hero, it's always going to be something like H followed by a name or a variable. So if we call Greta little g, then we would write HG. So, or if we were just talking about a variable, it would be something like HX. Whereas in contrast, when you have the capital letters of SL, you could have H, but there won't be any lowercase letter to the right of H. There would be, at most, a parenthesis or connective. So it'd be something like H and, dot. And so this H would be a sentence of SL, whereas this H is clearly a predicate because it's followed by a lowercase letter. So that's how we'll keep this straight. And so here, if you have 2 things coming after a predicate, that's telling you, okay, this is a 2-place predicate. This is, 2-area relation. Any questions about this? Cool. So for basically every problem where you're translating something, the problem will start with a symbolization key. And this is just like in sentential logic where, especially in the Carnap system, we gave you guys, a head start and said, hey, these are the atomic sentences to focus on. We'll tell you what the predicates are, what capital letters to use for the predicates, and what the names are, the names in your domain of discourse. So we'll give you some concrete lowercase letters for the proper names, and for the predicates, we'll tell you the uppercase letter to use, and also is a 1-place predicate, a 2-place, a 3-place, etc., based on how many variables it comes along with. So we might say, let lowercase a be Autumn, let lowercase g be Greta, and let h be the property of being hero. So we'll say hx, blank x is a hero. Let v be the property of being a villain. Let I be the property of inspiring somebody. We're feeling very inspired today, we might say, as we learn about quantifier logic. I don't know about you. Definitely, getting some great inspiration from this. All right, cx is where's the cape, And WXY, so this is a relation, this is the two-place predicate, this is the relation of blank welcoming some other thing. So X welcome Y, WXY. Oh, we have another one, AXY. X admires Y. And then this, I think this is our last one, capital Y, X lowercase y, X is younger than Y. So again, super important that the predicate's a capital Y and this variable is a lowercase y. You mix that up, Carnap is going to be super confused. You've got to keep that straight. Cool. So then there's always a domain, and the domain is just everything that's not a predicate that we're talking about. So it's all the concrete specific things that we are ascribing properties to in the particular context we're working in. And so you might take the domain to be all the people alive in 2022. This is where this 2022 is going to update every year I do this, you know, kind of creepy. So the book very grandly calls the domain the universe of discourse. I think this language is somewhat absurd, but I don't think I'm going to change this part of the book because we constantly use this abbreviation UD. I'd rather call this the domain of discourse and call it DD. But I don't know. I mean, I've already introduced UD. We're already going to be, you know, this is just going to be in the works. So we're going to stick this universe of discourse stuff, even though it sounds, you know, kind of ridiculous. Universe of discourse. Okay. I mean, these problems, you know, we talk about very small scenarios. Like these are not universes. These are, you know, very controlled things. All right. Any questions about this? So this is the symbolization key. So every translation problem will start with one of these. We'll start with a list of the things you're going to have names for, lowercase letters, and a list of the predicates that you'll use to schematize the sentence. And we'll tell you what you're quantifying over. Cool. So we'll start off with sentences where you don't use any quantifiers. And typically, I guess on a homework question or exam, we'll probably flag you, hey, this is a problem, don't use any quantifiers. And basically we do this to show that in principle, you don't have to use quantifiers if your domain of discourse is finite. If you can refer to everything in the domain, you don't need quantifiers. You really could get by just with predicates and properties, and you'll get pretty annoyed at doing this because some of the sentences will suck. They'll be pretty convoluted. And then when you're finally allowed to use quantifiers, you'll be like, yes, I love quantifiers. And so basically we do this kind of exercise to get you to appreciate quantifiers, because otherwise you might think, oh, I hate these things, you know, why couldn't I just stick with SL? It's like quantifiers are really your friend, compared to these cases where you're, you know, going to reference every single thing of the domain of discourse and write these long sentences. So if Greta Hero is just HG, Greta admires autumn is AGA, and so the order here is important because it might be the case that Greta admires autumn and autumn thinks that Greta is like a moron or something. And I think I screwed up autumn's name. There should be an N there at the end of autumn. There's always an N at the end of autumn, you might say. So it's very important that the G, the lowercase g, is before the A here. If we instead had capital A, lowercase a, and lowercase g, this would be autumn admires Greta, which would, you know, mean something completely different. And then we can combine these, you know, these are well-formed formula of quantifier logic. We can combine them using actives. So we could say Greta and autumn heroes, capital H, lowercase g, ampersand, capital H, lowercase a. If autumn admires Greta, then autumn is a hero, capital A, AG, and then our horseshoe, capital H, lowercase a. So basically, we're not running away from sentential logic, we're just enriching sentential logic. So everything that you guys have learned up until now will be, you know, totally useful. This honestly was the rationale for doing a midterm in this class, because historically it seemed to me this class didn't have a midterm, but it's like everything we do in the second part depends on, you know, having down the sentential logic. So I sometimes in classes, you know, I wouldn't really study anything until there was a test, right? And then I'd learn everything in like, you know, 2 days or something. And so my thought was like, all right, well, if there's anybody in this class in that situation, great. We'll learn sentential logic in 2 days, and then we'll be able to proceed for quantifier logic. All right, so, so pronouns. So this is where the linguists do things much richer than what we're doing. But it's okay, we'll get by with this. So often in sentences, we don't keep writing people's names, we use pronouns, and the pronoun refers to an antecedent. And so when you're schematizing something, you have to figure out what is the proper name that any given pronoun is referring to. And then that pronoun will be given the same lowercase letter as the name, that is its antecedent. So in this sentence, as Autumn is a hero, Greta admires her, her is not referring to Greta, her is referring to Autumn. And so in the consequent, we have capital A, lowercase g, lowercase a. Greta doesn't admire herself, but Greta should admire herself, we should all admire ourselves. So this would be, it's not the case that Greta admires Greta. Greta and Autumn welcomed each other. So there's two things going on here. Greta is welcoming Autumn, and also Autumn is welcoming Greta. So it's two independent thoughts, and we can join them with a ampersand. So this is a good example of a sentence where the logical structure is not manifest in the sentence. You really have to think about the meaning of the sentence. Always, our meanings for us are always truth conditions, and so we're basically asking, what does it take for it to be true that Greta and Autumn welcome each other? Well, it has to be the case that Greta welcomed Autumn, and it also has to be the case that Autumn welcomed Greta. And we don't have, you could, if you wanted to, introduce some other predicate that is the property of welcoming each other. You could do that. But if you have a symbolization key that doesn't have that property of welcoming each other, you just have welcomed, which is a directed thing, like I can welcome you without you welcoming me. Then you have to schematize it like this. So how you schematize is completely constrained by your symbolization key. It's constrained by the properties that you have chosen or been ordained to use. Okay, so modifiers. So this is where things can get a bit tricky because some of these modifying adjectives end up basically requiring their own predicates, as we'll see. And you have to have a sense of when it is not the case. Now, in a way, I guess, since you guys will always be given a symbolization key, you won't have to fret too much about this sort of thing because the key will dictate what to do. Unless we were going to try to set up a question and trick you, which I don't think I will because I care about you guys, and I'm not trying to trick anybody. At least not now. We'll see how I feel in a couple weeks, upon doing more grading and becoming even more disgruntled. No, I'm not disgruntled. If I ever seem disgruntled, let me know. I'd be kind of curious if I did. Some people you meet them, you're like, this person's clearly disgruntled. I never want to be somebody like that. I feel like it's just a bad vibe. All right, so Autumn is an inspiring hero, and so there's two things going on here. But we'll see. There's a way. I'm not even sure if this is the best way to do it. But here's one way you can do it. You can say, well, Autumn inspires, and she's also a hero. So we have a predicate for inspiring and a predicate for being a hero, and we would combine these two independent thoughts. But it's like you might. We'll come back to some examples later. You might think to be an inspiring hero doesn't necessarily mean that you're inspiring. Maybe you're only inspiring as being a hero. And if that were the case, then you wouldn't want a separate property for inspires and a separate property for heroes. You just want a single property of being inspiring as a hero. And some modifier phrases seem to require that kind of move. So here, Greta's a hero who doesn't wear a cape. This one, clearly, two different properties going on. Greta's a hero, and it's not the case that Greta wears a cape. So remember, wearing a cape is capital C, so not wearing a cape is tilde, capital C, lowercase g. Any questions so far? All right, so here's a good example of where you would go wrong. So if you tried to treat Greta as an international hero, the same way we treated Autumn as an inspiring hero, where we have inspires and hero, if here you thought, we'll have a predicate for international and a predicate for hero, then it's just not going to go well. we're not saying Greta is international and she's a hero. Superman is an international hero, and Superman is not international relative to the world. Like, Superman is not from any nation on the world. He's an international hero in the sense of being known internationally. But, Superman's not from Earth, right? So he can't be international in the sense that we normally mean international. And normally we mean international, meaning somebody who's from a nation different from the home country of context. That's what international normally means. So we have to make international heroes own predicate rather than splitting it up into two predicates. So here's another example. The Piltdown Man is a fake fossil. Now, the Piltdown Man, you might wonder, why the hell are we talking about the Piltdown Man? It's kind of an interesting example. So people can really be sociopaths, and as some of you have probably unfortunately encountered. And there was this early 20th century, I guess late 19th century, archaeologist person who wanted to become famous, and so he fabricated a fossil skull that he argued was the missing link. People were obsessed about, the evolutionary origins of humans coming from the great apes, and this guy had an elaborate hoax where he convinced people for decades that he had found the missing link, and it messed up a bunch of evolutionary biology research because they believed that this was, part of our human, lineage, and then that constrained their further theorizing. It conflicted with a bunch of other data they got, and so people were very confused for decades until it was definitively exposed as a hoax. And so it's just kind of, it's a scary thing in the world, but if you're in a position of quasi-power and you've established trust with people, you can really abuse that trust in terrible ways. This guy completely abused the trust that he had with his colleagues, and they believed him. So don't abuse people's trust. That's the moral of the Piltdown Man. We can learn a lot from fake fossils, it turns out. But so we have this property, fake fossil, and so you just can't paraphrase this as the Piltdown Man is fake and a fossil. It's not a fossil. The whole point is it's a fake fossil, so you can't say that it's a fossil. So fake is what's called a privative adjective. Other examples are pretend, fictitious. They're basically saying, I'm not the property that I'm modifying. And so you can't schematize things like this, Fake news is not news. Very important. Well, I don't really know what, fake news is something, but it's so it's not news. What is it? What is fake news? Is it just people screaming into the void? I don't know what else to call fake news. Fake news is not news. So what should we call it? Is it like a blog post? All right, so is this clear about the modifiers? Again, I don't think you guys will have to worry about this too much. The only way you'd have to worry about it is if there was a tricky symbolization key where we had some properties fake, we had fossil, and we also had fake fossil. But then you would see, it's like you'd be given, oh, okay, we have this other property for fake fossil. So I feel like you could only be tripped up if you were asked to make a symbolization key on your own. And if I stay lazy and I want Carnap to do the great thing, but I don't know why I have any incentive to ask you to do that. But maybe we'll do a short answer question at some point, and then this distinction would really matter. All right, so Autumn and Greta are inspired heroes. So again, there's really a lot going on in this. There's 4 separate units of thought, and you guys would have to pick out, these 4 separate units. You'd be given this sentence, and you would have to say, okay, Autumn is inspiring. Autumn is a hero. Greta is inspiring. Greta's a hero, and that's all contained in this sentence. Greta admires Autumn, but not herself. So yeah, I'll give you guys a moment to think about this. Remember, admires is capital A. I guess I'll make the mistake of passing back midterms for Daniel and Manny, and then they'll be completely distracted for the remaining of the class, right? Oh yeah, another Daniel. Henson. Okay. Make sure I do give stuff back in middle class, because then it's like we just kind of focus on it, right? Does anybody need scrap paper for any examples you want to break down? People need a scrap. You can always write in your hand, right? Alright, so Greta admires Autumn, but not herself, so we'll have capital A, lowercase g, lowercase a, ampersand. It's not the case that Greta admires herself, so it's not the case capital A, lowercase g. That's my guess. Cool. So, aga, and not arg. Sorry, schematization. Here's another one. Greta inspires only if all of us. So here's our only if. So again, you're not going to escape this stuff. You didn't like only if, you're stuck with only if. We're going to continue doing problems with only if. And these, kind of just. So we remember only if does not change the order of the antecedent consonant here. So Greta inspires will be our antecedent, IG, and our consequent will be Autumn inspires, capital I, lowercase a. That's this guy. Greta and Autumn welcome each other. This one we've talked about. We have two instances of people welcoming each other. We got Wugga and Wag. Greta is older than Autumn, so remember, we introduced a property younger than, so we had y, x, lowercase y, or x is younger than y, and imagine this is the only property you've been given that has anything to do with age, and now you have to schematize Greta is older than Autumn. What do we do? We can think logically, here. So note, you wouldn't want to negate the younger than relation, because if it's not the case that Autumn is younger than Greta, then, well, they still can be the same age, right? So when we say that Greta is older than Autumn, this has the same truth conditions as Autumn being younger than Greta. And so we're going to use our younger than thing, and we're just going to say Autumn is younger than Greta. So Autumn, younger than Greta, this just means the same thing as saying Greta's older than Autumn. And this is very different than if you had written something like, it's not the case that Greta is younger than Autumn. It's not the case that Greta is younger than Autumn, leaves open the possibility that they're the same age. This is something that totally will happen on the problem set at various points, where you'll be given a sentence that seems to have a property you don't have a predicate for. It will just be related in this, I guess, anti-symmetric fashion to some other property. Okay, one of Greta and Autumn welcome the other. Think about this one. We clearly don't want to say this, because this is they both welcome each other. We want to say something else. Okay, so we're going to have a disjunction, because this will be true. This will be true provided that at least one of them welcome the other. Now, if we wanted to say exactly one of Greta and Autumn welcome the other, then we have this disjunction thing, and we also negate them both welcoming each other. Okay, so that's here too. So this is at least one of them welcoming each other. We have the disjunction, and then to say exactly one, we have the disjunction, and we say it's not the case that they both welcome each other. So, but if you might think that the one of Greta and Autumn welcoming the other is ambiguous. If this was a homework question or exam, it would explicitly say, at least one or exactly one to avoid that ambiguity. Because these things clearly mean, very different things. Any questions about this? Cool. All right, so we now get to become existential. And we're all, everybody in high school is an existentialist, right? I was an existentialist in high school. Is anybody else an existentialist in high school? A human chooses what it is to be human. There's this beautiful analogy with the paper cutter, where the paper cutter is designed, its functional role is determined by the toolmaker, and the toolmaker decides this is a device that will cut paper. Now humans, allegedly, are not like that. Humans are radically free. Humans, every day, in every action we do, we get to choose what it is to be human. That's existentialism. And man, doesn't that sound really cool? You get to wake up, you can be like, today, I get to play a role in choosing what it is to be human. That's kind of cool. So I was an existentialist for a while, and then at some point, I stopped believing that we had free will. And you can't really be an existentialist if you don't believe in free will. I realized the whole existentialist program is founded on this radical commitment to radical free will. You take that away, I don't know if I'm choosing anything about what it is to be a human. Maybe being a human is choosing what it is to be me. So I stopped being an existentialist. There's still some cool things in it though. Like Camus' writing on the absurd, like the myth of Sisyphus, that and The Stranger, that's some cool stuff, grappling with absurdity. I still think about that on occasion. But that connects more, you might think, with nihilism, with a worry that there's no, ultimate meaning to life. So, if any of you ever actually want to talk about the meaning of life with me, let me know. There's an argument I came up, we're totally on a tangent. This is kind of cool. I think we're going to get through everything, at least by Wednesday, so I'm kind of like, we're chilling. So, I was getting an ice cream cone. And that's what I do when I'm like, really like, yep, we're living the dream here. So I went to Christina's, I got an ice cream cone. I'm walking around, I was listening to a book by a philosopher, and it was talking about, the meaning of life and arguing against there being no meaning of life. And this is something I think about too often. And I had an idea that came into my head, and I was like, shit, this is actually more compelling than what I normally say about the meaning of life. So, obviously I don't know what the meaning of life is. And so we're in a context where we're having doubts about whether there even is a positive answer to the meaning of life. And when you're in a context like that, you get a little depressed, you're like, what if there really is no, positive meaning of life? But then it occurred to me, I'm a fallibilist about almost everything. I think I could be wrong about most things. Now imagine I thought, ultimately I think, the universe is, created somehow. There's no fundamental value facts anywhere, so there's no positive answer to the meaning of life. Well, I could be wrong about that. I really, I'm humble. I think I could be wrong. So then I think, well, what if I am wrong? Then there is, unbeknownst to me, a genuine positive answer to the meaning of life. And there's some chance that in my lifetime, I might find out what it is. Wouldn't I then want to keep going on, in the hopes that I might find out the meaning of life? So we're led to, at least the final conclusion that part of the meaning of life might just be to keep searching for an answer to the meaning of life. And you'll have that until you find an answer. Now, I don't know if that is an answer, but it's kind of like a sort of a, it's really kind of like Pascal's wager, right? So Pascal's wager is, well, if there is a God, you don't believe in it, it's going to damn you for eternity. So you might as well try to believe in it. Here we're saying something like, well, there could be a positive answer to the meaning of life. And wouldn't it be a bummer if you were just like, peace, I don't think there's meaning of life, so peace out. That'd be, because what if you would have found out what it is? There's some chance that you might find out what the meaning of life is. Wouldn't you want to know? Wouldn't you want to think, if I found out what the meaning of life is, I'd be screaming through the streets. I'd be like, I discovered it. I have the meaning of life. You want to tell everybody. So that's at least one, I think, positive reason, to stay optimistic. Well, there could be an answer. All right, so that is some notion of existential that's very different from the notion of existential that we'll be talking about. Maybe bring it back there. All right, so when we say existential, we really just mean something or other, not very grandiose. So existential quantifier, which will be our funny symbol, it's a backwards E. A backwards E. We could have, I guess, we could have had a symbol like this. This is maybe how I felt when I stopped being an existentialist. I was like, it's all gone shit up. That's it. we're not going to use that one. This is backwards, the backwards E. So someone wears a cape. There is a hero. Something inspires. These are all instances of an existential quantifier. So these expressions, these something, someone, there is, they often go where a name and pronoun is placed. And so they're kind of functioning like a variable. They're functioning like, hey, there's some arbitrary thing. We don't know what its name is, but we can talk about it. Or, I don't know, when I say one of these pieces of chalk inspires, I don't know which one. It could be Bob, or maybe Chad is the inspirational. For those of you who came in late, we named the chalk. This is Chad. Maybe Chad is inspirational, but I just say something inspires. And if my domain of discourse is the chalk, then I'm basically saying there is a piece of chalk, at least one, that inspires. So here, something, it doesn't pick out a unique object, a unique piece of chalk, whereas, Bob picks out this piece of chalk. Okay, so we'll talk about one way that you might have thought you could go about doing this that really doesn't work well. So you might think, well, why not just introduce a special term, still a name, just SG or a something. Why not do that? So then we wouldn't be able to distinguish between someone is a hero and wears a cape versus someone is a hero and someone wears a cape. So we'd be symbolizing both of these as the something is a hero and the something wears a cape, whereas this one is saying there is at least one thing that both is a hero and wears a cape. Whereas this one leaves open the possibility that a different thing is a hero and a different thing wears a cape. This one's still true if something is both a hero and a cape, but this one doesn't require that. The second one would be true even if, for instance, Bob is our hero and Chad is wearing a cape for Chuck. Then the second one would be true, but the first one would not be true because it wouldn't be the case that at least one piece of our chalk is both a hero and a cape. So instead, we're going to stick with properties and we're going to introduce this notation, this backwards E symbol, for expressing that we can instantiate a property. All right, so before we get to our little symbol, we basically talk about properties now applying to the variables. So HX is this property of being a hero, IX is being inspiring, and we can get these, I guess this would be a one-place predicate. So we had this thing admiring, which with variables was AXY. So this was variable X admires variable Y. And this is a two-place predicate. We can get a one-place predicate by replacing one of these variables with a constant. So here we have a one-place predicate of X admires Greta. Greta should have capital G for the name. So admiring Greta, this is a one-place predicate that we derive from a two-place predicate. So wax, W lowercase a lowercase x, would be is welcomed by Autumn, i.e. Autumn is welcoming that thing. All right, so is a hero versus a cape. So each of these things has a single variable x, and we can quantify over this single variable x. This will be some notation we introduce, the notion of quantifying over variable. So this is our symbol, backwards E. In Carnap, what you'll end up doing to write this thing is just E. So in Carnap, you'll type in a regular capital E. Now again, you think, isn't this going to screw up everything we're doing with our predicates? Because over in predicate land, you could use capital E as a predicate, and you could have things like, EA, EB. So how is this not going to come in conflict? Our notation will prevent things from coming in conflict. And so we'll be good. We'll see why that is the case. So if we have this, property of being a hero and wearing a cape, to say something or someone has that property, we just say, there is some variable x. such that x is a hero and x wears a cape. So we're just quantifying over the variable x. And the key things in our notation are that the quantifier always comes with a variable. So this, there exists something, always has a variable that it binds, and it is always placed within a single pair of parentheses. So every time you write a quantifier, you have to write an open paren, the quantifier, the variable it binds, and a close paren. You have to do this every time. And so in Carnap, this would be open paren, you would type a regular capital E and a Y close paren, and the parentheses are telling Carnap, this thing is not a property. We're not saying Y has the property being E. We're saying this is a quantifier expression, and we're going to bind something to the right. So that's how our notation keeps track of the difference between a quantifier and a property. So the super important thing we'll try to emphasize a lot is you just have to remember these parentheses. There's tons of notations that you could use for quantifier logic, and we're not using the one that is most common in computer science, and so if you've seen that notation, I'm sorry, because this might be more confusing for you. I like this notation because, to my mind, it gives you a relative minimum of parentheses. And in the computer science notation, you end up with a shit ton of parentheses. And when we do natural deduction and you're writing a lot of these expressions in the Carnap, it's just really annoying if you have all those parentheses. So this notation, basically, you only need the parentheses around the quantifiers, whereas other notation, you need parentheses around the names and variables of you're acting on it with a property, you're doing the property as a function, and then blah, blah, blah. There's just so many parentheses. So and that's annoying. So that's why we're doing it this way. Okay, so yeah. Key thing, always remember, you have to put the quantifier and the variable it binds within the parentheses, or Carnap will be set, and then you will be set. Any questions about this? Cool. All right, so with the quantifiers, we can track this difference between at least somebody is a hero and wears a cape versus at least somebody is a hero and at least somebody wears a cape. So in the first case, what this is saying is, in order to be true, there has to be at least one thing that's both a hero and wears a cape. Whereas in the second one, you could have one person be a hero and one person wear a cape, and they could be different people, but not necessarily. So the key thing is, this second one is not saying that the two X's are necessarily different. It leaves open the possibility that they're the same. So you can think about these instances of the existential quantifier that are separated by other connectives. These are just independent thoughts, and this X is just a dummy variable. So if you've seen summation notation in physics, the notion of a dummy variable is exactly the same here. It's like you can think about these bound variables and their instances, they come in pairs where this X is in the scope of this existential, and we could swap out any variable we want for this X and this X as long as we make the replacement. So we can make this a W, and this is W, this is Z, and this is Z. That's what we've done here. So here we took this second bound variable, X, and we made it a Y. And as long as I replace the X here for Y and X here for Y, we're all good. It means the same thing, just a dummy variable. Any questions about this? We'll hopefully be more clear with more examples. All right, and so we'll never write anything like this. We'll never have two instances of a quantifier next to each other with the same variable. This will not be a legal sentence. This is not a well-formed formula of quantifier logic. So if you wanted to have two quantifiers immediately next to each other, which we often will have with the more complex sentences, you have to introduce a new bound variable for every sequential quantifier. So you could write there's an X and there's a Y such that X is a hero and Y wears a cape. That would be a legal expression. All right, so back to our domain of discourse, our UD, our universe of discourse. So the quantifier talks about everything in the universe of discourse. So what we're quantifying over is everything in the universe of discourse. So for instance, if our universe of discourse is the people who are alive in 2022, then when I say there is an X such that X is a hero and X wears a cape, this X could be any person alive in 2022. If instead my domain of discourse is the chalk in this box, then the sentence means something very different. It means there's at least one piece of chalk that is a hero and wears a cape. Clearly that is a very different meaning than talking about people alive. So the domain of discourse makes a huge difference as to what any one of these existentially quantified sentences means, because what it means depends on what we're quantifying over. What we're quantifying over just is the domain of discourse. And you have to be told that, or you have to choose what you want the domain of discourse to be. Okay. So the truth condition for an existential is just the existentially quantified thing is true if and only if there's at least one object in the domain. It could be multiple. It would be true if there are multiple. There just has to be at least one that has the property expressed by this ... x ... thing. Okay. So if we have, there's at least one person who welcomes Greta, then this is true if somebody welcomed Greta, perhaps Autumn. Now, if the domain only included Greta, then it would be true only if Greta welcomed herself. And maybe you think it's not possible to welcome yourself. I think I welcome myself all the time. On Friday, there was a Halloween party, and there was a lot of leftover chocolate fondue, and I welcomed myself to that chocolate fondue quite a bit over the weekend while I was grading midterms. There were little apple slices that were on sticks, and you could take an apple slice and you could stick it in the fondue. You could put little sprinkles on it and peanuts. And so when I grade, for reasons of fairness, you have to maintain a consistent attitude. And the only way to do that is with chocolate, I think. So, I don't want anybody to get grumpy me while we're grading, so we're just eating continuously. Hopefully there's no chocolate stains in your guys' exams. That would be gross. I think it was clean. But, the other thing too about the exams, in case you think about this sort of thing, the problems were graded in batches. And so I did all the ones, all the twos, all the threes, all the fours. And I tried to mix up your exams so that you didn't always get me at the start of a problem or the end of a problem. So you got various time slices of me. And hopefully that means if you had a relatively disgruntled me on problem 2, you didn't have as disgruntled me on problem 4. So that's a hope that we homogenize that way. It's just, I don't know if you guys have seen these studies. It's like disturbing stuff about judges granting parole, and the rate of parole grants goes way up right after lunch. And so if you just have the bad luck of trying to get a parole request, and the judge looks at your application as like the last one before lunch, you have just the lowest chance of getting the parole. And you would have had a higher chance if the judge had looked at yours right after lunch. And you think, that's just kind of messed up, right? That shouldn't be that way. That's why people are using various black box machine learning algorithms to try to change these parole systems. There's a lot of problems there. Well, it's not explainable, and people get decisions seem arbitrary. What's the Joe Biden has a saying that don't compare me to the Almighty, compare me to the alternative. And that's the alternative is you're at the fate of, the mercy of whether the judge is hungry. That seems worse, I think, than an algorithm. But people have different opinions about this sort of thing, right? This is a controversial topic in philosophy of law and technology ethics right now. Okay. So, something and someone, they are like singular terms, so that they can go typically wherever a name goes. But whenever you see one of these, you're thinking to yourself, okay, I'm going to introduce a variable, and I'm going to introduce an existential quantifier that's going to bind that variable. That's what you're thinking to yourself. But so some on its own, it doesn't have heroes. It is a determiner. It needs some complement. So some is a little different than something and someone. It's kind of like something and someone, they come with this complement already, whereas just some, you need something after some, like hero, or admirer, in order for this to be meaningful. So whenever you have some plus this complement, then it's just like someone. So some hero wears a cape is just like someone wears a cape who was a hero. But we wouldn't ever say some wears a cape. Some wears a cape is not a felicitous assertion. So that's what this complement is functioning. It's functioning to turn some into something that can function like a singular term, although we're also adding a property. So the general form is always some f is a g. We're often going to talk about f's and g's just like general properties. The property being f and the property being g. It's just when one is making slides and they lose the creative impulse, then they just resort to f's and g's. F's and g's. So some f is g. It's restricting the something quantifier to the g's. It's saying there's something that is an f that is also a g. And so you could, so again, the linguists are way fancier, and we probably need these fancy things if we were really going to model natural language. But again, our goal is not to give a facsimile of natural language. Our goal is to learn the things that have been taught in decades in the logic books. That's literally our goal, right? So we're not going to do this kind of quantifier restriction notations. For our purposes, we just don't need it. And so we'll save ourselves the hassle. So for us, it's enough to notice, okay, some f is g is true, just in case there's something that is both an f and a g. So we're just saying there's at least one thing x, such that x is an f and x is a g. And so we could also say some f's are g's, and that would mean the same thing. And also g some f or g something that f's. So any one of these forms would take this schematization. There is at least one thing x such that x is an f and x is a g. So basically, this case of restriction with the existential quantifier is very intuitive because it's involving ampersand, whereas when we get to the analogous quantifier restriction for the universal quantifier for all, it's not going to be as intuitive, and it'll be something that you really could get tripped up on. But this one, hopefully, just seems obvious in a way. That this is the way to do it. Some f is a g. There's at least one thing. It's both an f and a g. Okay. So I feel like maybe we'll do some more examples on Wednesday. I feel like in the remaining time, let's skip ahead to the universal, just so that we can at least introduce that today. Okay. So remember, that something really means at least one. That's something that often confuses people. Often we think something means exactly one, but don't. Just like you guys got used to or always meant inclusive or, get used to something always means at least one. Now everything is f is true if and only if every element in the domain is an f. So in quantifier logic, this is just going to be this new thing for all, which is an upside down a. So here, things have gone shit up, you might say, the universal. So we have, it is kind of interesting. We use upside down a, but we don't. Well, I guess we're just looking at where we want something like a mirror plane, I guess is what. In here, it's like with a, our mirror plane is this one. Because if instead, you took the mirror plane to be this way, well, you just have a back, because a has a symmetry down the middle. So, but you might think, why didn't we just put a sideways? Maybe that would look like a greater than sign. Okay, so everyone wears a cape. This is for every x that's in our domain, x wears a cape. And everyone, welcome to Greta for autumn. This is for all the x. Oh, and this is bad. I screwed up here. There should be parentheses around this for all x. So I need to add that back in. Very important that there's parentheses right there. So then we have either x welcomes Greta or x welcomes autumn. So we're basically saying of everybody in the domain, either they welcomed Greta or they welcomed autumn, possibly both. Again, because remember, this is an inclusive or. Yeah, I have a very complex code for all these quantifiers, such that in the preamble, if I want, I can toggle to any other notation, because I wasn't sure if I would stick with this notation in the future, and I didn't want to have to recode everything. So if I ever want to switch to computer science code, I can just change like 2 commands and then renders all the slides as computer science code, which is kind of cool. So the book is very similar in that regard. All right, determiners. So all, every, any. So these things often will be schematized using R for all. This is not always the case. We'll see, I guess on Wednesday, some cases where actually some of these you schematize, like any, sometimes get schematized as an existential. And that should be clear from context, although it is sometimes a bit confusing. So they take complements just like sum does. You know, so every hero, we wouldn't say every inspires. We have to say every blank something, inspires, where the blank is like a property. So every hero inspires, all heroes inspire, any hero inspires. So this is one that sometimes can be a bit tricky. So these are true in exactly the same cases. They're true whenever it's the case that every F is a G. So you need it to be the case that in our domain of discourse, this thing that we're looking at, which has everything in it we're quantifying over, you split off the F's, and when we say all the F's are G's, we're basically requiring, so let's imagine the F's were here, and to say all the F's are G's, we're requiring that all of the F's are within some possibly bigger thing that is the G's. So that's what this means, in terms of truth conditions. And now our goal is, okay, how do we symbolize this with our language? So yeah, we'll talk about any probably on Wednesday. So we got these 2 properties, F and G, whatever they are. How do we get every F as a G? This one is not as easy as there is something that is an F and a G. So we have some initial ideas. Only one of these is going to be right, so don't remember the false ones. So you might think this. Okay, for everything, it's an F and a G. This is not going to work, because this is saying everything in our domain of discourse is both an F and a G. Well, that's not necessarily true. There's, tons of stuff out here, outside our dotted line, that is not a G. And so, and also not an F. So that's not going to work. The or, everything is an F or a G. That's also not true. There the little red dot is on something that's neither an F nor a G. So this is how it goes. It is a conditional. And remember, whenever we see a conditional, we think, shit's going to be messed up. Because this is a material conditional, and it's counterintuitive, and has strange properties through conditionally. So things can become strange with our material conditional. But hopefully, you'll be able to work yourself into thinking this is fairly natural. So the way I think about it is we're saying, for everything X, if that X is an F, then it's a G. We're saying, if something's an F, then it's a G. I'm basically saying, hey, focus on the F's. Here's something, well, okay, if it's an F, then it has to be within the G's. And that's exactly what every F is a G means. It means everything that's an F, all these little dots in here, they're also G's. And that's the same as saying, if you give me an F, you've given me something that is within the G's. So ultimately, I think you'll find this pretty natural. But again, the surface structure of the sentence, every F is a G, doesn't say anything about conditionals in it. So you can't just go off of the surface structure. You just have to get used to schematizing whenever you see every F as a G, that you think to yourself, okay, we're going to have a universal quantifier, and we're going to have a conditional. So hopefully with practice, that will become natural. All right, so we've counterexampled these things. So this one's the good one. If X is F, X must also be a G. If X is not F, then it doesn't matter if it's G or not. That's a function of the material conditional. If you have something that's not an F, then the antecedent is false, and remember the material conditional is trivially true whenever the antecedent is false. So really, the interesting cases are cases where you have something that's an F, then you can infer, okay, it's a G. And if you had something that was an F that wasn't a G, then that would be the counterexample to saying every F is a G. So if you had, something that was, imagine that our little F region extended outside, and we had something that was an F but was not a G, that would be the counterexample to the statement. And so that would be the same as saying it's not the case that for all x, if something is an F, then it's a G. And this would be equivalent to saying there exists something that is an F and is not a G. So there exists something that's an F and not a G. And probably on Wednesday we'll talk about some De Morgan's laws for the quantifiers. Basically, there's a way to think about negating a universal and also negating existential, as the negation is going into the universal, it's flipping it to an existential, and then the negation is negating this whole expression. And you might recall the negation of a conditional will give you an antecedent, because what is this thing? This is not, it's not the case that F and not G. And so if we negate this thing, we have not F and not G, and so we just get F and not G. So this is a sense in which we don't really need to introduce a universal quantifier. We could get by just with the existential and be happy existentialists, but the universal is convenient because otherwise you have to write everything in existentials, and then often you have many negations running around that you might just want to avoid. So, but yeah, we'll probably do more examples of this kind of thing on Wednesday. This is something also that, just like with De Morgan's laws, you want to be fluent about it in your reasoning. You want to become fluent with negating quantified expressions, flipping the quantifier, and pushing the negation through. You just want to be able to do that, relatively quickly because it's a good conceptual resource. Okay. So yes, this is memorize this. If you end up not finding this natural, if this doesn't become natural, then yeah, you're just going to have to memorize this, because a lot of problems involve this, and it's super important to have this down pat. So if we have all F's or G's for everything, if it's an F, then it's a G. Same as every F is a G, and same as any F is a G. But again, watch out for any, because there are cases where any actually is symbolized as an existential, as we'll see. But any F is a G will, I think, always be symbolized this way. Okay. So let's do some examples of this. Every hero wears a cape. This is the same as all heroes wear capes, and so we're thinking, okay, every. So we're going to need a universal, and we have the complement hero. So we're going to go to the predicate hero, and we have this other predicate cape. And we're basically saying, of everything, if it's a hero, then it wears a cape. That's what we're saying. So again, you don't want to think that we're not saying that everything is a hero and wears a cape. We're saying everything is such that if it is a hero, then it wears a cape. So for all x, if it's a hero, then it wears a cape. Every hero who wears a cape, welcome Greta. So now we have an even more complex complement. Our complement is being a hero and wearing a cape. And so we're saying, of all these things, if it is a hero and it wears a cape, so if it's something such that both it is a hero and wears a cape, then, conditional, it welcomes Greta. So for all x, if it's a hero and it wears a cape, close this parenthesis, then that thing x welcomes Greta. And so this is our antecedent of our conditional, and this is the consequent. And it's important that you shouldn't close this parenthesis here, because if you close this parenthesis, then this x would just be floating free, and that x wouldn't be bound by the quantifier. But you need this x to be bound by this quantifier, so this initial open paren has to be closed at the end, not right after the CX. Questions about that? All right, so think about this one. Greta and Autumn admire anyone who wears the cape. I guess this is good theme for Halloween, right? In principle, somebody could have been wearing a cape today. I saw someone dressed as a pumpkin, so. I did think about wearing, because I was like this morning, I was like, oh shit, in principle, I could have worn a Halloween costume, right? And I was like, I don't have any Halloween costumes, but I do have a really hideous looking shirt. And I was like, what if I wear this really ugly shirt? And then people were like, why are you doing that? I could be like, hey, it's Halloween. I'm dressed as a moron. I might wear it at some point because it's just kind of ridiculous. It is a very bright salmon colored shirt. It kind of it hurts the eyes a bit. But if I had worn it, I could have been like, today I'm dressed as a salmon. I'm a fish. I did really like it during the midterm that I was able to say that the complication does not arise. And some people knew what that meant. I was like, this is just the most absurd thing, right? Like, in what kind of context is this, like a normal utterance? It was just, yeah, I thought that was really fun. All right, so we have this thing. We're saying for all x, if it's somebody who wears a cape, then Greta admires that x, and also Autumn admires the x. So here it's the consequent is the more complicated thing. And the anyone who wears a cape, this is the thing that's in, that we're saying is like the f. And so here we're saying, we're still saying every f is a g. We're still saying everything such that it wears a cape is a g, where g is being admired by Greta and Autumn. But notice how the order's flipped. So whereas here was the every was up front, just like our antecedent. Here, the every claim is at the end of the sentence, but it still is the antecedent. So you can't just rely on where the every claim appears in the sentence. You have to think about the meaning of the sentence. Okay. Autumn welcomed everyone who welcomed Greta. Think about this. Everyone who welcomed Greta, so this is our F, so we're saying everything that welcomed Greta. If you are something that welcomed Greta, then Autumn welcomed you. So we're saying for all x, if capital W, that x welcomed Greta, horseshoe, capital W for welcome, lowercase a, Autumn welcomed that thing. So for all x, if x is something that welcomed Greta, then Autumn welcomed x. So we're just, and the order here is very important that the x is the first term after the W here in the antecedent, and that the x is the last term after the W in the consequent. Very important for who is doing the welcoming, who is being welcomed. All heroes and villains welcome Greta, so this one is tricky. I think there is a question on the homework like this. Because what's tricky about it is there's an and here, you do not use an ampersand in this one, so that's going to mess you up. So you have to really think about what does this mean. We're saying that everything is such that if it's a hero, then it welcomes Greta, or if it's a villain, then it welcomes Greta. So it's really an or statement is in here. We're saying everything is such that if it's a hero or it's a villain, then it welcomes Greta. That's what it means to say all the heroes and the villains welcome Greta. So for all x, if x is a hero or if x is a villain, then it welcomes Greta. And I don't know if I wrote this on the thing, but yeah, you can think about this as well as for all x, if it's a hero, then it welcomes Greta, ampersand for all x, if it's a villain, then it welcomes Greta. And you could have written it. Oh, okay. Yeah. So this is another way to think about it. For all x, if it's a hero, then it welcomes Greta, and if it's a villain, then it welcomes Greta. So you could schematize it this way, and avoid that or, which you might find very tricky. And Carnap will take both because Carnap is a logic engine and doesn't make mistakes, assuming that there's no bugs and stuff. So if you find this way more natural, you could do this. And you could even close off this initial for all here with the parenthesis, have an ampersand, and have another for all, and do this one, and that would also work. So we'll end here today. We'll finish the rest of the stuff on Wednesday, and probably do practice problems on Carnap, and maybe some homework problems as well. So, thanks. You guys all got your returns back? I thought everyone would come to class today to get their midterms. Now it's like the rest of the day, whenever you hear every and some, you're just going to be thinking of quantifiers. And I was like 2 weeks late on this thing. And so I start to feel kind of guilty when I'm like 2 weeks late. They send you these reminder emails. And the paper was just so long. It was like 30 pages long. Everybody's always trying to do like way too much in a paper. They're trying to give their own like personal theory of like the nature of science and then apply it to quantum mechanics. And you're just like, dude, pick one. You can't do both. So I'm writing this referee report. So you've been putting something off, and then finally you're close to being done. You can see the finish line, and you're just like, I'm gonna power through on this. That feeling of like. That's like the feeling at the end of a project where you're like, really, you think to yourself, I probably should go to sleep and I should just do this the next day. But you're like, I'm so close, I can finish this thing, So that's what I did. And then, so I went to sleep too late, and then I was so excited I was done this thing, my body was like, let's wake up early. And so today I was an atypical morning person, but I'm not really a morning person. So it's gonna be a fun one, guys. Yeah. So we're picking up last time with our beautiful quantifiers, and we're gonna do some of the tricky phrases, and then we're gonna go into the Carnap stuff and do some of the homework problems. Do you guys have any questions before we go in? Oh yeah, thanks to those of you who did the survey. I really appreciated it. There's allegedly 6 people in this class who are having a blast in lectures, so that's pretty cool, basically it seemed like people were happy, and there were, I think around 3 people who were interested in more practice problems, 1 person who said fewer practice problems, and the other people were neutral. So I guess that means we just keep doing what we're doing. But totally, if at any point you have suggestions, feel free to get in touch with me, or you could use that form again and write things anonymously. Behind the veil of anonymity, what can't we say? You might wonder. Cool. All right, so this one is not that tricky. So no F is a G, or no F's are G's. We're basically just saying, for everything, if it is an F, then it's not a G. So that's the way to put it universally. Every F is not a G. Or we could also say, it's not the case that there is anything that is that is an F and is a G. Yeah. So it's not the case that there is anything that is an F and a G. I think that one will. Yeah. So not some F is a G. So we could either do the universal symbolization for everything. If it's an F, then it's not a G. You might prefer that one. Or, at least sometimes you might prefer it's not the case that there is something that is an F and is a G. And these are both equivalent by the De Morgan's rule for quantifiers, which I'm calling it De Morgan's. I guess that's like super anachronistic because, De Morgan is like alive in the early 1800s, and we don't really get quantifier logic until the late 1800s with Frege. So De Morgan didn't have these things, but I feel like, it's kind of, we're doing the same sort of picture mnemonic where if we have this thing, it's not the case that there's something that is an F and a G, then what we can do is push in the negation symbol and it hits the quantifier and flips it, and then it hits the entire expression that's in the scope of the quantifier. So this is the thing that's in the scope of our their system X. And so this ends up being equivalent to, for all X, we would have not fx or not gx. So remember, if we negate our conjunction, so it's not the case that f of g, we get not f or not g. And this is going to be the same as if we had a conditional expression. So think about this and we're like, what are our truth conditions for conditional? So if P then Q is the same as not P or Q. So here's a not F, and so this thing is like our P, and so we have Fx, then, did I screw this up? So Fx, I know it's up there, but we're trying to reason without looking at that. So for everything, if it's an F, then it's not a G. Oh yeah, okay. Because here, this is like our Q, and the Q doesn't change negation. So if it's an F, then it is not a G. Alright, did we get it right? Yeah, cool. So these things are completely equivalent, and you could, flip back and forth between them. And just, based on the sentence structure, sometimes one of them might be easier to reason through than the other. And the cool thing about Carnap or Homer, system is that it will, it checks any one that's equivalent. So, which is great for me. Honestly, normally as a grader, sometimes, people can write really creative things, and you can't immediately say it's false just because it's different than, the way you're thinking of it. And so it can get kind of annoying to check if these things are equivalent or not. Carnap just does that for me, which is good. So, cool. Any question about this? All right, if there are no questions, then we proceed. Oh no, here are examples. All right, well, so no hero wears a cape. For everything, if it's a hero, then it's not wearing a cape. Or we could say it's not the case that there is something such that it is a hero and it wears a cape. So no hero who wears a cape welcomes Greta. For everything, if it's a hero and it wears a cape, then it's not something that welcomes Greta. So it's not the case that Alex welcomes Greta. Remember, Greta is our little name for, lowercase g is our symbol for Greta. And X is a bear. Cool. All right, so Greta admires no one who wears a cape. I guess I'll give you guys like a couple seconds to try to think through this one yourself. Greta admires no one who wears a cape. We'll pull out the kind people who are here in our good pile name tag club. See if anybody else pops up today. So we're saying, for everybody, if they are somebody who wears a cape, then Greta does not admire them. And we're also saying it's not the case that there is anybody who wears a cape and Greta admires. So those are two equivalent forms. So here's our existential. It's not the case that there is somebody who wears a cape and Greta admires that person. And I guess, I didn't put the universal, but the universal would be for everybody. If that person wears a cape, then it's not the case that Greta admires them. Cool. How's it going, Luna? Put you in the good name tag pile. All right, so here's another one. Oh no, it's cool. I got it. Yeah. So technically the name tags are for your guys' benefit, so that you would know who each other are. A part of me is kind of curious how many of you come to class actually do know the names of other people. in the room, you know. Maybe at some point I'll pull you guys on that to see. I'm just kind of curious. It's yeah, I mean, it's like in my case, I have to really make, if I'm in a class, you know, where I'm like not the instructor, I have to make a really conscious effort to learn people's names. It's because you see these people like once, twice a week. It's like not, you know. Yeah, I guess, all right, close your eyes, and I'm just going to ask you guys anonymously if you know the names of, I'll say 3 other people in the class. All right, eyes closed. There's no shame. All right, raise your hand if you know the names of 3 other people in this class. All right, if you know the names of 2 other people in the class. All right, 1 other person in the class. All right, yeah, that's it. So yeah, so technically probably we should keep using the name tags, but it's okay. So, all right, so Autumn welcomed no one who welcomed Greta. So we're thinking, okay, for everybody, if it's somebody that Autumn welcomed, then it's not somebody who welcomed Greta. And we're also thinking it's not the case that there is somebody who welcomed Greta and who was welcomed by Autumn. Those are 2 equivalent things. So here's the existential. It's not the case that there is some X such that X welcomed Greta, that's this part, X welcomed Greta, and X was welcomed by Autumn, i.e. Autumn welcomed X. So remember the order is important for the 2 place brackets. This is Autumn welcoming our random person who doesn't exist. And if we had instead capital W, lowercase x, lowercase a, that would be our random person welcoming Autumn, which would be very different. And then, yeah, I guess I didn't put the universal, but, you know, you could do that one as well. So, cool. Any questions about this? Nice. All right, so only F's or G's. This one is a little more confusing than the other ones, I think. And so make a note to yourselves that, and I'll probably mention this in a future thing, if I'm going to try to trip you guys up on the final, I'm probably going to put one of these only things on it, because they're just like they're with conditionals and they're a little confusing. And so you'll want to have these down pat, probably. So we're thinking only F's or G's, when is this false? And it's false whenever there's something that is a G that's not an F. That's when it's false. So if we're saying only F's or G's, then we're saying something is a G only if it's an F. So maybe I'll put it up on the board so we can hold it in our heads. So only F's are G's just means G only if F. So there's really like an implicit only if here. And we've learned how to schematize only if. The only if is a conditional that doesn't flip the order. Order is preserved. So this thing is if G, then F. So one way you can think about this, which I don't think I've belabored with you guys, but it could be conceptually useful at this point, is the thing here in the consequent, this is a necessary condition. So F is a necessary condition for G, for the thing in the antecedent. And that's kind of what this is saying intuitively. It's saying only F's or G's, a necessary condition of being a G is being an F. And so the way I remember it is the necessary condition is the thing that's always in the consequent. The sufficient condition is the thing that's in the antecedent. That's like the more intuitive one to remember. Whenever I say if P then Q, I'm saying P is a sufficient condition for Q. If I go to the grocery store, then I'll get milk. I'm saying going to the grocery store is sufficient for getting milk. And the thing in the consequent is always a necessary condition for the antecedent, even though sometimes it seems a bit weird, but it is true. So only F's or G's is the same as G only if F, and that is if G then F. And so we're thinking to ourselves, with this expression, for everything, if it is a G, then it is an F. Only G's are F's. And so we're also, I guess, thinking it's not the case and this is probably how the slide does it first, it's not the case that there is something that is a G and that is not an F. Because when is the one case where if G then F is false? So the one case where this is false, so, this is false when G but not F. So it's false whenever G is true and F is false. That's when this thing's false. So really, I should be more precise when I say when G is true and F is false. So that would be the one case where G only if F is false, and that's this. This is a case where it's false. There is something that is a G, it's not an F. There's something that's a counterexample. And so if you're saying only F's or G's, you're saying there never is a counterexample. You're saying it's not the case that there's a thing that is a G and not an F. So, okay, so we asked only F's or G's is false when there's a non-F that is a G. And so that would be the same as it's not the case that there is something that is not an F and a G, or something's a G and not an F. Honestly, probably at some point I might, just as the, help the mnemonics, I might put all the G's on the left. Because it's really like the G is the thing that is the antecedent, the F is the thing that is the consequent. And so when we symbolize it, it might help us to remember if we keep it in that order. Or of course, you could view this as any X is a G only if it is an F. And we know only if that's our conditional. So for all X, if it's a G, then it's an F. In other words, being an F is a necessary condition for being a G. And remember, one way that we thought about only if was through the contrapositive. When we said G only if F, that's very naturally equivalent to saying if not F, then not G. And if not F, then not G is clearly the same as if G, then F. So, any questions about this? All right. If there are no questions, we proceed to an example. So, try to do this one on your own. Only heroes wear capes. And in this problem, we have for heroes as our predicate is H, and for capes, wearing a cape is C. So CX is X wears the cape. And H is for hero. So, the tricky thing is just to not screw up the order. That's it. So, for me, I'm always thinking the thing right next to the only is your F. So, that goes with that, and I'm thinking to myself, that's the thing that is the consequent. It's the thing right here. So, even though it appears first in the sentence, we're really saying, for anything, if that thing wears a cape, then it's a hero. It wears a cape only if it's a hero. Wears a cape only if a hero. That's our G only if F, and we remember only if doesn't change the order of the horseshoe, and so we're good. So for everything, if it wears a cape, then it's a hero. But you can imagine, you could very easily screw this up and mess up the order. For problems like this, you might find it more natural to do the existential, because the existential doesn't involve this ordering thing. Maybe you find that more natural. And so maybe you think it's more natural to say, it's not the case that there is something such that it's wearing a cape and it's not a hero. So you might end up preferring that way. All right, so here's another example. Only heroes who wear capes welcome Greta. Try to think through this one. Only heroes who wear capes welcome Greta. And welcoming is is W. W, X, Y. X, equals Y. I got you in a good pile, Tim. You're good to go. If any of you guys end up being super pressed for time with the problem set, feel free to get in touch and I will happily grant you an extension for my thanks to you coming to class. So that I do not lecture to an empty room. Okay. So this one is more complicated because now F is a more complicated thing. F is heroes who wear capes. So it's two properties. It's being a hero and is wearing a cape. So we're thinking, for all X, if X is somebody who welcomed Greta, then X is a hero and X wears a cape. So for all X, if X welcomed Greta, then X is a hero and X wears a cape. So again, it's confusing because we have, flipped the order here. Because this is really, for anybody, they welcomed Greta only if they're a hero who wears a cape. Alright, Greta admires only people who wear capes. So we're thinking, Greta admires only people who wear capes. So this one keeps the order. So for all X, if Greta admires the X, then X wears a cape. And we could also say it's not the case that there is somebody who Greta admires and who doesn't wear a cape. So it's not the case there's an X such that Greta admires that person and that person doesn't wear a cape. Cool. So yeah, examples like this, I feel like we got it. You got, oh, this one is a tricky one though, so we should do this one. Yeah, because this has this heroes and villains business. And when you have this and ends up being on some schematizations in OR. So that's tricky. Another question that could be tricky for a final exam, a question like this. The bottom welcomed only heroes and villains. So what does this mean? If if Autumn welcomed you, then you're either a hero or you're a villain. So for all X, so there's the existential, but here's the universal. So for all X, if Autumn welcomed you, then you're either a hero or you're a villain. So this and here is actually an or, if you do the universal schematization. Alternatively, we're saying it's not the case that there is somebody such that it's not the case that they're either a hero or a villain, and Autumn welcomed them. So if you didn't want to mess around remembering the or business, you could if you wanted to just think, really what this is saying is, it's not the case that there is somebody such that Autumn welcomed them and they're not a hero and they're not a villain. And that would be pushing this negation through using regular De Morgans and getting not HX ampersand not VX. So, any questions about this? Cool. All right, the indefinite article. So often we're using is a to lead up to a predicate, like being a hero. And often we're using A all by itself, this indefinite article, to make an existence claim. So Greta admires the hero is just saying there is at least one person such that that person is a hero and Greta admires them. So there's at least one thing X such that X is a hero and Greta admires X. But, and this is the tricky thing, sometimes you'll have A all by itself and A will actually be a universal. And so this is something to watch out for. So if you have a sentence like a hero is someone who inspires, this A here, this indefinite article, is a generic in the sense of we're talking about any arbitrary hero. We're not talking about a particular hero or even like at least one hero. We're just saying like any hero in general. So a hero is someone who inspires. We're basically saying for all X, if X is a hero, then X inspires. So for anything in our domain of discourse, if that thing X is a hero, then it inspires. So the thing to watch out for is, just sometimes A all by itself is going to be an existential, but if that A is functioning in this generic sense, like, any hero, then it's a universal. But yeah, and then another thing to watch out for if this indefinite article is in the antecedent of a conditional. So this is just like this generic case. So now we have the generic a hero, but it's in a conditional. So if a hero wears a cape, they inspire. We're basically saying, for anybody, if they're a hero and they wear a cape, then they inspire. So all the heroes who wear capes inspire. So for all x, if x is the hero and x wears a cape, close off the antecedent with parentheses, then x inspires. So you can't, you have to like read this in a certain way. We're like, well, if a hero wears a cape, they inspire. Or like, for anything, if it's a hero, then it inspires. Makes sense? Cool. All right. We want to be inspired by our heroes, right? Now, honestly, you never really want to meet your heroes because your heroes will almost always disappoint you because, your hero is probably somebody who is human and humans are fallible. And, yeah. Sometimes I've met my philosophical heroes and I've been disappointed. So don't meet your heroes. All right. So two other tricky cases. So often, most often some is an existential, but sometimes some actually gets a universal. And, typically any is a universal, but sometimes any gets an existential. So you gotta watch out for these. And, try to give you some criteria for this, but it's really just like, you just want to think about what the sentence means. That's like always your guide. It's just ask yourself, what does the sentence mean and what would it take for the sentence to be true or false? So here's our, confusing thing that you probably won't remember. So if someone or something is in the antecedent of a conditional that has a pronoun and the consequent that refers back to it, then you'll use a universal quantifier. It's very unlikely you're going to memorize this criterion, right? Probably you're just going to have a sense of what this sentence means, sentences like this, and be able to schematize them. So if someone's a hero, Autumn admires them. We're not saying like, if there's a particular person who is a hero, then Autumn admires that particular person. We're really saying like, if anybody's a hero, then Autumn admires them. If someone's a hero, then Autumn admires them. Like, if I have a student who doesn't come to class, then I'm less happy with that student. I'm not talking about a particular student, I'm talking about any student, any of the students who aren't here. So, we're really saying here Autumn admires all the heroes. If someone's a hero, then Autumn admires them. So Autumn admires all the heroes. So for all x, if x is a hero, then Autumn admires that person. So this is a case where someone is actually functioning as a universal. And then, contrast, we can have cases of any that function as an existential, and here's our little velocity. You probably won't remember. If any is in the antecedent, but there aren't any pronouns that refer back to the any, then it's existential. So if anyone is a hero, Greta is. We're really saying, like, if there's at least one person who's a hero, then Greta's a hero. And what's important here is Greta here is not in the scope of the existential. That's really important. This sentence right here is a separate existential claim. If there exists something that's a hero, close that scope. Shut that shit down. And then you have the conditional. So if there exists an x such that x is a hero, and this is an independent thought, this on its own is a sentence, then conditional Greta's a hero. And really important that you write it this way, and don't write it, so this is bad, for this sentence. If you instead wrote, there is an x such that x is a hero, conditional Greta's a hero, this means something totally different. So this is not a legit schematization of this sentence, so you do not want to write that. At some point, we might get into the quantifier conversion rules for this thing, but this thing actually ends up being related to a universal claim. So, yeah. All right. Are there any questions about this? All right. Cool. So, in principle, I guess, right, you could have this stuff like on a cheat sheet, but my hope is that you'll just intuitively develop an understanding of how to translate these sentences, and you won't have to remember these rules I mean, honestly, like, I learned how to do this stuff, and I don't think anybody ever made these two rules explicit for me. You just naturally got a sense of, you know, what the meanings of the sentences are and when to use which quantifier. Okay, so little thing on mixed domains, and then we'll probably get to the Carnap stuff. You know, what we're really here for, right, is to do homework problems. That's our goal in life, is to do homework problems. Okay, so sometimes we're talking about not just people, you know, in a domain, but like there's other things in a domain. Because our domains of discourse could really have, you know, tons of different kinds of things. People, animals, our feelings. You know, when we go to therapy, our feelings are in the domain of discourse. You know, the therapist, how are you feeling today? And that's what we're quantifying over. You know, and also, you know, your therapist, someone's like, so who did you meet this week? You know, things like that. And then we're also talking about people alongside our feelings. And so if we were going to have sentences that were a mix of claims about people and clothing, then, you know, conveniently you would just throw people and clothing into the domain. And then you just have, you know, properties that apply in general, but, you know, is a person will only apply to the people, is a person will always be false for the items of clothing. Clothing, you know, it's not. Clothes aren't people. I think even in this era, that is a non-controversial statement. Clothing is not people. So, you know, but some things are clothing. People are not clothing. Also not controversial. You know, you can't treat people like clothing. That, you know, don't do that. That'd be messed up. So we've already had a predicate CX for wears a cape. Now we'll have a predicate EX for is a cape. Being a cape is very different from wearing a cape. I hope. So you know, you got a sense of this. And so if we said something like, not everyone's wearing a cape, if our domain was just people, then we wouldn't need this person predicate. We would just say, for all X, I guess, you know, it's not, we say, yeah, it's not the case, how would we say this? Not everyone's wearing a cape. It's not the case that for all X, X wears a cape. Yeah, that's what we're saying. It's not the case for all X, X wears a cape, and this would be equivalent to, there's at least one person such that this person is not wearing a cape, not CX. And this is, I guess, a good place for me to make a note about a thing that really matters for Carnap, and that I often screw up on, which is, you see how I put parentheses here around the not CX? You technically can't do this. So don't. Carnap won't accept it as a grammatical sentence. So this thing on its own is a well-formed formula, not CX. But technically in our recursive structure, there's no parentheses around not CX. So you can't have parentheses around it. Yeah. So obviously if you guys do that, me the human grading your stuff, I'll see that on it. That's cool. That's the thing I would often do. Okay. So in the domain of people, yeah, it's not the case everything wears a cape. But if we have clothing in there, now I have to say it's not the case for all X. If X is a person, then X is wearing a cape. I have to make that additional thing to restrict the people. So if we had a domain that had clothing and people in it, I'd have to say it's not the case for all the X. If X is a person, then X is wearing a cape. So based on the domain of discourse you're working with, how you schematize things can change, you know, quite dramatically. So in your problems, you know, you're told what the domain is, and that really makes a difference to how you translate sentences. So again, if we just had people in a domain, we said some people inspire, some people do expire, we all expire someday, right? So we would say, you know, there exists an X such that capital IX, for if we just have people. Now if we have clothing items in there, we need to say, there is an X such that X is a person, and X inspires. Because we're not saying some clothing inspires in this sentence, we're saying some people. So there is an X such that X is a person, and X inspires. So you get the idea. You know, say I'm wearing something. All right, cool. So I have some slides on the Morgan stuff, the quantifier conversion, and also on formal definition of scope and extending our recursive definition. But I say, let's go to the Carnap things, we'll see how that goes, and then if we're still killing time, at the end we can go back to this stuff. So I might not talk about these slides. Maybe next week if we're killing time, I might return to it. But they'll be there for you in case you want to look at them. So I would pull up your problem set. I guess the easiest way to get to it is probably from the Canvas page. Canvas homepage, you should be able to get to problem set 8. If that's not the case, let me know. I screwed up. All right. I will be working with the instructor's version to make sure that I don't give you guys any false information, right? Prevent minor moral tragedies. All right, so the first batch of questions are dealing with a domain of discourse where we're talking about some seniors at some imaginary university, and these people are happy because there's no logic homework at this university, unlike our current ones. And you have these predicates, and so the key, I'm just going to flag this, and then we'll move on to, I think, the harder problems, because the initial ones all have auto-checking anyway for you guys. But I'll just flag, so in the first 3 problems, you're not using any quantifiers. You're going to explicitly refer to the items in the domain of discourse, because there's only 4 people in this domain of discourse: Alice, Bob, Carol, and David. And so whenever you see a sentence like, if everyone graduates, you're basically saying, if it's the case that Alice graduates, and Bob graduates, and Carol graduates, and David graduates, and there's only 4, so you can say that and it's not too tedious. So in 2, you can't use the universal for everyone. And then here, like, at least one of them will get a job. That's saying, either Alice, it's basically saying like this, but with J's. So either Alice gets a job, or Bob gets a job, or Carol gets a job, or David. So that's the first 3. And then when we get to problem 4, now you can use quantifiers, and I think you have to use quantifiers because now we have a domain of discourse that's all the MIT seniors and super seniors, and you could in principle have a name for each one of them and list that out, it'd be like hundreds of people, right? But I haven't given you those names, and Carnap won't recognize those names. So you're forced to use a quantifier, and you'll be happy that you get to use the quantifier. So that's the next ones, and so that should be chill. Then we go to the last 9 problems, where we have a symbolization key that's involving celestial bodies. We're looking to the stars, for inspiration in our lunch and problem sets. So our domain of discourse is celestial objects that are in the solar system, and we have, 7 constants. So lowercase o is the sun, which could be confusing. It's not lowercase s, it's lowercase o. We have M for Mars, J for Jupiter, D for Deimos, P for Phobos, L for Sela, and N for Neutron. And these are objects that are like in the Kuiper belts or something. There's some name. These are like connected with like Greek mythology or something. Something to do with like terror and fear. So that's great, right? That's how we're feeling about our problems. That we're terrified. We're fearful. So in this first one, we're not using quantifiers, but then the rest of them will have quantifiers. So let's do the first one, which will be an example similar to some of the previous ones about quantifiers. So problem 8, 2 of Sela, Mars, and Jupiter are planets, but not all 3. So I'll give you guys, a minute or 2 to try to do this on your own, see where you might screw up, and I will do it myself. And hopefully I won't screw up. What I can do is I can hide the screen, right, while I work on it. Oh. And so our relevant predicate here is capital P, for planet. Okay, so the first part, 2 of these are planets. This is really saying at least 2 of them. 2 of them are planets, that just means at least 2 of them are planets. It would be, this part on its own would be true if 3 of them were planets. So what are all the ways for at least 2 of them to be planets? This is like the thing that you're thinking through in these cases where the domain of discourse is small enough that you have to reference, every possibility. You think, all right, there's only 3 possibilities for at least 2 of them to be planets. It's either, Scylla and Mars are the planets, or Scylla and Jupiter are the planets, or Mars and Jupiter are the planets. Now, if we were really being, like anal, we have way more parentheses running around to, to make these things proper, well-formed formulas for a language. Carnap, fortunately, is a bit chill with some symmetric expressions. And so I think Carnap will accept this without adding additional parentheses. We'll see. And then the last part is, but not all 3, we're saying it's not the case that all 3 of them are a planet. So all 3 of them are a planet would be this conjunction, and we're saying that's not the case. So now we'll see. Cool, Carnap says correct. And if you wanted, the parentheses and stuff, you would need, you'd have to make one of these your main connective, and then you'd have to have parentheses around the second conjunct, and then you'd have to pick one of these ors to be the next main connective, and so you would need another set of parentheses. And so this would be a well-formed expression of our language, and Carnap again says correct on that. You can see, Carnap didn't require me to have all the parentheses because it was basically because it was of this kind of form, more or less, where we had something like symmetric A and B and C. It's like this, or the ors. So, but yeah, you want to watch out because sometimes you might think the parentheses don't matter, and they actually do matter. And then Carnap will need them. Okay, so now we do ones with quantifiers. Some moons orbit Jupiter, and some don't. So I'll give you guys a minute to ponder this one. If you know any of your neighbors' names, you can ask them for help. Or you could ask them their name. Who are you? I feel like that's like, the great mid-semester activities. We just go around, like, who are you? Who are you again? What am I doing here? We're learning the deep truths of the solar system. And remember, the existential is a capital E. And you gotta bind that thing in parentheses. Trying to read the room. People are working still. Listening for the clacks, the clicky clackies. Okay. So the first part, some moons orbit Jupiter. This is saying there is at least one thing X such that X is a moon and X orbits Jupiter. So capital O, X, Y is our orbits predicate. And so that's the first part, and then when we say some don't, that's just a separate existential statement. So it's, we've closed off the scope of this first existential. This ampersand's our main connective of the whole sentence. And now we just start a new existential, and we're saying, okay, and there's at least one thing X, that's a moon, and it doesn't orbit Jupiter. And we didn't have to use X here we could have used y, we could have used any other variable, but it's not a problem that we use x again because this is just a totally independent existential from the first one. So you can never have two of the same variable running around in like a single, independent thought. But it's fine, once we're outside the scope of this first bound x, then we can use x again, because x is just a dummy variable. So, but if you're ever concerned about, could I use x again, just don't use x again, just use a different variable. And then you don't have to worry about, whether you're like legally using, the same variable again. So let's see, if I screwed up, knock on wood. Yeah, perfect match, that's cool. So, great. So we got that one. Are there any questions about this?
Just
Yeah.
afterwards it says turning off auto checker. Was auto checker supposed to be on for 8 and 9? Because at least for
Yeah.
mine-
I think, I wanted auto checker to be on for 8 and 9. I think I put auto checker on for you guys for like 8 questions maybe. I'm
Okay.
trying to, it's like, there's just a lot of things you could screw up, and I feel like getting used to the syntax.
Like, at least for me, it doesn't look like it's.
Oh,
auto
really?
checker.
Oh, shit, okay, well then, I'll make a note to myself to check. I think I wanted to have auto checker on for 8 and 9. So, yeah. Because I think what I was trying to do was to set it so that auto checker was on, you could still submit a false answer. I was trying to, because it's like, I don't want you guys to, sometimes when auto checker's on, it will force you to submit a correct answer, it won't accept anything. But at the end of the day, like if you guys, can't solve the problem, I want you to be able to submit something. But thanks in that regard. So I'll check 8.8 and 8.9. Okay. And yeah, if it turns out that I can't get auto checker to work with that feature, well then, I'm sorry, but hey, you guys were here, right? So it doesn't matter to you, right? Why do you look out for your classmates? To hell with them. Now, we have to all build each other up, right? Is this part of MIT culture? We're all engineers together. One world, one engineer. Yeah, this paper I was referring last night, basically the view ends up being there's only one particle in the entire universe. There is a single Bohmian world particle. That is what is fundamental. You're like, oh my god, what are you drinking? But that's the perfect quantum mechanics. So people really believe this stuff. All right, all planets larger than Mars orbit the sun. Cool statement, bro. Let's think about it. I'll let you guys think about this as I think about it. And yet, remember the sun is lowercase o. So we're thinking universal. So incarnate, that's a capital A in parentheses. So parenthesis, capital AX, close paren. So that's our universal quantifier. Now we're like all planets. So we're like, okay, we're thinking if something is a planet, if capital PX, and this further property, if it's larger than Mars. So if it's a planet and capital L, our X thing is larger than Mars. Mars is lowercase m. So this is the antecedent of our universal. So that has to be in parentheses. So these parentheses are important. Now we're like, okay, if something's a planet and it's larger than Mars, then it orbits the sun. Orbits is capital O. Our planet, lowercase x, orbiting the sun, which is lowercase o. And now we have to close the whole expression so that the whole expression's in the scope of our universal quantifier. So what's important here is these parentheses do matter, that you have the antecedent, lumped together, the antecedent of your conditional. So without these parentheses around the P and the LXM, this thing would not work, would be false. Let's see if we got it. Yeah, let's go. So yeah, any questions about this one? The key thing is just when you see an all statement, think to yourself, okay, probably it's going to be an if-then statement. It's going to be something, that's what these all statements come to. To say all planets larger than Mars orbit the sun is just to say, for anything, if that thing's a planet and it's larger than Mars, then it orbits the sun. And so that's, where this conditional structure is coming from. Even though clearly, the sentence as written doesn't have an if-then in it. But you just think, all statement, okay, we're thinking if-then. We got to identify the antecedent and figure out, what the property is that's in the consequent. Okay, so no asteroid is larger than Mars or has an atmosphere. And here we introduce a new predicate, capital T, for X has an atmosphere. No asteroid is larger than Mars or has an atmosphere. And here's our key again, the whole key, so we can see the whole thing. So it's like this one, you have a choice whether you want to attack it from a universal or attack it from an existential. Who's voting existential on this one? Existentialists in the house? Who's voting the universal? No more. All right, so we'll do the universal first then, if there's preference for that. I think the existential is easier to think about for this one, but okay. So for all x, if x is an asteroid, so notice here that we have, and this is why our notation is really important. We have an AX and we have an AX, but the first one is a universal because it's closed in parentheses, and the second one is not a universal. This just is the predicate being an asteroid, and Carnap does not get confused about this thanks to our notation. So for all x, if x is an asteroid, then it's not the case that, so we have negation. It's not the case that it is larger than Mars. So this thing x. So being larger than Mars would be LXM, or this thing having an atmosphere would be TX. So for anything, if that thing is an asteroid, then it's not the case that it's either larger than Mars or has an atmosphere. So see if this is right. No asteroid is larger than Mars, or it has an atmosphere. Fingers crossed. Yeah, nice. Okay, cool. So that's one way to do it. So we'll put that. Well, I know what we can do. So we can see. I'll paste this one up here in PS10. Don't get confused. This is not an answer to PS10. Just so we can compare. So that'd be the universal. Now let's do the existential to make sure we can go that way too. So I'll let you guys think about how to start the existential. So we want to say it's not the case that there's some x such that x is an asteroid and x is larger than Mars, so x is larger than Mars, or x has an atmosphere. So they're saying it's not the case that there is anything such that that thing's an asteroid and it's larger than Mars or it has an atmosphere. So I think I probably naturally found this one easier because I didn't have to worry about what the negation scopes over in the inside. I just thought, okay, this thing is larger than Mars or has an atmosphere, and this is the same form, larger than Mars or has an atmosphere. Hopefully this is right. Nice, okay, cool. So these are two equivalent ways to do it. And of course, from this and from the quantifier, negation rule, the Morgans for quantifiers, I could get here. And from here, in the quantifier negation, I could take this negation, I could push it through, flip this to a universal, negate this whole expression, and negating this whole expression would end up being equivalent to this expression. So that would be another way to do it. Or you can just think through the truth conditions, intuitively yourself. Cool. Any questions about this? Cool. So you can see, you can see how you can screw up on a lot of this stuff. And so my advice to you guys is, even if you plugged in the right answer, I would later on try to do this on your own to see, can you really do it on your own without having the answer? Because that's, a true test of your understanding. Okay, so 12. Cool, we're doing great. So all moons of Mars are smaller than Mars. So this one, so this is a cool example of the richness of our language because we only have the predicate larger than, but using the predicate larger than, we're going to express smaller than. And I think in one of these we even do, in 15 we get to do the same size. So still just using larger than, we get to express the same size. So that's kind of cool. Cool. Maybe you guys don't think this is cool. This is pretty up and dumb, man. But I'll say, not all F's are G's. So. The other thing to think about too for this one is we have moons of Mars. We don't have any predicate for moon of Mars. We have a predicate for is a moon, and we have a predicate for orbits. We don't have a predicate for moons of Mars, so you have to construct this, using the predicates you have. Okay, so thought process, we see the all, so we think universal, and then we think, okay, a regular universal, there's going to be a conditional somewhere, so we have to think about it as an if-then statement. So we see all moons of Mars, they're smaller than Mars, and we think to ourselves, okay, for anything, if it's a moon of Mars, then it's smaller than Mars. That's our thought process. Before we've written anything down, we know we're going to, have this conditional, you put it in, and the consequent of the conditional smaller than Mars, that's the easy part. So smaller than Mars just means Mars is larger than that thing. So capital L, put the lowercase m first for Mars, and then our arbitrary thing x. So that's our consequent. X is smaller than Mars is the same meaning as Mars is larger than that thing. Any questions about this so far? Cool. And then in our antecedent, we have this slightly trickier thing, moons of Mars. So we're like, all right, X is a moon, mx, and it's a moon of Mars, so it has to orbit Mars. It can only be a moon of Mars if it orbits Mars. So capital O, X orbits Mars. We put the X first, because the X is the thing orbiting Mars. Of course, Mars is in some sense orbiting X. We know from our physics classes, but you know, we're hewing to this meaning. I guess it's a funny question. I feel like, yeah, Carnap, semantically, you know, if it had semantic knowledge, it should accept if I do OMX, but it wouldn't. So you don't want to, you want to think like, I don't know, like pre-Newtonian physics in this conceptual scheme. Cool. So hopefully this works. Yeah, and you can see, you know, I have like tons of, you know, bizarre spaces here, and it's like, that's like no big deal, you know, that I have this random ass space here. It's all good, you know. I have a space here, but I don't need that space. I'll take it. So, you know, there's still a bit of flexibility in what it accepts. Cool. All right, so not every moon larger than Deimos orbits Mars or Jupiter. Every moon larger than Deimos orbits Mars or Jupiter. Cool. Well, what do you guys think about this one? We'll think about it too. Try to do it both ways. If you've done it one way, try to do it the other way if an existential or universal. See if we got these bad boys. So here's my attempt at the universal one. We're saying it's not the case that everything such that that thing is a moon and that thing is larger than Deimos is such that it either orbits Mars or it orbits Jupiter. We Hail Mary and yeah, let's go. Got it. Did anybody who attempted the universal have a question about this? Does this seem not natural? The tricky thing with the ors is just to get the parentheses right. You know, like it's important that this is the whole consequent, this or expression. Alright, so that's the universal. First I'll paste in, this is what I think the existential is, and I'll put the universal up on 12. So I'm writing over the answer to 12, and I'm putting a wrong answer to 12, just so we can compare. Alright, right, so if you instead wanted to think about it with the existential, you're thinking, okay, not every moon larger than Deimos orbits Mars or Jupiter. You're thinking there's a counterexample to this statement. There's a counterexample to every moon larger than Deimos orbits Mars or Jupiter. What would such a counterexample be? It'd be something that is a moon and that's larger than Deimos, such that it's not the case that that thing orbits Mars or orbits Jupiter. That would be the counterexample, I hope. And we make sure our parentheses look good. Okay, we closed off outermost left and right, and then we center. Yeah, cool. So this one works as well for the existential. Any questions about this? So yeah, it's like, I guess in principle one could always say, like, for a problem like this, they're either going to do the existential or the universal. I'm kind of like, yeah, why not understand how to do it both ways? That shows your understanding of the truth conditions. It's like, and reasoning through this, it's not like I memorized anything. I didn't memorize like really any schemas. We're just like thinking about what these things mean. That's the ultimate endpoint that we're aiming at. Okay, so 14, and allegedly for 14 I put auto checking on. So maybe we'll skip 14 and come back to it if we get time. Probably will. And yeah, let's do this fun same size one. So 15. Fun is a very relative term, of course. So some asteroids are the same size as Phobos, allegedly. Phobos is lowercase p. Obviously, if you've already done this, feel free to move on to other problems, since this is in fact your problem set. So we see the sum, so we're thinking existential. We will choose the existence of asteroids and define them in their full freedom. But we will say that they're not the same size as Phobos. So there is something X, close that off, open up a new thing. X is an asteroid, and we're saying it is the same size as Phobos. So what does it mean to be the same size? Well, it means if I'm the same size as you, then I'm not larger than you. So this thing, X, is not larger than P. It's not the case that X is larger than P. And likewise, if Phobos is the same size as me, then Phobos is not larger than me either. So it's also not the case, so ampersand, it's not the case that Phobos is larger than me. And so this expression, this conjunction of negated larger than claims, this is just what it means to be the same size. This is what it means for this arbitrary thing X to be the same size as Phobos. So that's the little trick in this problem. Because we don't have a predicate for same size. And of course, if we're going to be really, I guess, sticklers for our well-formed formula, we would need another set of parentheses here so that this and is the main connective of the thing in the scope of the existential. But Carnap won't care about that sort of thing. So it takes this, but even if we didn't have this second set of parentheses, since these are all conjunctions, it's symmetric, and Carnap is cool. Carnap's cool with that. So that's why we're cool with Carnap. Carnap didn't accept that, and we wouldn't accept it into our hearts and minds, and we would say, burn this to the ground. And we would email Dr. Graham Leach Crouch and say, "You have constructed a monstrosity." I still need to email that guy and thank him. I think I'm close to this point. I've done most of what we're going to do in Carnap, I think, and there's no further books, I think. Yeah. Even though it is, I do find it a bummer, this thing about the, that it doesn't accept parentheses around the atoms. Maybe we'll see an example of that. It's just a little annoying. Okay, so 16, all and only planets larger than Mars have an atmosphere. So this is the kind of problem we've not done yet. All and only planets larger than Mars have an atmosphere. Pictures on my little board work. In case this is anything I want to build in the slides later on in life when I'm teaching this in 2044. Honestly, I mean, I hope I am teaching logic in 2044 because that would mean I didn't kick the bucket, right? Okay, so the question is, what connective is going to function for the all and only? Any brave volunteers? Yeah?
Would be the biconditional.
Yeah, biconditional. So that's the key trick in this one. So we have the all, so we're thinking universal, but we got to get that only in there. So we're basically saying, for everything, that thing has an atmosphere if and only if it's both a planet and it's larger than Mars. Equivalently, for all things, it's a planet and it's larger than Mars if and only if it has an atmosphere. So we have an antecedent of our biconditional. It's a planet and it's larger than Mars. And we're saying if and only if that thing has an atmosphere. So we're basically saying, like, the only things in the universe of discourse. And here we're, our universe is the solar system. But it seems more grandiose, right? And it's at least celestial. At one point we thought, that we were the center of the universe, right? So our solar system is very special in our minds. So yeah, we're basically saying the only things in the whole universe that have an atmosphere are things that are planets larger than Mars. So if anything was not larger than Mars, it wouldn't have an atmosphere. If anything wasn't a planet, then it wouldn't have an atmosphere. That's what this is saying. And I hope this is right. Yeah. Cool. All right, and then we have one more in this batch, and I guess also the one of auto-checking 14 that we could come back to. So 17, if Jupiter has a moon, it has a moon with an atmosphere. Oh, and this one might illustrate the little Carnap foible that I want you guys to be aware of. Cool. So yeah, try to do this one. Jupiter has a moon. It has a moon with an atmosphere. This one definitely is a bit trickier. So it's cool we're doing it in class. Thank you guys. You'll have the right answer. Whether you understand the right answer or not. One can always understand later, right? Understanding is aspirational. The understanding will always be out there waiting for you. Forget my beloved chalk. I left my mini stapler in this room during the exam. That got taken away. There's a happy MIT student with a beautiful blue mini stapler. We're happy. In my heart, I'm happy for them. That little stapler is going to serve them well, probably better than how it would serve me. So. There'll be more mini staplers in my life, right? You know, they're out there waiting.
Didn't you say you had had that for like a long time or something?
Oh, the black stapler, I took that. I put my name on that bad boy. Yeah, the black stapler. Yeah, I had that since Pittsburgh undergrad philosophy of science club. So I got that from the Pittsburgh Student Activities Committee. Nobody's going to take that away from me. Yeah. If I lost, you know, like people lose their dogs and they put up like missing, you know, dog. If I lost that black stapler, you'll see a missing sign. You know, mark my words, right? All right, so let's do this one. If Jupiter has a moon, so just take it step by step. This is an existential statement at the get-go. Jupiter has a moon. We're basically saying if there is something, some x, such that x is a moon and x orbits Jupiter, namely it's a moon of Jupiter. So that's the first part. If there is something x such that x is a moon and x orbits Jupiter, now we close this off. We're outside the scope of this existential. We're doing an if-then statement. So the whole sentence is an if-then. The main connective of the sentence is a conditional. Now we have another thing, has a moon with an atmosphere. Okay, it is Jupiter. So we're basically saying if there is something, so another existential, if there is something such that it's a moon and it orbits Jupiter. But now this further thing, it has an atmosphere, Tx. So capital T is our predicate for atmosphere. So this is an if-then statement of two separate existentials, and it's really important that you have the two separate existentials. You would not want to put the if-then statement within a single existential. It just wouldn't be the meaning of the sentence. We're saying if there is at least one thing that is a moon of Jupiter, then there's at least one thing that is a moon of Jupiter that has an atmosphere. That's what this sentence means. So let's see. Knock on wood. Yeah. So this is correct. And again, for the second existential, you could use y everywhere. You just have to be consistent. So if you're, concerned about mixing up your variables, you could just follow a rule that whenever you introduce a new existential, a new quantifier, you're going to introduce a new variable, and then you wouldn't have to worry about, is the thing being a dummy variable or not. So also, accept that. So. Any questions about that? Yeah.
It feels like it should be semantically equivalent at least to something you could express in only one, like EX.
Mm-hmm.
Like, shouldn't you be able to say EX, like it's a moon and it orbits Jupiter, then...
Yeah, so the tricky thing, so it's like, yeah, so, let's try to think about it this way. We're going to put the whole if then in, get rid of the second conditional now, and we'll go back to x's. So we're thinking, what would this be saying? This would be saying there's at least one thing such that if that one thing, is a moon and orbits Jupiter, then that one thing is a moon that orbits Jupiter that has an atmosphere. And so this sentence is saying, whatever is the thing that is a moon of Jupiter also has to be the moon with an atmosphere. Whereas as written, this sentence doesn't require that the thing that has the atmosphere is the same thing in the antecedent. It could be the case that it could be the case that what makes the antecedent true, Jupiter has a moon, is a moon of Jupiter that doesn't have an atmosphere. And then there's some other moon of Jupiter that does have an atmosphere. And as written, the sentence would still be true if that were the case, but this schematization would be false in that case. Because this thing...
But wouldn't the schematization still be true because there still is an X being that other moon that does have the atmosphere?
No, that's true. But I wonder, I maybe have to think of a different example. I wonder if we're in the background relying on some facts about physical
because if you write the if then as the or
mm-hmm.
if you say either the consequent is true or not the antecedent, then if the consequent is true, then the antecedent
doesn't matter.
Has to be false, right? Because the consequent
mm-hmm.
includes the antecedent.
Yeah.
So, can't you just basically like shorthand it as.
Yeah, no, I guess I'll think about it some more. So I think Carnap's gonna say no on this, yeah. But yeah, I'll think about your question. And I mean, it is true. If anybody writes this in, they're gonna get a ton of partial credits. You know, I'll probably take a point for this if somebody writes this. You guys won't have written this. You'll get all points. But yeah, I'll think about whether this on its own should really be a legal answer. So cool. All right. So you guys have done more than half the problem set. Yeah.
I think the thing that's there is true so long as there exists any X which is not a moon of Jupiter.
Okay.
And then that's
because this. Oh yeah, no. See, this is a good point because with conditionals, yeah, they can be trivially true if the antecedent's false. So, but I guess, but this thing on its own would also be trivially false if Jupiter doesn't have a moon. So it's tricky.
Well, Jupiter could have a moon, but no moon with an atmosphere.
Mm-hmm.
And there could also be a thing that is not a moon of Jupiter.
Uh-huh.
And then the thing that the formula there would be true, but the sentence would not.
I see. Okay. Yeah. Does that help me out in terms of what I'm doing is the right answer? Or
Yeah, because then that would have to be wrong.
Yeah. Okay. So cool. Thanks, Owen. But yeah, we'll ponder this some more. But cool. All right. So thanks, guys. And I have office hours basically right now. So feel free to come to those. And hopefully you're well set up for the problem set. She really wanted her meals to be very specific temperature. She wanted me to start a company on hot plates. She was like, you should get on this. This will be, a great invention. People need hot plates for their meals. And I was like, I don't think most people care that much.
My family thinks I'm weird for preferring all my food cold.
Yeah, I mean, there's some advantages, which is sometimes I'm upset if I heat something up and it's too hot and I'm really hungry and I really want to eat it, but then it's so hot that you have to take like little bites or you're gonna burn yourself,
Mm-hmm.
And then you're kind of just like, I should have just eaten this cold, because then you could chow down at Chowtown. How was your weekend, Charda?
Pretty good.
Good on?
Yeah, relaxing.
That's good. That's what we want from the weekends.
One of those days, I just do not feel like doing anything. Oh my god, I'm gonna wear the same shit. Did not do a very good job of color coordinating today.
Color coordination is not essential. I don't really know what the rules are. You're not supposed to wear white after Labor Day, right? That's a rule. But when does it become before Labor Day? Right? Like, does it reset in January? I think the thing that always gets me on color coordination is, like, let's say you're gonna wear something green, and then what other kinds of green are you allowed to wear? Clearly, like, they don't have to be the exact same tone. Like, there's ways of like having like dark green and like a light green undershirt, and certain forms of that are acceptable, but other forms would be unacceptable. Like if you wore like an emerald green shirt with like I don't know, like a Kelly green. Well, maybe, I don't know, maybe that would work. I don't know, you could think like some bizarro kind of green color with some like dark green, that'd be weird. What's funny is really I think a lot of philosophy comes down to this kind of intuition that some things just fit together and some things don't. And when you're criticizing a philosophical view, typically you have an intuition that it's basically like these two things don't work together. They don't fit. They're not matching. And it's really kind of like art criticism in a way, like looking at a painting and like the great paintings, you're just like, wow, it all works, it's all there. And then like paintings that are good but not great, you're just like, something is off. It might be pretty difficult to describe what's off, but something's off, you know? And then you worry, do we only have these intuitions because we've been brought up in a certain culture, and if we've been brought up in some other culture, we'd have other intuitions? Is there really anything to say here?
It's the last day of Dracula.
The Last Day of Dracula?
Mm-hmm.
What is is this a play or something?
No, like the book Dracula. It's
Oh, is it gonna be in the public domain?
no, the book takes place from May 3rd to November 7th,
Oh, okay.
and I've been reading it every day.
Oh, that's cool. I didn't realize, I've never read Dracula. Do you recommend reading?
It's yes, with a couple of caveats. One being, holy shit, the racism.
Oh, okay. Yeah, I guess this is written in like 1860s?
I believe like 1890.
1890, oh, okay.
1896. Published 4 years before blood types were discovered. So there's like huge like plot points about, oh no, is this blood transfusion going to work?
Oh, interesting. Oh, okay. That's pretty cool.
And it's like, well, just check the blood type. Some of them just do not work. But the book is fun. I especially like there's a character that like every adaptation cuts out. It's the American cowboy who just like, whose solution to everything is gun.
Wait, the solution to everything's what?
Gun.
Gun, okay.
He just goes around shooting people.
Yeah.
I mean, he never makes it into anything.
Uh-huh.
That's guy.
Yeah.
Good.
So it's like a Braun character?
Hmm?
Just like the plot line for this character is just like fight it out?
Yeah.
Yeah.
He's just there. And every time they're like, what do we do to combat the vampires? He's like, I have a gun.
I feel like, in most people, there's that kind of emotional state. Definitely when I was going through rough times a couple summers ago, I just watched all the John Wick films, and that was my mentality. I was like, let's go.
Let's go.
This is how I feel about the world. And then I was like, come on, John Wick 4, don't be delayed because of COVID. I need you. Has John Wick 4 come out yet, or is it still delayed?
Yeah, it came out.
It came out? Oh, okay. I need to jump on that. That would really be cathartic for me at the moment, I would say.
What year is it right now?
It is 2022.
Okay.
Morning, Daniel. How's it going?
It's good.
It's going. Is this week not as chill as last week?
It's starting to not become so.
Yeah. I could sense it. We had that calm before the storm, When everything slowed down, part of me is always like, am I really caught up on everything, or am I about to be woefully behind?
Like if I have a week with no test, and just know next week's gonna be a week with tests.
Yeah. Totally.
I don't know. Can I just like be ahead for the rest of the semester?
Yeah. No, I think the thing is like, at least my psychology, whenever I know there's something I have to do, thinking about it makes me feel like I am behind, even if I'm not behind. Just knowing that it's in the future. It'd be really cool if one could like just trust themselves that, they'll stay on top of things as things come up, they'll handle it, and there'll be nothing to worry about because, as the, issue arises, you'll deal with it then. If you could have that kind of trust.
But that only works if you always get what you expect from yourself, right?
Yeah.
Because say you get a bad grade and you trusted yourself.
Yeah.
Yourself again.
Yeah. No, it is true. It's almost like, I don't know, I can't surf at all, but the people who are professional surfboarders, they're not in control of the waves, but assuming they're not stressed out all the time, they're probably not, because they seem kind of chill, right? That's like surfboard attitude. They might think, if they think about this at all, they might think to themselves, well, I'm well trained, I know what to do, I'm a professional. And no matter what the waves are, I'll be good. I'll handle it.
But I feel like that's only for like a task that's, you can do all the same thing,
Mhm.
like the same time, right? You like, you surfboard into different things obviously, but
Yeah, yeah.
ultimately the same thing.
Mm-hmm.
Because I take a test, and the next week, the test's completely different.
Yeah,
So
yeah.
I can't, there's no continuity.
Yeah, no, that's a good point too. Yeah, no, I do think the mentality that I am aspiring to, it does seem to only work if you're given a very consistent set of challenges.
Yeah.
Yeah. But I don't know. I mean, I hope that each one of us at a certain point in our life will say like, yeah, we're good, for the stuff that's going to come up. I'd really like to have the mentality of, I see people like, go to their office jobs and they have a cup of coffee, and I just think, this person's job is probably, like, what if it's like data entry, like, what if my job is data entry? I wake up, and would I be stressed about anything? I'd be like, no, I'm just gonna input data today. And I don't really know what this means, but it sounds chill. I'd get my coffee, and I'd sit down, and I'd be like, great, we're gonna input data. And when I'm bored, I'll take a break. It'd be really cool just to feel that way about everything, like things that aren't as boring as data entry sounds.
Some of the data entry people, they'll write like Python script to do it
Mhm.
automatically. So they go to their desk, just turn on Netflix or whatever.
Yeah.
Every time the boss comes, you switch off.
See, that sounds great, right? Yeah. Yeah, as long as you're not bored. All right. Oh, I guess we're contractually obligated to start. So we'll start with some stuff that we, I guess, breezed over last week, and then if anybody trickles in, then they won't miss the start of models and interpretations. So, but this I think is good stuff to review. So, just to have it in cram, we have these conversion rules for quantifiers. So, whenever you have a negation symbol in front of a universal quantifier, you can always imagine taking this negation, hitting the universal, you turn it into an existential, and then the negation carries through and hits whatever is being quantified over and negates that thing. And likewise, if you had a negated existential, then the negation hits the existential, turns it universal, carries through, and hits the thing that you were existentially quantifying over. And so this is useful for a lot of problems, especially if you're asked whether or not two sentences are equivalent, and one of the sentences has a negation in front. Often it's helpful to convert the thing to a sentence that doesn't have a negation in front. So if you had, this sentence, it's not the case that there is something that's an H and a C, then we say, okay, this is equivalent to saying everything is such that it's not an H and a C. And then at this point, you can do the regular De Morgan's and push this negation through. And you say, okay, everything is such that either it's not an H or it's not a C. And so being able to do this is often really useful for the kinds of questions for this week where you're basically being asked to compare sentences and to figure out, okay, if I make this sentence true, can I make this other sentence true? Or if I make this sentence true, will this other sentence have to be false? All right. So scope of quantifier, subformula for which the quantifier is the main operator. So here Lx and Rgx is in the scope of the existential. Here Lx is in the scope of this existential. Rgy is in the scope of this universal. And these are just independent thoughts. They can have independent truth values in an interpretation. And so here we have a notion of this variable y is being bound by this universal quantifier in this existential. This variable x is being bound by this existential. So, any questions about the notation? Cool. So one thing we didn't do last week, but could be helpful this week conceptually, we're talking about the truth conditions of these sentences, is to briefly expand our recursive definition. So we are taking sentential logic and we are strictly adding more stuff. So this was our recursive definition for SL. We had the atomic formula, and here the atomic formula were really easy to think about. They were just sentence letters. That's what an atomic formula was. And SL, those things are still going to be atomic formula, but now we're going to have more atomic formula, more atomic sentences. And so we knew we could take something that was a well-formed formula and negate it. We can combine things with an ampersand, with a disjunction, with a conditional, or with a biconditional. And then we said nothing else is a sentence of SL. So now we're like, how do we modify this to get our quantifier logic recursive definition? So here, one thing that is very easy to forget is the atomic formula include things that are, pretty long ways. So if you had a three-place predicate of T, so if T was a three-place predicate TXZ, then this thing would be an atomic formula with variables. If you instantiated each of the variables in a TABC, this thing would also be an atomic formula. So it's not just sentence letters anymore that are atomic formula. And the sentence letters, you can think about them as being a kind of degenerate case. So when we just have sentence letter, let's say B, so this could be something like, we in this class today are beautiful people. So this would be our atomic sentence. B, this is a zero-placed predicate. It's basically a predicate that doesn't take any variable or name. Whereas this is a three-place predicate, it takes in three things. And often, we're talking about one-place predicates, so we could have a one-place predicate bx, which would say x is beautiful. So in quantifier logic, you just have to keep these things straight. This atomic sentence B is very different from this atomic sentence bx. And this one, bx, is also different than, we could do bh, where h is me. Huh? We're having positive thoughts on Monday. Yeah. So that's the atomic formula. So we basically just modified what it means to be an atomic formula from our earlier recursive definition. And then we add on two additional ways of generating things. So if you have a well-formed formula, and you have some variable chi, so chi is a meta language thing, so chi could be any variable. Our variables can be w, x, y, and z. And if phi doesn't have any quantifiers that bind chi, so basically if there's nothing in phi that is an existential chi or a universal chi, then for all chi, phi is a well-formed formula. And then any of those chi's that are in phi, they would now be bound by this universal. Likewise, if you had a phi and you had some variable chi, and phi didn't have any chi quantifiers, then you could bind it with an existential. So the main thing that these definitions are telling you that you can't do is you can't do something like the following. You can't take bx. So if you had something like for all x, bx, where this is everybody's beautiful, you could not add on an existential with the same variable x, because here chi, here's our chi, this little guy, or this is our phi. So this is our well-formed formula phi, and here in this case chi is just x, and here phi does contain a chi quantifier. It has a quantification over x, and so we can't add on a there is an x. Can't do that. You could do any other thing. You could add on like there is a y. This would now be like a very interesting sentence. There's a y such that everybody's beautiful. Doesn't really say much, but you could do that. So that's basically the main thing. And then we say that's it. That's all the stuff. And the one thing that's often a little confusing in Carnap, but which I, the human, will be graceful about with you guys, is since this bx is an atomic formula, you can't put parentheses around bx. You can't put parentheses around txyz all on its own. Just because you remember in SL, we never put parentheses around just bare atomic sentences. The parentheses only entered when we added a binary connective. You add an and, or an or an if then, or an if and only if then you get parentheses. But the atomic guys never have parentheses around. So, any questions about this? Cool. All right. So one, this is just the terminological note. Whereas in SL, we could just move back and forth between well-formed formulas and sentences. The sentences just were the well-formed formulas. Now this is not the case. And there are things that are well-formed formulas that are not sentences. So now you ask me, well, what really is a sentence? A sentence is something that has a truth value. A sentence is something that is true or false. And when we're looking at t, x, y, z, these guys are variables. There's no, on its own, like this doesn't have a truth value. It's just, it's basically just saying x and y bear t to z. But you don't, x and y and z are variables. They're not concrete things. So in contrast, TABC, where A stands for something, B stands for something, and C stands for something, this will be either true or false. And any interpretation will be true or false whether A, B, and C stand in relation T to each other. And so TABC is a sentence. TXYZ is not a sentence, but it is a well-formed formula. Yeah, Henry?
So I guess how is that different from like in SL? You can have the well-formed formula psi and phi for sine and phi are variables.
Yeah, so basically the difference is that whenever we have in SL, whenever we have sine and phi, where psi, phi sentences, then this means these guys are either true or false. And so this thing is a truth functional connective. And so basically, this thing is a sentence if and only if sine and phi are sentences. Because that's precisely when psi and phi will have a determined truth value. Under any truth value assignment to the atomic sentences, psi and phi will have some truth value, and so psi and phi will have a truth value by the truth table. But if you had something like, now we can do the following, so we could let psi be TABC, and we could let phi be TXYZ. So this thing is a well-formed formula of quantifier logic. We just followed, one part of our recursive definition. I took something that was an atomic QL formula, and this is another atomic QL formula. I put them together with an ampersand. So I basically used this rule 3, now for quantifier logic. But because TABC is a sentence and TXYZ is not a sentence, this thing will be a well-formed formula of QL, but not a sentence. This is not a sentence. So this is, just a terminology thing, where now we're thinking sentences have this special meaning. They're the things that are determinately true or false in an interpretation. Whereas, TXYZ is just not determinately true or false in an interpretation. If we did write something like the following, so if we bound all these variables, if we have for all x, there is a y, such that for all z, TXYZ. Now this thing has no free variables. Every single one of these variables is bound by its own quantifier. And so this thing is a sentence. And this thing will be determinately true or false in a model, in an interpretation. And so this is basically our criterion. A sentence of QL is a well-formed formula that has no free variables, where free variable is just a variable that isn't bound by a quantifier. It's a variable that's not in the scope of a quantifier, with its variable. And it's you could have more stuff going on in here with x, y's, and z's. You could have something like a bx, and you could have a bz. And so this x and this x are both bound by the same quantifier. This z and this z are bound by the same quantifier. So it's not the case that there's like a one-to-one relationship between quantifiers and variables. It's just that whenever you have a well-formed formula that's in the scope of a quantifier, every instance of x that's in the scope of this for all x is bound by this for all x. Every instance of y that's in here is counted by this. So if you had, we closed this guy off, and now if we had another thing, and we put txyz again, these guys are not bound by those quantifiers. These guys are outside the scope of those quantifiers. And so now that we tap on this thing, which is a well-formed formula, but it's not a sentence, now this whole expression is no longer a sentence, but it is a well-formed formula. So, and technically, it should be within, a mega parenthesis. And Carnot will do that, but you don't have to be anal about the mega parenthesis. But you would go wrong if you put a baby parenthesis around this thing, because this is atomic. So, cool. Any questions about this? All right, so basically today we're doing the truth conditions for quantifier logic, and the way we think about them is through interpretations, where an interpretation is really just a generalization of truth value assignment from sentential logic. So we're really just generalizing this notion. It's pretty fun. We can draw pictures, everybody likes pictures. We're graphical thinkers. All right, so basically the whole reason we're doing this is we want to have methods for assessing validity. That's what we're obsessed with in this class. We have a validity fetish. This is deductive logic. And so we're confronted with the following argument, and we're like, all right, is this a valid argument? Everyone is either good or evil. It's true, right? Not everyone is a villain, we hope. Not everyone. Only villains are evil, and then we conclude some heroes are good. Now, this is clearly a true conclusion, but the question is this thing valid? Where, remember, validity is a function purely of logical form. It has nothing to do intrinsically with the meaning of any of the sentences. So even though, each one of these premises seems true and the conclusion seems true, that on its own is not good enough for validity. So we're trying to basically just get the structure, the logical structure of quantifiers and names. And so in order for an argument to be valid, it has to be true in every interpretation. It has to be true no matter what we assign to these predicates. Here we have a predicate good, evil, we have villain. No matter what we assign to those predicates, no matter how we interpreted them, the argument, if it's a valid argument, would have to be valid under any interpretation. It would have to be the case under any interpretation. If the premises are true, then the conclusion is true. That's our definition of validity. So basically, if you're trying to counterexample this thing, we're allowed to do any interpretation we want. We can assign anything to these predicates. And an argument will be valid in QL, valid in quantifier logic, if and only if there's no interpretation where the premises are true, then the conclusion is false. So basically, today we're going to have a method for getting counterexamples to validity. We won't have a method today or this week for proving that an argument's valid. Next week, when we return triumphantly to natural deduction, then we'll have a formal system for proving validity. We will, maybe today or on Wednesday, we'll have like informal arguments. You can give informal proofs that an argument is valid, where basically you are saying something like, consider an arbitrary interpretation. In this interpretation, if the premises are true, then the conclusion would have to be true. And so it's just like a little proof in that. So we can still do stuff like that. But to have a formal proof and a proof system, that will require us to extend our natural deduction system. So basically, this week is super chill. If you guys end up with time to spare on logic, it could make sense to review sentential natural deduction. If you found natural deduction tricky, you're going to have to know everything that you were called upon to know in the sentential case and more. And we're going to add, next we're going to add in rules, and 2 of them are going to be somewhat complicated and have somewhat complicated restrictions that it's really easy to screw up. So you'll want to have down pat the sentential stuff. And this week is pictures, which we love. So we can schematize this argument. We just decide what predicates to use, and so we'll do G for good, E for evil. So the first premise, everyone's either good or evil, saying for all x, either GX or EX. When we say not everyone is a villain, we're saying it's not the case that every X is a VX. And then remember, the only sentences are a bit tricky. So only villains are evil. This is the same as saying, it's the same as saying you are evil, and all of you are very evil, I would say on this Monday. So you are evil only if you are a villain. And so, not too far. Spoilers. So you're villain, and I spelled villain wrong. See, villain is tough. It's a tough word to spell. Villain. So this is, I write everything with voice software. If you use voice software at a certain point in your life, you kind of forget how to spell words because you're just not writing them. So I think about words like in the word, like not the letters. Yeah. So it's kind of weird in a way. So you're evil only if you are a villain, and this, remember, just is our conditional, and it doesn't flip the order. Only if keeps the order the same. So this is just saying if E, then B. So this is equivalent to saying, all evil people are villains. I'll try to learn how to spell villain. Villains. All evil people are villains. So that's, a tricky one. You don't even. I think, if you see an only, you're thinking that's the necessary condition. The necessary condition is the consequence. That's one way to observe. Or you just think you're leaving it. And then we have some heroes are good, there's something that's inherently good. So basically the heuristic for this argument, it's invalid, as we'll see. We'll give an interpretation where we make the premises true and the conclusion false. But one intuition you can have is just, there's an H in the conclusion, there's no H up here. And so this H is coming out of nowhere, and it's not coming out of nowhere with an or. Remember that with ors, you can often just tack on disjunctions willy-nilly. That was our disjunction introduction rule. It's like, typically when you add on a disjunction, you're just weakening, the sentence. You're just making it logically weaker. So it could be entailed by things that don't mention it. But here we have an ampersand, and we have some predicate we've never talked about. So you're kind of thinking, there's going to be a counterexample to this argument. So this is what we'll use for our counterexample. Well, now we switch to a totally different interpretation, totally different model. So our previous model was people, and we interpreted the predicates good, evil, villains. Now we have a new model, and our domain of discourse will be the inner planets, Mercury, Venus, Mars, and Earth. And we'll have, now G will mean X is smaller than Earth, E will mean X is inhabited, V will mean X has a moon, and H will mean X has rings. And we'll just show that each of these three premises is true, but the conclusion is false. All right, so before we do that, we step back and we define some things, because that's what we're doing in teaching things, right? We give definitions, make our concepts precise. So, domain of discourse, or universe of discourse, in this example will be our solar system of discourse. Some collection of objects that cannot be the empty set. And for each of the names, you have a referent. So if you have, let's say, a name A, so this will be like the way that things will look on Carnap often. You'll have your names, which are things like A, B, and C, and then you have your referent, which is what these names refer to. So here, let's see, if I give myself the name H, then H refers to me, Hunt. And often in Carnap, we're using numbers. So you might have the name A, and you might choose to let A refer to the number 1. And so it's just that, it's kind of like, here, you might, so it's like Hunt, this is where we really get back to use mention. I didn't put Hunt in quotes. Here I'm using Hunt, and it really means Hunt. It's referring, it's Hunt. The name, that we use typically is not a lowercase h, but we typically use Hunt in quotes. Hunt in quotes is a name of Hunt. So just important to keep those things separate. And this is I guess a function in the sense that every name has to stand for one thing, but you can have two names for the same object. So for instance, I am also Josh. So Josh is another name that also refers to Hunt, and there's no problem here. We have multiple names. You can have multiple names for the same object. What matters is that on the reference side, there's only one thing, Hunt. There's only one me. I'm unique. We're all unique, and in virtue of that, we're all special. That's the case. But you can have multiple names, and so you could have A refer to one, and you could have B refer to one. There's no problem with that. And then I guess 2 weeks from now, when we get to add identity into our quantifier logic, then it'll make sense to say things like A is equal to B. To say A is equal to B basically just means A refers to exactly the same thing that B refers to. So clearly, the symbol A is a different symbol than B. Here we're saying, is it the case that what A refers to is identical to the thing that B refers to? And in our typical case, people's names, it's true that the thing that Josh refers to is the same as the thing that Hunt refers to. Okay, then we have properties, and each property is represented by a predicate, and the predicates have extensions. So an extension of a predicate is just a set of things in our domain of discourse that have that property. So if you have a one-place predicate, for instance, if we had our most beautiful of predicates beautiful, the extension of the predicate BX, that's beautiful, is just everything in your domain of discourse that's beautiful. So if our domain of discourse is people in the class, and if we're all beautiful, then the extension of B just is the set of each one of us. It's the set that includes us all. Now, if you have relations, like multi-place predicates, then in the case of a two-place predicate, it's just the pairs of objects that stand in this relation. So if we had a predicate, we had something like shorter than, so S was, so SXY is, X is shorter than Y, the extension of a two-place predicate is just a set of ordered pairs, basically. So extension of S, S is some set, here are little squiggles, and the book uses brackets, like basically on Carnap they'll use like a less than and greater than sign. The book, it's rendered nice as like angle brackets. But so let's introduce C. C will be our piece of chalk Chad. So I don't want to get in trouble these days. We've got to be politically correct, right? So one thing I'm confident I can say is that Chad is shorter than me. This is Chad. I don't know if that's the same Chad as last week, So here we have C comma H. C comma H is in the extension of S. Something that's not in the extension of S, so the following H comma C is not a member of the extension of S because I am not shorter than Chad. So we wouldn't put H comma C in there, but you can put C comma H. And so again, the order of these things for asymmetric relations, can make a big difference. And then likewise, if you guys are in the domain, for each one of you, you have some name, and so there's going to be other stuff in here for each one of you. Like for Gerardo is also, taller than Chad, so we would put C comma G in this thing as well. And this is the kind of thing you're doing on Carnap. as we see, when and if we get to examples. So here we have our domain, these 4 planets, and we're, basically we just have to figure out, all right, what are the extensions of these predicates G, H, V, and H? So G is X is smaller than the Earth, and Mercury, Venus, Mars are all smaller. This is like diameter. They have shorter diameter than the Earth's diameter. Of these 4 planets, the only one that is inhabited, as far as we know, is Earth. Perhaps on Mars, somewhere under the surface there's like microbes, but here we mean something like inhabited by like, not like bullshit life or something. Not like bacteria, right? It is funny. You read these news articles and it's like basically scientists getting super excited about. We have evidence that on Mars, under the surface, hundreds of feet, there's like little bacteria, like in the dirt. And it's like cool, like we have a lot of bacteria and a lot of dirt around here, It's just kind of funny. I mean, yeah, I totally ran, the significance of it, but yeah, so we don't mean that by inhabited. So it has a moon. Earth and Mars both have moons. Mars has 2 moons. It's the 2 kind of demonic sounding things that we used in the prompts of last week, Phobos and Deimos. Phobos, which are like tear or fear and dread or something. And they are, in Greek mythology, they are the sons of Mars. Mars had 2 sons, and aptly named, those are the moons of Mars. And then none of these things has a ring. And so this is going to be part of our counterexample. So we look at these things and we're like, all right, have we made these 3 premises true? Is it the case that everything is either a G or an E, either smaller than Earth or inhabited? And we're like, yeah, everything. This is all the 4 things, and so we got that one. Now we ask, is it the case that not everything has a moon? And we're like, yeah, there's 2 things that don't have moons, Mercury and Venus don't have moons. Is it the case that everything that is inhabited has a moon? And we're like, yeah, Earth is the only thing that is inhabited and it has a moon. And now we ask, is there something that has rings and is smaller than Earth? And we say no. So the first 3 premises are true, but the conclusion is false. So we just gave a counterexample. So this is our counter model. So on the problem set, at least one of the questions is the same kind of thing. It's like, look at this argument, construct a model that makes the premises true and the conclusion false. And you just punch in numbers in your domain and decide what to put in the extensions of things, and then you get your counterexample. So yeah, you could also, we could change the things we're talking about and have structurally the same counterexample. So that's what, any model you can have with like non-numbers, you could always just use numbers as names of those things. And then you could just say, well, let's just talk about the numbers. And so we could have a domain of 1 through 4, and we could talk about 1, 2, and 4, and the number 3 would have this property E, whatever it is, and these 3 things have property G, whatever G is. 3 and 4 would have the property B, whatever B is. And there'd still be nothing that's an H, and these 3 premises would be true in this model, and the conclusion would be false. And so you don't, it's like in Carnap with coming up with these examples, I don't even really think about the predicates as meaning anything. It's all that really matters is you're taking numbers and you're putting them in the extensions of some predicates such that certain claims come out true and other claims come out false. And you don't really care, I don't really care what E means. It's like it's just structurally this shows that we don't have a valid argument. You could have, you could come up with something creative, I'm sure, for what, these things could be. All right, so here's a really simple way to counterexample. So often in Carnap, you'll be able to give really minimal examples, like often writing very little stuff, and it will be a model that does what you want it to do. So here we could have a domain of 1 object, just the number 1, and we could say, let's assign 1 to G, and we'll leave the other predicates empty. So the other predicates will have empty extension. So basically what we're saying here in this example is that the extension of E in this model, extension of E, is equal to the empty set. So there's nothing in E, whereas in contrast in the extension of G is a set with one thing in it, namely the number 1. And so we look at our sentences and we're like, okay, is it the case that everything is a G or an E? And we're like, yeah, because there's one thing and that thing is a G. So this one's true. Now we're like, is it the case that not everything is a B? And we're like, yeah, nothing is a B. Now we're like, is it the case that everything is such that if it's an E, then it's a B? And we're like, well, yeah, because there aren't any E's. So trivially, everything that is an E is also a B, because the extension of E is empty. And this, I guess, doesn't even matter, but we can also note the extension of B is empty. But even if the extension of B, had a bunch of stuff in it, this guy would still be trivially true. So basically, remember, the material conditional is such that when the antecedent is false, the if-then statement is trivially true. So if you just focus on the EX, VX part, and you say, okay, put in anything for X, there's only one thing to put in, put in E1, you see, oh, E1 is false, because 1 is not in the extension of E. And so here, this antecedent is false, and so the conditional is true. This is basically what we're doing when we interpret this stuff. And we're just saying that this thing, if EX, then VX, we're saying this is true for everything in the domain, and we verify that just by checking the one thing, because there's only one thing in our domain. We'll give more examples of this. But this is a really important thing to keep in mind, that when you see a if-then sentence in these models, you should immediately think to yourself, okay, easy way to do this problem might be a trivial case, a case where you're relying on the strangeness of the material conditional. Cool. And the conclusion is false because there is nothing in this domain that is an H. So, any questions about this? All right, so some pictures. Yeah, you can draw pictures if you want. Honestly, like most of the examples are so chill, you probably won't have to draw pictures. But it's a nice technique, and it can make things more visual. So if you get stumped on a problem in Carnap, start trying to draw a picture to figure out what's going on. So if we have 3 things in our domain, 1, 2, 3, then when we assign 1 and 2 to P, we're basically saying there's a P circle. And 1 and 2 are in the P circle. And with Q, we're saying 2 and 3 are in the Q circle. And so the picture makes manifest that 2 is something that is both the P and the Q. Because 2 is lying in the intersection of the P and the Q. And to show that R has empty extension, there's no R circle at all. R is just chilling empty. R is how we feel on a Friday night when we're all done. That's right. Did any of us feel that way this week? Maybe. This is logic test. Until we put our feelings into the domain of discourse, we're not able to talk about them. All right. So I guess this is another counter model to the same argument. So here we have 1 and 2 in our domain. We put 1 in G, and we put E, V, and H. We put 2 into E, V, and H. So E, V, and H have the same extension in this model. And I guess, yeah, so we look at, the truth values of these things. Is everything a G or an E? We're like, yeah, because everything's either over here or over there. Is it the case that not everything's a V? We're like, yeah, because here's something that is not a V. It's not in the V circle. Is it the case that everything is such that if it's an E, then it's a V? Yeah, because E and V have exactly the same extension. So only the V's are E's, equivalently anything that's a V is an E. And then we ask, is there something that's an H and a G? No, because there's one thing that's an H, namely 2, but 2 is not a G. So the conclusion is false. So this is also a counter model. Pictures. So when it comes to two-place predicates or multi-place predicates, then you can start drawing little arrows can sometimes be helpful between things. So basically, when we make this claim that Chad is shorter than me, we basically have our little Chad dot, and we have a little H dot, and we're saying there's a directed relationship from Chad to H. And what we're saying is, what's not the case is that there's no dot from H to C because I'm not shorter than Chad. So if you wouldn't draw that, we're just saying Chad's shorter than H. So it's a directed thing. And that's what the arrow's picking out. So here, if our relationship A, so A might be something like, I don't know, loves, So here we're saying one loves itself. So from 1 to 1, there's an arrow. 1 loves itself. 2 does not love itself in this model because there's no arrow from 2 to 2. But 1 loves 2, and 2 loves 3, and 1 also loves 3. And so that's what this extension of the predicate A is saying. And we've depicted it with this picture, and we've also said that A is a name of the object 1 in this model. So A, loves itself, where that just means 1 loves itself. Any questions about this picture method? So this sort of thing would be useful if you have a question that has one or more multi-place predicates and you're hung up on how to get stuff to work out. You can start drawing pictures like this. Cool. All right, so basically we've been talking intuitively about the truth of the sentences of QL, and now we're going to give a somewhat more precise characterization, not like super anal. Over the summer I rewrote one section of the book on satisfaction semantics where I made it really anal. So if you want a very precise, if you want to be satisfied, really get to the bottom of things, you can read the satisfaction semantics section, which was something I did in August, and that's really where I was questioning the meaning of my life at that point, writing that. But we did it, and it's there, and it's really, I think, just not necessary to understand in any deep way. It's like we're using a quasi-heuristic approach to understanding the truth conditions of these things, and it's going to be fine. We'll be able to solve all these problems, and you won't need to understand this arcane notation in tedious way of thinking, tedious but precise way of thinking. So, but it's in the book. If you want to read about it, you can knock your socks off. So when we try to figure out whether or not a sentence of QL is true, but remember the sentences are a subset of the well-formed formula. The sentences are the things that have a truth value within an interpretation. So an atomic sentence is true just in case the reference of the constants are in the extension of that predicate. So if you have a constant A, then the atomic sentence PA is true if and only if whatever A refers to, so here A is referring to R, if R is in the extension of P, then this thing is true. So it's just like saying, when we had this sentence, BH, so if we ask, in a model, is BH true, we're just saying, okay, H has to refer to something. H is a name, it's a constant. In our model that we're talking about, H refers to me. And so we're just asking, is Hunt, this thing, this object, is Hunt in the extension of the predicate beautiful? And if Hunt is, then this is true. If Hunt is not, then I go home and I crack that into myself in my cereal bowl. I don't eat cereal anymore. I stopped doing that. I don't know. I don't think that's relevant to anything here. If you're, a fan of cereal, then that's great. I'm happy for you. So RAB, this is a relation R. This is true if and only if this ordered pair R, P is in the extension of R, where again, R is whatever A refers to, and P is whatever B refers to. So if you're just like with our little Chad chalk thing, if you're confronted with a QL sentence, this would be, we'll use Chad to write about Chad. Chad likes to write about Chad. So if we have SCH, and you're asked, is this thing true? You're basically just, you're asking, all right, is it the case that whatever C refers to is shorter than whatever H refers to? You're just asking, is C comma H in the extension of S? And if it is, then in that interpretation, this thing's true. If it's not, then it's false. So you can see that the truth of QL sentences is completely dependent on the interpretation. You could make these things true in one interpretation, and they'd be false in some other interpretation. The only things that are true in every interpretation of QL are the tautologies. And there are tautologies. And the only things that are false in every interpretation are the contradictions. But this SCH, this is a contingent sentence. There are some interpretations where SCH is true, namely this one, and there are other interpretations where SCH is false. All right, and then we get into stuff, it's really obvious. Not A is true if and only if A is false, where A, here is not necessarily a sentence of SL. A could be a sentence of QL, quantifier logic. A or B is true if and only if at least one of them is true, one of the disjuncts, and B is true if only both the conjuncts are true. The conditional, again, always have this memorized. A lot of the problems hinge on these truth conditions of the conditional. If A then B is true, if and only if A is false or B is true. And so in particular, this conditional is true whenever the antecedent is false. And remember, the antecedent here could be a really complex thing. This antecedent could be like, universal X, universal Y, universal Z, blah, 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 blah. And then close that all down and do a conditional and then have the B. And so if you had that, giant sentence and you want to make it true, typically the easiest thing to do is just build an interpretation that makes the antecedent false. Because then, it'll be trivially true. Cool. And then, and I guess we have our biconditional as well. That's on the slide. Biconditional. All right, so these ones, we have to say something about, and this is where we could get really tedious, but we won't. We'll just have this, quasi heuristic understanding. So when we say there is something that's an X, such that property AX, really A is any sentence here, sentence, or any well-formed formula that has X occurring. This existential thing is true if and only if AX is satisfied by at least one object in the domain. And satisfied here really just means when you substitute in that at least one object in the domain, this thing, AX, with that substitution, ends up being true. So you can imagine how spelling that out precisely, what I just said, would be kind of tedious. It is. So we won't do that. But heuristically, what we're saying is something like this. Some object O satisfies AX if and only if AC is true in an interpretation just like our interpretation I, but one where we've replaced whatever the reference of C is with O. So you had some interpretation where C might refer to something. Now we're like, okay, we're going to take that interpretation, we're going to make C refer to O. O will be the referent of C. And so O will satisfy AX if and only if basically AC is true when C is referring to O. So, to try to make this concrete, because it sounds like a very confusing idea, but it's always, in every individual case, it's easy. So it's like, don't get hung up on the precise way of putting it. You just want to be able to think through cases. So if we had a sentence, there is something X BX, and we wanted to know, is this true in an interpretation? We're really just asking, is there at least one thing in your domain of discourse that is in the extension of B? That's all we're asking. And in this case, where our domain of discourse, our running example is the people in this room plus Chad, our beloved piece of chalk, we're like, yeah, there are tons of people who are beautiful. We're not sure about Chad, but each one of us is beautiful at least. And so, there's of course at least one thing that makes this true, at least me. So here, our O is H. So we're basically like, BH. So because BH is true, the existential, there's at least one thing that is a B is also true in this model. So that's all this is saying. If instead we were in a scenario where our domain of discourse contained only ugly things, so take your least favorite kind of art. I despise country music. And now, for some of you, my teaching evaluations have just gone way down. I've marked myself as an enemy. So in a really extreme mood, I will say, there are no beautiful country music songs. And obviously, that's false. There are some beautiful country music songs. But I'm being bold. I'm saying a generic. Country music sucks. It's ugly. Country music is gross. If that's our interpretation, then this existential would be false. Because I'm saying in this model, in my interpretation of country music, there aren't any beautiful ones. And so there's nothing to satisfy this existential one. So, any questions about that? Hopefully intuitive. So if universal, we're basically just asking, is it the case that every object in the domain satisfies the thing that's being universally quantified? So if we're looking at the sentence, everybody or everything is beautiful, and we want to know, is this true? We're just asking the following: is everything in your domain of discourse in the extension of B? So B, some extension of B, there's some set of things in it. We're at least saying, all of us. And if we just did all of us, but not Chad, sorry Chad, Chad is kind of an ugly piece of chalk. So Chad's not in the extension, then for all x, dx would be false in this interpretation, because there's at least one thing that's not beautiful, namely Chad. So that's our, so these are, the two things we're adding to recursively get at the truth conditions for every sentence of QL. Or the sentences are the things that, are true or false. Any questions about this stuff? Cool. All right. So I guess, to give some concrete examples. So we say there is something such that AX is true and BX is true of it. It's true if and only if there's some object that satisfies AX and BX. So some object O satisfies AX and BX if and only if it satisfies both AX and BX. Likewise, if we're saying every A is a B, then this is true if and only if every object that satisfies, true if and only if every object satisfies if AX then BX. Where again, this A is a meta-language variable, this script B is a meta-language variable. Script A and script B, they could be any well-formed formula of QL that has an X appearing in it. So these statements are true, for these arbitrary meta-language things. But it's easiest to think about A and B as being predicates. Then it's like, really clear what's going on. And so now we're like, all right, what does it take to satisfy this conditional if AX and BX? Well, thanks to our conditional properties, if O does not satisfy the antecedent, then this conditional is basically true. If O satisfies the consequent, then no matter what's going on in the antecedent, this thing has to be true. So remember, the conditional is true just in case the antecedent is false or the consequent is true. So another way to put it, it's false, the conditional is false, only in the case where the antecedent is true and the consequence is false. That's the one case where you have a counterexample to the conditional. So, and you want to remember that too, in case your job is to construct an interpretation that makes a thing with the conditional in it false. Because then you're thinking, oh, to make a conditional false, I need a counterexample. Counterexample is true antecedent and a false consequent. So basically, if we had some predicate, for all f, so x will do, for all y, we'll do, for all y, beautiful. So basically, we want to know, is it the case that, I guess, yeah, so, because this would be an unbound guy. Yeah, we just think of symbols then. So, let S now be some predicate like shorter than Chad. And we want to know, is it the case that everything is, yeah, it's a kind of confusing one to say. Is it the case that for all things, if it's shorter than Chad, then there's something that's beautiful? And if you wanted to make this vacuously true, then you could just have the extension of S be such that none of the Y's are in the extension of S. Just have the extension of S be empty. If the extension of S is empty, then this antecedent will be false for anything that you put into the Y position. And so then this whole statement would be trivially true. Okay. So now we go through some pictures. Actually, maybe, I feel like let's jump to Carnap and do some Carnap examples. And then we can pick up the pictures on Wednesday, I think. And that would be good refresher anyway. So let me pull up Mr. Carnap stuff. Somewhere in we need some active learning. All right, so practice problems. So if you have your laptop, you can go to the practice problems. It should be linked on Canvas. So on the Canvas homepage, module 9, you should be able to get to practice problems. And we're going to do some that are at the end of this practice problem document. So at the very bottom, there are examples from week 9 lecture. That's where we are right now. We are week 9 lecture. So these examples will be listed in the slides as well, at least these 4. So in the first one, our goal is to show that these 2 sentences are not equivalent. So we have one universally quantified sentence, everything is such that either it's an A or it's a B, and we have another sentence which is a disjunction of 2 universals. This one is saying everything is an A or everything is a B. And the goal is to show that these are not equivalent, and to do that, you just need to construct a model that makes one true and the other false. So I'll let you guys think through this one. Does anybody need scrap paper now with a laptop? No, looks like you guys are all good. Cool. You guys came to play. Oh yeah, and vote. Vote is registered, and proof. I made good on my promise. I changed my voting thing. This is not lying to you guys. I would have paid you the money if I'd screwed up. So I'm a man of my word. It's like one thing you might ask is, does one of these sentences entail the other? Because if one of them entails the other, then whenever that first sentence is true, the other one would have to be true. So that would force your hand. Basically, like you need to make one true and the other one false, and one of them entails the other. Well, you can't, in order to solve the problem, you can't make true the one that entails the other. Then, it would never work. So in this case, one thing we do notice is that this second sentence entails the first one. So whenever it's true that everything's an A or everything's a B, well then of course everything is either an A or B. Because for instance, imagine everything was an A, well then everything would be either an A or B, or imagine everything was a B, then again, everything would be either an A or B. So the kind of argument I just ran through, this is the sort of thing we'll probably talk about more on Wednesday, and then we can use this example, where I just gave a proof. I gave a proof that the second sentence entails the first, obviously not vice versa, proving that's a problem. And the proof was just an argument by cases. I was just like, consider an interpretation that makes this sentence true, then it has to make true, this disjunction or this one. If it makes true this disjunction, then this sentence is true. If it makes true this disjunct, then again, this sentence is true. Those are the only possibilities, and so second sentence tells the first. So clearly, in order to solve this problem, we're going to have to choose a model that makes the first sentence true and the second sentence false. So any proposals for what to put in our domain? Do we need to expand the domain? Could we do this just with 0? No. You can't do this one with one thing. We're going to need at least one other thing. So we add 1, and now, you just have to assign some stuff. And this can be, pretty arbitrary. Let's make 0 an A, and we'll make 1 a B. And now we ask ourselves, okay, had we made the first thing true, we're like, yeah, everything is either an A or B. There's two things, and 0 is an A, and so for 0, the sentence is true. And then for 1, the next thing, this thing's true, B1 is true. So this whole disjunction is true. And so remember, what does it take for the universal to be true? For the universal to be true, the thing that it's quantifying over has to be satisfied by every element of the domain. And we just went through cases. There are 2 elements in our domain. We showed that AX or BX is satisfied by 0, and that AX or BX is satisfied by 1, and so the universal is true, because everything in the domain satisfies it. Is that clear, what I just said? That was cool. So that's why, again, that's the intuitive way to understand it. That's natural to say, much better than the thing I wrote over the summer. Basically no reason, because it's pedagogically atrocious. But precise. And it has some funny lines in it. As every week I don't always get to reread the chapter actually. And some weeks I do manage to reread the chapter, and I notice the random sentences that I throw in and shit. It really makes me sound like, man, I must have gone through some rough times over the summer, and I was. Well, we might talk about that. We might talk about that at one point. If I ever need to give you guys a motivational speech, I'll tell you about my summer. Well, man, that'll be something. That's a reason to come to class. There'll be one day where I tell the story properly. You don't know what day it's going to be. But whoa, man, that's something. All right, and then we just asked, have we made this thing false? And we're like, yeah, because it's not the case that everything's an A. 1 is not an A. And it's also not the case that everything is a B, because 0 is not a B. And so we've done what we wanted to do, and then we can check it, and turn it as a success, and turn this green. So basically, for all of the homework problems, you guys just get to check them all, and you get to verify that you got a correct answer. And they all have checking enabled, and the reason for that, which I'm not writing publicly, is I'm going on a trip this week. I'm going to Pittsburgh for a conference, and I really don't think I'd be able to efficiently grade all these problems anyway. So it's basically, you guys get to, basically guarantee you get 100. There's 20 questions, and you got to solve 17. You can try, as many things as you want. Most of them aren't hard. There's maybe 2 or 3 that require some thought, but nothing insane. I mean, it's if you know what you're doing, you could probably solve the 17 problems in 30 minutes, probably under an hour if you like. But take advantage of it to do practice. Don't, because you really can with some of them. As I know in the problem set, you could just try out random shit and eventually it would work, but you're not really going to develop an understanding of what's going on. So it's the goal is to view, they start off really easy and then they get a little bit harder. The goal is really understand the initial ones and then you should feel like you could handle, any sentence, no matter how complicated, it was. Cool. All right, let's do another. Show that the sentences are jointly satisfiable. All right, so our goal is to construct a model that makes both these sentences true. I'll let you guys think about this one. Alright, so this problem, we see these conditionals, and we're immediately thinking to ourselves, there's going to be a really trivial thing. And this is what I mean by, you just check this, for every one, you just go, hey, what if it works, right away? And you're like, yeah, it does, I didn't have to do anything. But you want to understand, why this is success. So we notice, well, if nothing is in the extension of A, then, we got to go through, before all, you got to plug in everything in the domain. Here we have one thing, so we're going to plug in 0. We're going to ask, is A0 true? No, A0 is false because 0 is not in the domain of A. And so this conditional is true, and so 0 satisfies this universal claim. And 0 is the only thing, so this universal claim is true. Likewise, we go to the next one. Oh yeah, this universal, for it to be true, it has to be satisfied by everything in the domain. We check in on 0, and we're still like 0 is not an A, and so this conditional is true. And this, a good example of you can play around with this to get other models that satisfy it. Like what if we did add in 1 and 2, and we made something B? Well, as long as we leave A extensionless, this thing will continue to be true. It looks like I screwed up our syntax here. Oh, okay. I think it gets kind of finicky with spaces. So here after 2, I have an extra space, and that gives you a little warning sign. So this honestly is another reason just to give you guys auto checker on this stuff, because it is a little finicky. And really one of the main rationales is, there's an infinite number of models you could come up with. And many of you are so creative, and at least one student in class really likes to make everything like literally as long as possible. We're talking like some of the derivations that could have been done in like 8 lines. These were like 28-line derivations, and they worked. But you're just like, what's going on? So there's some paranoid fear I have. If I made this due Friday night, Friday night I'm gonna be partying. Saturday night I'm gonna be partying. So I wouldn't really grade this stuff, until Sunday anyway. So that seems cruel to make it due. And then, I could get back Sunday night, and I could be confronted with people who, have clearly, this is like their only class or something. What if somebody wrote like a model that had like, they went to like 100 or something? And you could do that in this. And what if it was wrong, but it was almost right? And then I was like, I need to discern how close they were to it being correct. It sounds like a nightmare. So you guys can experiment all you want, and Carnap will tell you, if it's right or not. And so, clearly in this case, like, to make it more interesting, you'd want to try to add in some things for A's, but then you would see as soon, if you made A true for something, so if you did assign something to A, well then A would be true for 0, and here, this first one would still be okay, because 0 is not a B. But then this second one would be false, because this is saying not B0 is true, because 0 is not a B. And so it would be false then for everything. If it's an A, then it's not a B. And so really what you notice in this question is that the only way to satisfy these sentences is for the extension of A to be empty. And it's like, this is the kind of thing that you want to be able to understand what the sentences mean so well that you could reason through the argument that we just gave. Not merely that we, figured out how to get a little green check mark, but that we understood, in fact, I had to make A empty. There'd be no way to satisfy, no way to jointly satisfy these sentences if I put something in the extension of A. Cool. All right, so this is a good example too. Show that the argument is invalid. So you have to make the first two premises true, and you have to make the conclusion false. This one immediately looks a lot more complicated, partly because we have a constant running around. So we have a constant with a name, so you have to make a choice about what you want the letter B to refer to. So to get that in numbers, the numbers are objects, things. We're all Platonists here. Or not really, I'm not. On Friday, I was accused of being a Platonist, and it really got under my skin. I got in this argument. So there are people who are just like, they take things too personally in a way, and they get more interested in like just winning an argument than like really like coming to a view. And I was genuinely trying to understand this person's philosophy of math, and they were basically saying that part of the meaning of 2 + 2 is equal to 4 is people. And I was like, do you really mean that? Do you really mean that part of the meaning of 2 + 2 is equal to 4 is people? And their claim was, well, yeah, we wouldn't have, unless there were people, there wouldn't be sentences. So clearly, like, when you say 2 + 2 is equal to 4, you have to implicitly be referencing people, because the people are needed for sentences. And I was like, well, people are a precondition for language. Like, yeah, you couldn't have language without agents, but we're talking about, the meaning of 2 + 2 is equal to 4. Is there anything in 2 + 2 is equal to 4 that refers to people? So we got in a big argument, and this person accused me of being a Platonist. I'm not a Platonist, and I got pretty upset. But I didn't say anything mean to them, but they were really mean to me, and it hurt my feelings. When someone's really coming at you, they're like, your view's dumb, and this doesn't make any sense, and you're just like, I just had to take it right, because you can't do it ad hominem in an argument. Even if somebody is coming at you with ad hominem, it's just not appropriate. But basically here we sound like Platonists, but we're not necessarily Platonists, but we are talking about numbers as objects. You might, wonder, like, what does that really mean? Like, say that a number's an object. But clearly, it works well enough for us to get our little green check marks, our little rewards and stuff, right? So. All right, so yeah, I'll give you guys some time to think about this one, which is hopefully more interesting than the previous one. So yeah, one question you might have is just like, what's the strategy for approaching these? Like, you have to make 2 of these sentences true, one of them's got to be false. What's like the way to go about it? My tip to you guys is start with the existentials, because the existentials are more controlled. To make an existential true or false, you only really have to focus on often one thing. Because to make an existential false, you basically just need to make sure that, well, now it's tricky. So false existential is kind of the universal. But at least when you're making existential true, you just need one thing that makes it true. So if I'm like reasoning through this problem, I might think to myself, I know I need to make the conclusion false. So every time I add something, I'm going to make sure that what I add doesn't accidentally make the conclusion true. So if If I accidentally make the conclusion true, I've screwed up. So what's a way to make the conclusion false? Let there be something that is an A. So the conclusion is saying there is an X such that it's not an A, and if I want to make this false, I want there to be something that is an A and nothing that is not an A. So as soon as I add in something into the domain, like if I added 1, and if I didn't put 1 in the A thing, then this conjunct would become true. And now there'd be, you're getting closer to the possibility of the conclusion being true, and I don't want that. So I want to make sure, that anything I add in, if I can, I'll just make sure that whatever I add in is an A, because then it will make this conjunct false. So, but I don't, so far I'm just chilling with 0. I'm going to see how far I can get with 0. I'm going to see how far I can make it before I have to add something, if I have to add something. So at this point, the conclusion is false. And now I look at my existential, because that's easier to handle than the universal. And I need to make this true. So this thing's saying there is something that's a B, and there's something that bears relation C to B, whatever B is. Well, here we have B is 0. Let's see if we can get by with that. So I need something to be a capital B. So I still only have 0, so I'll make 0 that and see if we can do the work. And I need something to bear relation C to B. And so here I'll say, let's let 0 bear relation C to B, where lowercase b just is 0. And so now I've made the second premise true, and the conclusion is still false, because this, here it's not the case that there's anything that's not an A. Everything in here is an A. So this guy is still false. And now I ask, okay, I need to make my first premise true. I need to be the case that everything is such that if it's not an A, then it's a B. Well, here we're like, there is nothing that is not an A. Everything in my domain is an A. And so this antecedent is false for everything in my domain, and so this will be trivially true. So I think this should work. And then we see, yeah, cool. So we did it just with 0. There's another way you could rush into these problems where you could just be like, yeah, let's just like throw in some stuff, let's like do 1, 2, and like 1, 2, and 3, or like 0, 1, and 2, because that sounds fun. And then you could just start like, yeah, let's make, like this thing true, and let's start putting in a bunch of stuff in here, and it is more fun in a way, but it can also really make a mess. So one way to approach this stuff is just to say, like, basically don't add in something to the domain until you're confident you need to add in something new to the domain. Because every time you add something to the domain, it could break some other sentence, because it could break any universal sentence, because the universals are true relative to everything that satisfies them. So. Cool, all right, and I guess, yeah, we'll do these other examples on Wednesday. We might do some homework problems on Wednesday. I'll take a look again at like which ones seem tricky. I think it really was only like 2 or 3 where I was like, okay, must think a bit. It should be pretty straightforward. Like these, I feel like this example we did is in some ways probably more complicated than most of the homework problems. And it's still not really that bad. So you guys should be pushing. Any questions before we adjourn? Do you guys have concrete plans to get to the polls tomorrow? For anybody, you'd have to be registered in Massachusetts, right? That's what. Yeah, it's like, how many of you are registered to vote in Massachusetts? Just out of curiosity. Nobody. Yeah, because the natural thing would just be registered, wherever you're from, right? Okay. Are any of you guys from Massachusetts? Yeah. None of us are massholes here. Oh wait, does anybody need their midterm back? Henry, I still have yours, right? Does anybody else want their... I meant to do this on Wednesday and I forgot. Anybody else still need their midterm back? More. Morning, good morning. hopefully today's lecture will be a brief distraction from updating the New York Times election statistics stuff, which you should not be doing. If you're doing that, then I tell you as somebody with past experience, it's not worth it. It's not going to make you feel better about it. You know, the thing to do is to have a categorical prohibition on it. Just never do it. And then when everything shakes out, you'll find out. You know, you'll learn. You know, all in good time. You know, by the end of the week, maybe next week. And you can do what I'm doing. If you really want to know, you can ask somebody to check for you. You guys have any questions before we get started? Is the homework thing clear? How you don't have to do all 20 questions, you just have to do 17. And you have auto checker on all of them. So before you submit one, you know, click check. If it's green, then click submit. Don't forget to click submit. Cool. So we're going to start with some pretty pictures on stuff that, for the most part, is pretty clear, but you know, it could be helpful conceptually to have these pictures. If you're trying to make an existential claim with a conjunction true, you just need there to be some overlap between A and B. And so I guess there's a sense in which there's 4 ways. Yeah, what's up, Manny? How's it going? There are 4 ways that you could do this graphically. So you could, you know, have them overlap. You could have them be equal to each other. Or you could have B be entirely contained in the A's. So this would be saying every B is an A. Then of course it would be true that there's something that's an A and a B. Or you could have every A be a B. And then again it'd be true that there's something that's negative. And these same 4 situations are exactly what goes on to make no A's or B's false. So, yeah. Okay. So now if we have this thing, it's not the case that there's something that is an A and a B. We're thinking these 2 things have to be disjoint from each other. It's not the case there's something that's an A and a B. Alternatively, you could have one of them be the empty set. So you could have there just be nothing in one of them. And then again, it'd be true that it's not the case that there's something that is an A and a B. And you know, it's often helpful to push the negation through and just think about what would the equivalent universal sentence be. So we have, it's not the case there's something that's an AX and a BX. This is equivalent to all the X's are either not an A or not a B. And you know, you might find that easier to hold in the mind's eye. It's basically what we're saying here. All the A's are either, everything is either not an A or not a B. So, and yeah, for no A's or B's, I guess you could also think about this as saying for all X, if something is an A, then it is not a B. That's the same as saying no A's or B's, and this just comes from the truth conditions on the conditional. So remember, conditional is just saying either not the antecedent or the consequent. This is not the antecedent, not AX, and this is the consequent. So these 2 things are equivalent. All right, so then we get A be empty, we get B be empty, or we could have them both be empty, which is how we might be feeling looking at the New York Times election statistics. What is A and what is B in this case? I don't know. Joy and hope. It's not the case that there is anything that is joyful and hopeful. All right, so we could make all A's or B's true. And so here, you're really just saying that the thing that's in the antecedent is contained within the thing in the consequent. So you're saying if something is an A, then it's a B. And here, you know, you kind of maybe at this point, you know, at long last, we gain some motivation for why we chose to use the superset symbol for horseshoe. You really can think about the set A as being contained in the set B. So hey, that's kind of a cool kind of a cool mnemonic, right? Maybe somebody was really thinking hard when they decided to use this symbol, not me. You know, and I can say that truly because I've never actually realized this before. It's just at this moment when we were talking about these pictures that I was like, oh shit, actually, you know, there's a good mnemonic there. So, because sometimes, honestly, sometimes when you go to draw these pictures, you do kind of pause and you're like, shit, which one's the big one? You know, which is the bigger symbol? Well, hey, the notation's telling you that the antecedent is contained within the consequent. And so that's pretty cool. All right, and so yes, same situations would make only B's or A's true. So remember, the only B is really saying something like, you're an A only if you're a B, and remember, so A only if B, B, which is B if A then B. So only B's or A's, the only B is the thing in the consequent. Remember, the consequent is necessary condition. Yeah, what's up, Don?
Isn't the notation kind of backwards? That's always confused me. The fact that, you know, like
Oh
the
shit,
A's-
you're right, dude. Oh yeah, that's super sick. No, yeah, you're right, because it's I guess what if we have the set, see, this is why I shouldn't say stuff off the cuff. Yeah, no, you're totally right. It is backwards, because yeah, we would say, all right, totally scrap anything about mnemonic here. It totally is backwards, and it's not natural at all. We should have been using this symbol for the if then. Then we have mnemonic. Yeah, you're right, because we say 0, 1 is contained in 0, 1, 2. Yeah. So yeah, no, it is true. When you write this in LaTeX, this is superset. So this is saying, I guess A contains B, so shit. Don't, you know, everything I said about the mnemonic on conditional is false. There is no mnemonic on conditional. Sometimes, you know, the mnemonic I remember for things it's the opposite of what I think it would be. And that sometimes works if you can remember it as a mnemonic. So, all right, well, that's a bummer. Yeah, you know, I feel like maybe Bertrand Russell's behind this. I should know the history, and then it'd be fun. You know, I could blame a historical figure. All right, so only B's or A's. This is just saying B is a necessary condition for being an A. It's just saying, you know, if you're not a B, then you're not an A. If not B, then not A. And so again, this only B thing, this is a confusing one to remember. So probably on the final, there's going to be a question with an only B's thing. So remember how to do this only B's or A's thing. Some A's are not B's would be false in this situation. All right, so we could have them be equal to each other. Or trivial case, you know, which is often really useful for the problems, you could have the thing in the antecedent just have empty extension. So if there's nothing that is an A, then this antecedent will be false for every element in the domain. AX, no matter what you plug in for X, will be false. A conditional is trivially true when the antecedent is false. And so this universal sentence is trivially or vacuously true whenever there's nothing in the A. So you want to remember that too, because that's sometimes really useful for these questions about countermodels. Okay, so if you want to make this thing false, you just need a counterexample. So you need there to be something that's an A that's not a B. So here, this whole region is things that are A's that are not B's. And so, you know, here we made it false that for all X, if it's an A, then it's a B. What it means to make this thing false is just to make the negation true. So we've made true the negation, not the case of everything. X to BX. Then we're just saying there is something X such that not this thing. And when we negate a conditional, we're just negating, you know, the truth condition, which is not A X, or the consequent BX. And then we can use our regular De Morgan's law to push this through. So we're saying there is something that is a counterexample of conditional, namely there's something that is an AX, and it's also not a BX. So that's what we do if we want to make this thing false. We just say, there is something that's a counterexample, there's something that's an A, not B. Any questions about this? Okay. And so, of course, you could have nothing in the B situation. So let's think through this one. So, yeah. So the extension of A has to have something that's not a B. Extension of A has to be something there. But B could be empty. So there's something that's an A and not a B. Okay, yeah, because in this case, all of these things that are A's, they're not in the extension of B, so they're making true, not B. So take something in A, call it little c. Little c is an A, and little c is not in the extension of B, so for little c, not B is true, not BC is true. So this would also make this universal claim false. And we get a B be empty, completely empty. And we would still get this true. The extension of B. Okay, any questions about our pictures? All right, so we're gonna do some philosophy in a way, not really interesting philosophy, not like philosophy of logic or math or anything. We're gonna do some ethics. We're not really gonna do ethics. We're going to take an argument in ethics and put it in the logical form, which is something that you really do. I mean, it is funny, if you're a philosopher, I've thought about it, I'll teach in this class, I use logic a lot. I'm in these reading groups, I'm in these talks, and I really do actually schematize people's arguments to see if when they take themselves to making an inductive argument, they actually are. And so this is basically a little premise form of just some natural prose text from like an intro ethics book. And this is, kind of a powerful thing that you can do if you were reading a speech by a politician and they were making an argument. You now can see, are they making a deductively valid argument? And you could do what we're going to do. Now, of course, often in politics, you're making inductive arguments, and we're not commenting on that. You can't do everything in a semester. So here's premise one. If an action X is morally wrong, then A is blameworthy for freely doing X. Now, of course, we're taking a lot on board with this notion of freedom. Does anybody ever do anything freely? But we're imagining that is the case. Now we say, too, if X is rationally optimal, where this notion of rational optimality is the idea that there's no action which A has reason to think there's more reason for A to do. So right now, if teaching this logic class is rationally optimal for me at the moment, then there's nothing else that I have more reason to do. There are many things I might consider doing, such as taking my phone out of my pocket and checking the New York Times. If I don't do that, in virtue of thinking that I have more reason to do what I'm doing right now, and I feel the way about every other action, I have some reason I could go get a candy bar. I could just be like, yo, peace out, I'm hungry, I'd like to go get a candy bar. If I take myself to have more reasons to be teaching this logic class right now, then that is more rationally optimal. So that's our notion of rational optimality. So it's the thing for which you basically have the most reason to do. And there's nothing else that you have more reason to do than that. So if X is rationally optimal, then A is not blameworthy for freely doing X. So basically the thought is a sufficient condition on not being blamed is that you did the thing that it made the most sense to do. Even if, you think maybe that thing under normal circumstances could sound pretty heinous. So you could imagine being in like a trolley problem case where I pull the lever and I direct the train to run someone over. There's a sense in which I just kill a man. But in a certain situation, that might be the rationally optimal thing to do. I might have the most reason to pull the lever and kill him, then let the train go on and kill 5 people. And so if you thought I satisfied rational optimality in that trolley problem case, you would think I'm not blameworthy. for freely telling someone. It's getting heavy, right? All right, so 3, so this is our conclusion. Therefore, if x is morally wrong, then x is not rationally optimal. So we're basically saying a sufficient condition on being not rationally optimal is being morally wrong. In other words, a necessary condition on being morally wrong is that something's not rationally optimal. Something, basically, if it's rationally optimal, then yeah, it can't be morally wrong. So these are our premises, and again, so these appear just, like regular text, you extract them, and now we can use predicate logic, quantifier logic, to schematize these. So here's premise 1. We have a domain of actions. W is a predicate for moral wrongness, and D is a predicate for blameworthy and freely. So you could split this up into 2 different predicates, but this argument, for whatever reason, blameworthiness and freedom come together in the right way that you can treat as a single predicate, keeps it simpler. Cool. So our goal is to schematize this premise 1. So if an action X is morally wrong, then A is blameworthy for freely doing X. So try to jot this down or think through it in your head how we would schematize this. And if you can't, then you'll be intellectually blameworthy for not paying enough attention in logic class. Does anybody need scrap paper? All right, anybody want to volunteer an answer? What do we think this bad boy is? Brave, so yeah, Manny?
Give it a shot. For all x such that wx, therefore the x.
Cool, yeah, so it's a conditional, I hope, anyway. Let's see, yeah, great. So yeah, so for all the x's, if x is a w, then x is a b. So for everything, if it's morally wrong, then it's blameworthy. So in other words, we're just saying everything that's morally wrong is blameworthy and done freely. Everything that's morally wrong is blameworthy and done freely. Cool, any questions about this one? All right, so then we go to premise 2. If x is rationally optimal, then A is not blameworthy for freely doing x. So try to jot this one down as well. Where now we have a new predicate O, capital O, for x is rationally optimal. Our hope is that there will be some therapeutic feeling of putting arguments into quantifier form. So any stabs on this one? All right, guys, we're gonna make, yeah.
For all x, OX entails not BX.
Yeah. Again, we shouldn't really say entails for the conditional, but it's like I know what you mean. It's like, again, entailment is a very different notion than conditional. But it is hard to say these things verbally, right? So yeah, so for all x, if it's an O, then it's not a B, where B is blameworthy and freely doing. So, cool. So we got that, and then our conclusion, therefore, if x is morally wrong, then x is not rationally optimal. This one's going to have the same form. And so we say, okay, for all x, if x is a W, then it's not the case that x is no. So for all x, if x is a W, then it's not the case that x is no. So now we've schematized the argument. And so now we could ask if this argument is actually deductively valid. We could ask if it's valid in quantifier logic. And so if we didn't have, these universals out here, and if we just had these if-then things, you would see that this is basically a kind of hypothetical syllogism, where you're saying, first, if it's W, then it's B, and then with the second premise, you notice that, so for premise 2, this guy's equivalent to putting the contrapositive in the inside, so contrapositive, if it's a B, then it is not a no. So that is equivalent to premise 2 by the contrapositive of conditional. And so you could just go through and say, okay, if it's a W, then it's a B. If it's a B, then it's not a no. And so if it's a W, then it's not a no. And that would be hypothetical syllogism. And you could show that argument is valid with the truth table or with our natural deduction system or with the tree. But we don't yet have any method for showing the validity of a quantifier logic thing. So next week we're going to have natural deduction for quantifier logic, and then we'll be able to prove that this is a valid argument. The best we can do right now is reason about interpretations, and basically say something like, in any interpretation where this was true, and in any interpretation where the second premise is true, the conclusion will also have to be true. What's up, guys? We're getting a 10 o'clock thriller. Yeah, that's great. The more the merrier. As I said at the beginning, the hope is that this class will be a reprieve from checking our phones for the New York Times election stuff. So, we can distract ourselves for the moment with logic rather than the world beyond these walls. All right. So any questions on the schematization? So this is a valid argument, but we can't yet prove that. So if it was invalid, then we could give a counter model. All right. What else? Yeah. So just translations of these things into how we've been thinking about them. All W's are B's, no O's, RB's. In other words, no B zeros and no W zeros. Oh yeah, so this is maybe one intuitive way that you could see that the argument's valid. This is something we can do at the moment. So basically, if you want to show an argument's invalid, you have to make the conclusion false with the premises being true. So let's imagine to ourselves we were going to make this conclusion false. So the conclusion is saying anything that's a W is not an O. Anything that is morally wrong is not rationally optimal. And so if we were going to make this false, we'd have to make its negation true. So when we negate this thing, so negate all x. If it's a W, then it's not an O. So for those of you who just joined, we've done some negating quantifier things, so we'll just do another example of that. The negation converts the universal into an existential, and then the negation carries through and negates the whole quantified expression. And so what the if then is saying not the antecedent or the consequent, and so basically it's saying don't have a case where the antecedent is true and the consequent is false. So now we're going to negate that, so the negation would just be a case where the antecedent is true and the consequent is false. The consequent is false is not O. And so the negation of our conclusion is there is something that is morally wrong and it's rationally optimal. And so there's something in this overlap. But now we notice that if we've made the conclusion false, and now our next goal is to make the first premise true. To make the first premise true, we just need everything that's a W to be a B. So we just need the whole W circle to be contained in the B circle. And so we do that. But now what we notice is there has to be something that's an O and a B. And so this is going to make the second premise false. So there's going to have to be something that's an O and a B if there is something that is both a W and an O, and if the W circle is contained in the B circle. And so we seemingly can't make the premises true and the conclusion false. Now, you might say, oh, well, this is just one picture, so this isn't really a proof, because there's other pictures you could draw. You have a similar kind of problem like Euclidean geometry, where you're using diagrammatic reasoning. You need to have control over the diagrams. You need to be able to say, there's a sense in which you've drawn every possible diagram. You need to have like a generic version for every one. So in this case, we can draw other pictures, and then you can reason and think, okay, these are really the only possibilities left. You could have the B circle contain everything. You could have the property being morally wrong be identical to the property of doing something in a blameworthy and free manner. Or you could have the property of moral wrongness be equal to the property of rational optimality. That would be a very strange world. If everything that's rationally optimal was also morally wrong, that would be very strange. But again, validity has nothing to do with the meaning of any of the terms. So even though we're interpreting an ethical argument, whether or not this argument is valid is purely a function of the formal structural properties of it. And so you would have to consider all these scenarios. Cool. All right, so I feel like let's do some of the extension stuff on Carnap, and then we'll come back to glosses on our semantic notions. They're basically doing this stuff intuitively anyway. It's more fun to do some practice, right? Let's see if I can find. So I think you guys, you should be able to get to the practice problems on the Canvas page. Should be on the Canvas homepage. So this is week 9 practice problems. We need some active learning, otherwise we're gonna doze off, right? But there's a risk now that we're on the internet. We're only a few clicks away from the New York Times. So, is the rationally optimal thing for me to do to just continue carrying on? Describing models and counter models. I could just click this button. You see, I don't have the New York Times as one of my little things because I'm off that. I'm not doing that shit anymore. So we're clean on the New York Times. I was telling Gerardo at the start of class that at one point in my life, I was so bad that the New York Times election meter, it wasn't updating fast enough for the Georgia Senate race in 2020. So I got the data and I made my own meter so that as the data was coming in, I could update it faster. So if you're addicted to the news, there's hope for you. You can get off the news and you can become a quasi news hermit like me. And I feel a lot better, I swear, compared to how I felt then. All right, so we did 3 of these. We did A, B, and C on Monday. So I guess we can do D. So the goal is to show that the following is not valid. So in other words, it's not a tautology. That's probably a better way to say it. So we just need to show that there's some interpretation that makes this sentence false. So I'll give you guys a minute or 2 to think about this, as I will also think about it. Does anybody need scrap paper? You guys all got computers? Tim, do you need scrap paper? Oh, cool. Put you guys in good attendance pile. I don't have my usual green Sharpie with me, but you could write your name really big, just your first name, and then you can just leave that up at the front at the end of class. So key thing with this one is the main connective is a conditional. So main connective is horseshoe, so the only way for this thing to be false is for the antecedent to be true and the consequent to be false. So before you plunge into doing anything, we have a strategy. We know what to do for this problem. We know we have to make, there is something that A bears, little a bears, big relation A to, true, and we have to make it false if there is something that A is itself. So, and then, then once you've done that, it's like, all right, there's a ton of ways you could do that, but you know what to do and you're not, floating around the dark. So the key thing is always just to assess what the sentence means first, try to get a strategy on how to set it up. So let's add something else to the domain, so that A has something else that it can bear capital relation A to. Maybe we'll talk about capital A as associated, so we can form normal English sentences. So we want little a to associate with something other than itself. So we add in 1 so that we can say that little a, which is 0, associates with 1, and now we've made the antecedent true. There is something x, namely 1, such that little a, which is 0, bears the relation big A to it. Any questions about that? Making the antecedent true. Cool. And then we're like, is the consequent false? It's false, provided there is nothing that bears A to itself, and in here, there's nothing that A is itself. And so we're confident that this is going to work, and we get success. We're like, yeah, green light. And we've just saved American democracy. No, we haven't. So, but so, if you added in something that did associate with itself, so if we added in 1, 1, then Carnap's going to tell us that not all the formulas are false in this model, and that's our goal. And it tells us to take another look at this one sentence, which is not a great hint because it's the only sentence. But the hints honestly are pretty good. And if there's like 5 sentences and you've made 4 of them true, but not one of them, Carnap tells you which one you haven't satisfied, which is pretty cool. This is one of the rare instances where Carnap is actually giving you good hints and not, kind of bullshit. So thanks, Carnap. All right, so we could do E and F. But one thing that occurred to me was we had this brief discussion at the end of class, like maybe last Wednesday, everything runs together, where we were symbolizing this sentence on problem set 8. So it's the last problem, which was if Jupiter has a moon, it has a moon with an atmosphere. And we were debating 2 different schematizations. So remember, we had this predicate M for is a moon, and we had a predicate T for is an atmosphere. We also have orbits, and so technically we need to put orbits in there and say there's something X such that X is a moon and X orbits Jupiter. Let's just leave that aside. So here, if we're thinking about this natural language sentence of Jupiter as a moon, we're going to let M be is a moon of Jupiter, just to simplify things. So the question really is which one of the expressions below has the general form needed to schematize this sentence. And there was a question like, aren't these just equivalent? If I have this one where I have an existential in the antecedent and an existential in the consequent, why can't I just take this existential and pull it out and just have a single existentially quantified expression? Where I'm saying there is something X such that if it's an M, then N and T. And so we had some back and forth about this, and I think Owen said some things very fast that showed that they're not equivalent, and I was kind of fried, and so I was like, Owen, is this good news for me? And he was like, yep. And I was like, great. But now that we're back and we're thinking clearly, we've coded this problem, and so the goal is to show that there must have been a true thing that Owen could have said. I don't remember what Owen said, but he might say the solution. He might have said the solution to this problem. So I'll give you guys, like a minute or two to try to show these are an equivalent. So you have to make one true and the other false. That's the goal. And a single interpretation, and that will show that they really, don't mean the same thing. And often the tricky thing with questions like this can be if one of the sentences entails the other, then clearly if you make that sentence true, the other one will be true. And so sometimes you have to think hard about which one of these do I need to make false and which one do I need to make true? Because sometimes you don't have an arbitrary choice. And I think that's the case in this problem. One of them you have to make false, and the other one you have to make true. Or else it's not going to work. Alright, so much like in the previous problem we did, we see that the first sentence is a conditional. Main connected is an if then, so if we're going to make this thing false, we have to make the antecedent true and the conclusion false. But now we're like, well, what if I wanted to make this one false and this one be true? What would happen then? And here, you can reason heuristically and say, whenever the first sentence is true, the second one's going to be true. So if there is concretely something that's an M, and then this conditional is true, then that thing would all, then you need there to be something that's an M and a T, the consequent of that to be true. Whenever this thing is true, there is something that's an M and a T, well then clearly there's something that's an M, so this is antecedent's true, and then the consequent's true. So even in a totally trivial case where nothing is an M, so let's think about that, nothing's an M, then this antecedent would be false, everything's not an M, and so the conditional would be trivially true. Conditional is always true if the antecedent's false. And then even over here, if there's nothing that's an M, then for everything, really just, for a single one, so put in 0 for MX, and you would get false, because 0 here is not an M, and then this would be a false antecedent, and so this thing would be trivially true. So I think in this case, both of these guys are true. I guess I could have coded something like that, and we click check and we'd get a green thing. The question had been, give an interpretation that makes both these true. But so that's not our goal. So we want to make the first one false and the second one true. So let's start on making the first one false. Basically, we need a counterexample. We need there to be something that is a moon, but that is not, doesn't have an atmosphere. So let's let 0 do that thing. So here, we've made the first sentence true because there is something that is a moon, namely 0, but right now, there's not anything that is a moon and has an atmosphere. So this guy's false. And now we go look at this thing, we think, well, is this one true or false? And right now, this one is also false. So we have to add something, because we want to make this thing true. And now this is the weird part. This is like the strange property of conditionals, and this is why conditionals do not play well with changes of quantifier scope for the most part. A couple exceptions. If we have something in the domain, something called 1, and 1 is not an M, then in virtue of 1 not being an M, this expression will be trivially true. Because plug in 1 for MX, look at M1, M1 is false. Because 1 is not in the extension of M. So we're basically saying the following. In our little M circle, this is M, looks like a moon, we have 0, and we don't have 1 in there. And so when we go to evaluate M applied to 1, we see that this is false. So M1, false is not really the right word. The other, it's like the correct way of putting it is that 1 does not satisfy MX. So apparently one does satisfy. Not mx. And so basically it's making not mx true, it's making mx false. You know, we're talking heuristically here, but it's, you know, it's good enough for our purposes. And so it makes this antecedent false. And so if this antecedent's false, well then the whole conditional is trivially true, trivially satisfied. And so this existential is then true in this interpretation. So basically the weird thing is when you have an existential scoping over an entire conditional, you can make that existential true just in virtue of there being something that doesn't satisfy the antecedent. And that's really weird. So let's see if this works, otherwise I've been spewing a lot of bullshit, right? Yeah, great. Yeah, maybe one should check things before they start talking a lot, right? So it's like, you know, what's going on in this model? We step back and we think about moons and atmospheres. We've said that there is something, you know, we made this one true. We've made it true that there is something such that if it's a moon, then there's a moon and you know, it's a moon and it's an atmosphere. But intuitively, you know, this sentence, if Jupiter has a moon, it has a moon with an atmosphere. Here, you know, there is a moon of Jupiter, but 0 doesn't have an atmosphere. So intuitively, in this model, we made this sentence false, right? If Jupiter has a moon that has a moon with an atmosphere, we've given, you know, this sentence is not true in this model, because here's a moon of Jupiter, but it doesn't have an atmosphere. So what this is telling you is this sentence cannot be the correct translation of our Jupiter sentence, because this sentence is true in this model. This sentence is true, but clearly the sentence we wanted to schematize is false in this model, and so this is your evidence that this is the good one. So that's the, you know, so the homework problem had this as the right answer. This is a much better explanation than whatever I said, you know. It might be just as good as what Owen said. But, you know, so this shows that if you want to schematize this if-then statement, if Jupiter has a moon with an atmosphere, you really do need two separate existentials. So. Yeah, so I mean, my advice to you guys is, when in doubt with quantifiers and conditionals, don't try to play any games with like moving quantifiers around conditionals. So there are cases where you can pull a quantifier across a conditional, but sometimes it flips. Sometimes it has to flip to a universal. So I think we'll probably talk about this next week. I'll see. This is where one really needs the mnemonics to try to remember this stuff. I think it's something like the quantifier commutes when the thing is consequent. Yeah. So I think if you had something like FC, if FC, then all x gx, you could pull this universal across the quantifier. I mean, yeah, across the conditional. And you could have everything is such that if FC, then gx. So you could do that. These guys would be equivalent. And likewise, if you had FD, and then you had there's something that's an HX, you could pull this one across. And there is something X such that if FD, then HX. So this is saying if FD, then there's something that's an H, and this is saying there's something such that if FD, then an H. And these are equivalent. But not if we had this in the antecedent. If we instead had, if there's something that's an H, then FD, you couldn't scope the existential across the whole conditional. You'd actually have to change it to a universal, and that's kind of weird. So this is really the only kind of case where you can pull out the scope of the quantifier across the conditional. And that's what I found. If I were you guys, I'd be like, I just don't really want to take a chance, because, it's just easy to screw up unless you have this stuff written down in front of you with like, a list of equivalencies. Cool. Let's see. All right, survey impact. So there's probably more stuff to talk about in the slides, but I feel like let's do some of the homework problems. At least some of them are interesting, and then if we have more time, we'll go back to the slides. So let's see. I'm going to click this and not type in the New York Times. And get to homework problems. I think the week 10 stuff will probably go live on Friday. I'll probably be at a bar getting drinks at this conference, but this will automatically update, I think. So if that's not the case, get in touch with me. Offset 9. Okay. Cool. So I think 13. So I think 9, 10, 13 are interesting. I think 9's probably chill. So yeah, we'll go. I think we have enough time. So we'll go in order and work through it. We'll work through at least 5. I think 5 that are more interesting. So I think our goal is to make all of these true. Yeah, for each of the following sentences, give an interpretation that shows they're jointly satisfiable. So let's do number 9. We have 3 sentences, and our goal is to have one interpretation that satisfies them all. And obviously, if you do this one, you can move on to 10, probably do 13. We'll see. I know that there's at least 2 other ones that are interesting enough to warrant some class discussion. So yeah, there's always a question of I guess what's the smallest interpretation that you could satisfy? I feel like, a part of me thinks if I want to do one of these problems on an exam, I might say something like that, give me the smallest interpretation, because that's more interesting than like having, all of these possibilities. So in this case, there's a question, can we do this with just one thing in the domain? Remember, the domain can't be empty. There has to be at least one thing in the domain. Can we do this with 0? So we look at our sentences and we know, all right, everything has to be an A or a B. So we're going to have to assign 0 either to A or B. We need there to be something such that if it's an A, then it's not a C. If it's a C, then it's not an A. So basically, when you look at this expression, you're just saying you need something such that it has different membership properties for A and C. So basically, if it's an A, then it's not in C. If it's in C, then it's not an A. That's what this one's saying. And then for everything, if it's an A or B, then it's a C. So here it's like knowing that 0 has to be either a B or an A, I know 0 is going to satisfy this antecedent, and so 0 is going to have to be a C. So I know that right now. 0 is going to have to be a C. And then I know, okay, if I want to try to do it with one thing, then if 0 is a C, then it can't be an A. Well, it has to be an A or B, so 0 has to be B. And so now we think, okay, yeah, we've made them all true, we think. Yeah, and we only had one thing. So this, I think, is the smallest, or the simplest. What is simplicity? That is a grand philosophical question. I'm sure, I'm going to Philosophy of Science conference, and there'll probably be many talks on what is simplicity, and many people will make appeals to simplicity as a theoretical virtue and say, well, this theory is simpler than this other one, so it's more likely to be true. Should we think that simplicity is tracking truth? Hard questions. Really determines a lot of your, mindset on many philosophical issues, and perhaps some, actual methodological issues in science. So cool. So I made this one true. Any questions about this? Obviously, you could do this with more stuff. You could add in, like 1, and then we say, okay, well, 1 has to be an A or a B. Let's make 1 an A. And this existential is still true, because it's true in virtue of a single thing. But now this universal, this has to apply to, anything new you add to the domain. So now I need to make sure that this universal is still true. Here's where Carnap has this cool feature. Let's check it out. So I haven't made the third sentence true, and Carnap says, take another look at the third sentence, which is pretty cool. I'm like, yo, thanks, bro. Thanks, Carnap. Carnap's chilling down under, but he's still, spouting the good wisdom. So I need my new thing 1, which is an A, to also be a C in order to make this third sentence true. So I assign C, and then we're good. Cool. All right, so let's do 10. So CAA, where A is some constant, and then for everything, if X bears C to A, so if X sees A, we might say, then either X is a B, or it's not the case that A sees X. And our goal is to make both of these true. Can we do this one with just 0 again? Okay. So if we let A be 0, as Carnap has suggested, you can make A anything else. You can make like A be 5, right? But then you just have to add 5 to your domain. But so let's stick with A being 0. Now I know that A has to see itself, so I need to put 0 in the extension of C. So remember, for the multi-place predicates, you use less than or greater than signs. You could also use, if you really prefer, you could use a bracket. Carnap takes left and right brackets. But choice is yours. And you always separate these things with commas. And no spaces at the very end, or else Carnap is disgruntled. All right, so we let A see itself, and now we ask about this universal. How do we make it true? For everything, if that thing X sees A, then either it's a B or A doesn't see it. So I have to, just run through everything in the domain. So right now 0 is the only thing. So if 0 sees A, so 0 sees 0, and it does, so this antecedent's true. So I know that I'm going to have to make the consequent true. And this disjunct is false in this case because 0 does see itself. So I know that I have to assign 0 to B. And then this universal is true for everything, and so we're good, and this should work. Yeah. So, clearly, more interesting if you add in more things. So if we add in 1, then we have to check the condition for 1. And, for everything, if that thing sees A, Well, here, 1, we don't put it in the extension of C, 1 doesn't see A. And so this antecedent is made false by it's not satisfied by 1, and so this thing should still be true. But if you did say that 1 was going to see A, so if you're going to have 1, 0, now 1 satisfies the antecedent of this universal, and so you're going to have to do some further stuff to make the consequence satisfied. And so here we're like, oh, okay, automatically we see without doing anything, this should still hold because it is true that A doesn't see 1. We don't have 0, 1. We have 1, 0. So this guy should still be cool. So you can really test your understanding of these sentences by adding stuff into the domain and getting it still to work. All right, so I think 13 is a good one. So we have 5 sentences. Our goal is still to make them all true. So our goal is interpretation that satisfies these 5 sentences. I'm curious what else is on the slides for the that I could have talked about. Oh, I guess it really wasn't that much. We're basically doing it. We're crushing it. This one I had to buckle my brain belt for. I think this was one of the ones that I screwed up the first time I did it because I was, going through the solutions myself. This was one where when I clicked check, Carnap told me I was wrong. And I was like, shit, that's not good. But it's okay, because we have infinite chances, right? If only life could be as generous as this problem. So then, at the end of this week, we could just do it all over again. We could be like, let's have another midterm next Tuesday, That's the people of Great Britain can say, let's do another vote on Brexit, All right, so I think just that have this be a good illustration, we won't fuss around with minimal interpretation. So you could in principle say, hey, can I get this to work if I have some of these A, B's, and C's referring to the same thing? And you probably could do it with 2 things, but let's just have them all name different things, be more concrete. So if I have B name 1 and I have C name 2, I have to add 1 and 2 to my domain. Gotta remember to do that. And now we're like, all right, these are just claims that I make true by putting in relations to C. So I need 0 to C1, so 0, 1, and I need 1 to C2, 1, 2, and I can't let 2 see itself. So in order to make not C, 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 make not C, 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 true, I just don't put in thing. Yeah, I really have to be careful if the not C is right, because there really are certain ways of saying where, it sounds like Nazi, and that's bad. We're against Nazis in this place. where Nazis are terrible. We go back to our moral argument and we think that was not the rationally optimal thing to do, and they did it freely and very blameworthy. So, all right. So we made these true. Now we have an existential, so they're often easier, to get to be true than universals. Universals you typically hold off to the end because you got to run through everything in your domain to check that it's going to work. So we ask, what do we need to do to make this existential true? We need there to be something x such that A sees it. Right now A sees one thing, it sees 1, and we need that thing to not see C. So right now 1 sees C, so 1 does not, here it's like 0 doesn't make this thing true already. What we could do is we could add in 0, comma 0, and now there is something, namely 0, such that 0 sees it, and it doesn't see C. So 0 doesn't bear C to 2, and 0 bears C to this x, namely itself, 0. So now we've made this existential true. And now we look at the universal and we ask, is it the case that everything that A sees, everything that 0 sees, sees itself? 0 sees one thing, 1, and it also sees, this is where you go wrong. It's like, and I think this is where I did go wrong. You might think to yourself, all right, let's do it for 0, and C00 is true, and then C00 is true, and you might stop there and might be like, cool, we're good. You got to check everything in your domain. So check 1. Does 0 see 1? It does, but right now 1 doesn't see itself. So we're going to have to add in 1, comma 1 in there. So if we didn't add in 1, comma 1, Carnap should tell us that we screwed up. Yeah, take another look at the universal. Add in 1, comma 1. And now we check it for 2. So does the universal hold for 2? 0 does not see 2. So C02 is trivially false. False. And so this universal holds is satisfied for 2. And so this should work. Cool. Questions about this one? More exciting problem? In our overly exciting lives? All right, cool. So I know that there's at least 2 other ones that are interesting. Okay, yeah, I think 17. So 17 is a purported argument. There are 3 premises and a conclusion, and our goal is to show this argument is invalid. So remember, that's the only thing we can do with counter models. We can't prove that our argument's valid with these models, but we can give a counter model to validity. So your goal is to give a counterexample to the validity of this argument, namely a scenario where each of these 3 premises is true, but the conclusion is false. So that's the goal. so the initial thing on doing one of these kinds of problems is you know you have to make the conclusion false, and so it often just makes sense to start there and think you're gonna have to hold that in your head the whole time. And so here it can be helpful to explicitly negate the conclusion and have the a universally quantified thing in front of you. So if we negate this existential, remember the negation is going to convert the quantifier to a universal, and then it's going to negate the whole thing in the scope. And so this is going to be the equivalent to, for everything, it's not A at C. So for everything, it bears A to C. So we're basically saying, to make the conclusion false, we need everything to stand in relation A to C. And so this is a serious constraint, because we know whatever we let C be, so let's let C be 1, we know that we need everything to stand in relation A to it. So we need 0 to stand in relation A to 1, and we also need 1 to stand in the relation A to itself, because 1 is the thing. We are all things in the domain, in the universe of discourse. Oh yeah, we have to add 1 to the domain. Cool. So that, at the moment, makes our conclusion false. And then, yeah, it looks like at this point you can look at the third premise and you can push that negation through. So this is not everything bears A to itself, not all x and x is equivalent to, there is something, there's at least one thing, x, such that it is not A itself. And at the moment, this is true in our model because 0 is not A itself. So at the moment, we've also made premise 3 true. So that's good. So premise 2 is an existential as well, and so they're often the next thing to look at. So is there something that A is 1? And we're like, yeah, 0 A is 1, also 1 A is 1. And is there something, could be a possibly different thing, that is a B, and it doesn't, it's not A'd by C. So what's something that's not A'd by 1? Right now 0. So 0 right now is not being hit by 1 in the A relation, but 0 right now is not a B, so let's make 0 a B. And now this second conjunct is true. There is at least one thing that's a B, and it's not A'd by C. So 0 is a B, and 0 is not A'd by 1. And also there's something that A is 1, namely 0, or 1. Cool. So we've made second premise true, so now we go to the universal, we just got to check through everything in the domain, and then make modifications, as necessary. So for all x, if x is something that bears A to B, B is 0, or if it's something that bears A to C, then it's a B. So here, 0 bears A to itself, or no, it doesn't. So this disjunct, first disjunct is not satisfied by 0, but 0 does bear A to C, to 1. So it makes this disjunct true, so it makes the antecedent true, so it would have to make the consequent true. And it does, because 0 is a B. So 0 is good for this one. Now we check 1. So does 1 hit 0? No. Does 1 hit itself? Yeah. So again, 1 makes the antecedent true. So right now, if we didn't do anything else, this wouldn't work, because 1 would be a counterexample to this universal. To prevent that, we have to add 1 into the B bracket. So now at this point, it should work. And because I didn't, I checked all these things, and I've gone through and I haven't added anything new, I don't have to recheck anything. You know, I was confident my universal was true. I didn't add anything new. This was an existential. This was also an existential. If I had added something, I'd have to go back and re-ask, is any universal still true that I needed to be true? Cool. So let's check this. Yeah. All right, so I got that. Cool. Any questions about this one? All right. So yeah, we have enough time for at least one more. So I think 19. 19 is a decent one. Yeah. So 19 is really similar to structurally to this example we've done in class last time about these two for all statements where we had a universal over disjunction versus two disjuncts of the universals. Here we have an existential of a conjunction versus two conjuncts that are both existentials. So the goal is to make one of these true and the other one false. We're not trying to make both these true. We're trying to show that they're not equivalent. So again, you want to ask yourself, does one of these entail the other? Because if one of them entails the other and you make that one true, well then the other one's going to be true as well, so that's not going to work. So we look at these and we notice that whenever the first one is true, there's at least one thing that both A is B and is also A by B. And so if that were the case, well then that one thing, at least one thing, it would make this conjunct true and it would make this conjunct true. So basically the first sentence entails the second. So whenever the first is true, the second is true. So you know, if we're going to show these are inequivalent, we need to make this one false. We need to make the first one false, make the second one true. So basically, we need there to be at least one thing that A is B, and we need there to be a different thing that is A by B, such that in our model there's nothing is the case that it has both these things. So we know we're going to need at least two things, might need more. So let's make this conjunct true. So we need something to bear A to B. Now notice that if we let it be reflexive, if we let something A itself, well then we would immediately make this first thing true. And so that's not going to work. So we can't let anything, or at least you can't let B A itself. What about 1? So if we let 1 A itself, well, this has nothing to do with B, and so this is just irrelevant, because both these things are involving B, and B is 0 in this case. So let's let something hit 0, so let's let 1 hit 0. Now we've made this true. There is something that a is 0. Now we need 0 to a something, and we can't let it a itself, and we can't let it a 1 either, because then 1 would make this thing true. So at this point, it seems we need to introduce a third thing into our domain, and let 0 bear a to that thing. And so now this second conjunct is true. There is at least one thing that b bears a to, namely 2. And this first conjunct is true, but we look at our first sentence and we ask, is there anything that both a is b and is a by b? And no, there isn't. So this should work. Cool. Got it. All right. So yeah, so my hot take is the other problems, at least 12 of the other problems, are really chill. So you guys should be in great shape for this problem set. Should be able to bang this out under an hour. You know what you're doing, hopefully. But yeah, take some time to really test your ability to look at any of these random ass sentences and ask what they mean. Don't just go blindly clicking through and getting little check marks. You wanna use this as an opportunity to deepen your understanding of quantifier logic, because we love quantifier logic. Now we can schematize so much. So I'll see you guys next week. I'll be on email if you have any questions about anything. And yeah, hopefully you guys have a good rest of the week. I gotta get my ass to the airport. And be on the back, so you have everything at the tips of your excited fingers. You're welcome. So yeah, basically today we're going to talk through these 4 new rules that complement our existing 10 rules plus reiteration. So we have 15 rules. And these ones, they look more complicated because we have all these quantifiers and variables running around. But 2 of them are really chill, 1 of them's okay, and then the 4th one is genuinely a bit confusing. And that's the one you're probably most likely to screw up. So before we do that, I guess we didn't quite finish the semantic stuff, so let's just do, and this will kind of be some motivation for what we're doing today. Screen. All right, so just a quick review on the semantic notion, which does kind of motivate why we're going to do a proof system. So remember, if you have a set of sentences P1 through Pn, they semantically entail some sentence Q, provided that there's no interpretation that satisfies all of P1 through Pn, but doesn't satisfy Q. And so you can say some sentence is a validity if it's true in every interpretation, satisfied in every interpretation. You have 2 things that are equivalent if there's no interpretation where they differ in truth value. And to say that a set of sentences are jointly satisfiable, which remember is the same as saying they're consistent, is just to say there's some interpretation that makes them all true. And what we saw with our models is we can do a bunch of things, but not everything we might want to do. So in particular, we can show that an argument's not valid by showing a model that counterchecks the validity. We can show a sentence is not basically a tautology. We can show 2 sentences are not equivalent, and we can show that a set of sentences is satisfiable, i.e. consistent. But with our models, we couldn't show these following 4 things. So we couldn't show that an argument's valid, or that a sentence is a tautology, or that 2 sentences are equivalent, or that a set of sentences are not satisfiable, i.e. inconsistent. So with our proof system, we'll be able to prove that sentences satisfy these 4 properties. Assuming, of course, that we're able to show that our proof system is sound, which is something we'll do after Thanksgiving. So we'll be taking for granted the soundness of our proof system when we make these semantic claims. Yeah?
Do we not use the word tautology for quantifier logic?
I think, no, we should use tautology. I think I was just lazy when I was writing these. Yeah. So I think, yeah, when I go to, now that I say this stuff, I think, yeah, we've been saying tautology the whole time. So, yeah, I should write a sentence that says tautology in QL. So before, yeah, maybe I'll repost these with that definition. But feel free to take a rule sheet, Manny. We got new rules. Cool. So we did these examples, and then the one thing we didn't talk about with semantics is in informal language, you could give a proof. And so let's run through this, and then we'll see the contrast with our formal proof system. So we can, in general, show that an argument is valid because we don't, in general, have a way to inspect all possible interpretations. We saw one example where we had some diagrams, and we could reason diagrammatically, and we could feel comfortable that we had spanned all of logical space, but it's something that we just don't have as much control over, you think. What if I just didn't think of a diagram that's possible? Then, your argument would break down. That would be a failure of rigor. So when we reason informally, we're basically appealing to the truth conditions of these sentences, and we're arguing that if some set of sentences is true in general, then some other sentence would also have to be true. So a really simple example would be the fact that this disjunction, everything's an A or everything's a B, entails the universally quantified sentence for all things, either that thing is an A or that thing is a B. And so to reason through this, you're basically saying something like, consider an arbitrary interpretation that satisfies this disjunction, then show that that interpretation would have to satisfy this universally quantified sentence. And so if you had an interpretation that satisfied this disjunction, well, it'd have to satisfy either the first disjunct or the second disjunct, or both. And so you just do a proof by cases, and you think, well, in the first case, your interpretation satisfies this guy, then everything's an A, and so of course, any instance X will be an A, and so all of those things will satisfy this universally quantified formula. And likewise, in the second case where everything was a B. And so this is our informal argument. And today we'll see how to do a formal argument in our proof system to derive this thing. I don't actually know if we'll run through this today. We have a ton of practice problems doing stuff. I think this is a week where it's kind of inexhaustible, the number of practice problems you can do, because there's just so many sentences in so little time. So, we'll try to do ones that are illuminating. Are there any questions on this kind of style of reasoning? This is the informal stuff, contrasting this with our proof system. All right. So now we are into the proofs. So one other way that you could motivate these quantifier logic proofs is we'd like, especially, to have a way of showing two sentences are equivalent. As I basically just talked about, the models only give us counterexamples to equivalence or validity, and so we're going to extend our natural deduction system. Then we can prove that any sentences that are equivalent are in fact equivalent. And so there would be two ways to do this. You could derive one sentence from the other, or you could show that the biconditional of the two sentences is a tautology. And remember, when you to show something is a tautology in a natural deduction system, the thing to do, does anybody remember the thing to do to show a sentence is a tautology in natural deduction? The key property, the key syntactic property of a tautology.
If you negate it, there's a close tree.
So that would work for trees. In natural deduction, remember, we have these scope lines, and we have things in the assumptions. Things are in the scope of assumptions. So in general, you're starting off with some set of sentences, some set of premises, sentences 1 and 2, and then you go on to derive something. And this thing N down here is still in the scope of 1 and 2, and so this would be basically the claim that P1 and P2, they syntactically entail Q. Remember, for the syntactic notions, we have a singleton sound. So if we wanted to show something as a tautology, this would be just to show we can get Q from no assumptions. And so it'd be a scenario where we have down on line N Q, but we have discharged every assumption. So if we started with an assumption up here on line 1, this would be something we assumed, or some instance of a rule that relies on an assumption. Then we did some stuff, and at the end, we discharged, and we're now not in the scope of any assumptions. And that's what it means to say that this thing is a syntactic tautology, and then if our system is sound, remember we can convert the soundness of our system, we would have semantic entailment, and so this would mean Q is equality. So this is the kind of thing we'll be able to do now with any sentences in our predicate logic. So there's a bunch of equivalences on this slide, and I guess if we're really, killing time this week and want more examples, maybe we'll talk more about this stuff. But it's in the slides kind of for your guys' benefits. So I'll run through this really. Maybe I'll just click through some of these as examples, then we'll get to the rules. So if we have a conjunction of some sentence that basically doesn't have, I guess, free x variable, with a sentence that existential, gx, and it doesn't have a running around, you can pull out the existential to scope over the entire sentence. And basically you're saying A is an F, A is, remember, some constant, somewhat concrete thing. So this is like, Alan is my friend. Alan is my friend, and there is something that is my groupie. That's equivalent to, there is something such that Alan is my friend, and something is my groupie. So, and likewise for universal, and you get the same kinds of rules for disjunction. And remember, conjunction and disjunction, they're symmetric binary connectives. And so you, of course, would also have the same kind of equivalencies if you had the existential as the first conjunct, or the universal as the first conjunct, likewise for the disjuncts. So these are, really easy cases, very natural. Just, it seems the way that, you would think it should be. Conditionals are tricky because conditional is not symmetric. And so you have one direction of this kind of equivalence with the conditional. If you have the quantified expression in the consequent, then the quantifier commutes over the conditional. So your mnemonic here is something like quantifier in the consequent commutes over, consequent commutes over, it's like 2 C's. And so if the quantified sentence is in the consequent, then you can pull out the universal and scope over the whole sentence, but not if you had the existential in the antecedent. Then it would not be equivalent to this thing. And so, we'd have to examine this case separately, the case where we're saying, if there is something that is a G, then Alan is my friend. And we don't have any analogous rules for biconditionals. So in general, if you have a biconditional expression where one of the biconditioned things is a universally quantified sentence, there's nothing generally you can say about pulling out the quantifier for biconditionals. Done. Cool. So we could, maybe at some point we'll talk more about these, what you do in the case where the quantified expression is in the antecedent. It's confusing because basically what happens is when you want to scope over the whole thing, it flips. So the existential becomes a universal. And so this is like a hard thing to remember. And so you probably wouldn't successfully remember this. So if you end up on an exam or something needing to manipulate sentences like this is something you probably want to have handy. If it seems to me like you guys are going to want to have this handy for the final, I'll give you a heads up so you can have this kind of thing on your rule sheet. But yeah, so at some point on Wednesday, if we've gotten through everything, we might try to derive this equivalency to show that these two things are equivalent. And similar, there's a similar rule for universal. If you use universal and antecedent, then when you scope this thing over, it flips to an existential. And so it's kind of counterintuitive. Various ways to motivate this, but you can't argue with it because it's logic. Right? So all right, so let's get to the rules. All right, cool. So basically what we're doing today, this week, the main thing to try to get down and really be proficient with is these 4 new rules. And remember, in our quantifier system, one reason we like this kind of system is for every connective, there's always an introduction rule, a way to introduce that connective, and for every connective there is an elimination rule, a way to eliminate that connective. And so here, in quantifier logic, we've added 2 connectives. Remember, there's a way to think about our existential and our universal. It's basically a kind of unary connective, kind of similar to negation. And so we've added 2 connectives, and so each one of them has to get an intro rule and an elimination rule. And so you just have to get comfortable with these rules. And they're pretty intuitive. I mean, they really do match how we reason naturally about, there at least something is blah, blah, blah claims, and everything is a blah, blah, blah claim. And the only tricky part, really, that's going to throw you is 2 of the rules. So the rule for universal introduction on the bottom left. Oh yeah, Daniel, do you want a rule sheet? Dan, oh, it's going to do. Does anybody else have a rule sheet? This will just be helpful to look at as we go through examples and stuff. So the rule on the bottom left, you'll see it has 2 restrictions on the constant, and so you got to get comfortable with those restrictions. And then the rule on the bottom right has 3 restrictions, although there's a simple mnemonic that's easier to remember. And you'll also notice the rule on the right, existential elimination, it has a subproof. So it involves making an assumption. And so you guys, remember, well, whenever you have the possibility of making assumptions, you have the potential to screw things up way worse, right? So basically the rule that's going to give you the most trouble is the existential elimination rule. There's just the most ways to go wrong on existential elimination. It's a good example of a rule that you're going to think you're following this a lot, and you're not. You're going to be screwing it up. You're going to be looking at these things, you're going to be running through them, and you're going to think, yep, I did that, and so no, actually you did. And so that's, just kind of interesting. So if we get through everything on Wednesday, then on Wednesday we'll talk about the rule-following paradox. Maybe at the end of class today, I'll give you guys the rule-following paradox as a little puzzle that you can think about in your spare time, and then you can see if you can solve the rule-following paradox by Wednesday and give a therapeutic solution. So, hint, you're not going to solve the rule-following paradox, because maybe it's unclear if it's really a paradox. It's at least like a very serious puzzle and a disturbing puzzle if it clicks in. A part of me is kind of bad really to tell to anybody, because if they really understand it before they've resolved it for themselves, it's very disturbing. And you think, well, it's not really nice to go around disturbing people, is it? All right, so we need these rules, and oh yeah, probably in the background, the easiest way to motivate why we're doing this is we just don't have truth tables for quantifier logic. So whereas with sentential logic, you could have said, well, if I'm happy with my mechanical truth table, I'm just going to do that no matter how long it takes. Here, you don't even have recourse to that. So the practical need for something like this is just that much greater. So we want our simple rules. What does simple mean? Great question. We want elegant rules. What does elegant mean? I don't know. Yeah, it's I have a theory of this because I'm a philosopher, but But, it's a fun thing to think, what does it really mean when a mathematician or a physicist says such and such is elegant? And yeah, of course we want them to only give valid arguments, we want them to be sound. Such that when you have, syntactic derivation, you have semantic validity. So in the case of the universally quantified sentence, and I guess this really should be, here we have a clash of variables, this should be a chi symbol, so that's a typo. So for all chi, where chi is a meta-language variable, it's a meta-language variable standing for any variable. Where remember the variables in our predicative logic are the following symbols. So the variables are x, y, z, possibly with subscripts. And so chi is just a meta-language variable. So chi stands for any variable. Stands for arbitrary variable. And remember, the constants ran from A to W. Is that right? Do you guys remember? I know there's different conventions on this. I think we're A through W. But who knows? Maybe I'm wrong and maybe W is a variable. That's all right. So to eliminate the universal, basically, you can write any instance of this sentence. So you can go from the sentence, everything is an A, to AC, where what we've done is we've replaced any instance of the variable chi with a constant C. So here we're using really a script C, and the script C again is a meta-language thing that stands for any constant. So you don't have to write C's, you can write any constant. I guess I really should check that W is a variable. Let me see if I think this is in chapter 4. Sorry, chapter 9. There's a hole in the ground. I feel like, the kinds of people who work at MIT, you think really dangerous to have a hole in the ground, right? And, it's like an electrical thing. Variables. It's chapter 8. Let's see. Okay. Constants. Right. Constants run. Oh wait, no. I changed this. Yeah. This was because I'm trying to follow the logic book right now. So I'm gonna check this out. Why do you guys? Because this kind of thing matters on Carnot. If you try to use W as a constant, it wouldn't work. All right, so in our system, W is a variable as well, and the constants run through V. Right. W is a variable. I wanted you guys to have one more variable than the initial free version of this book. So, cool. All right, so basically, you can go from any universally quantified thing to an instance, and there's different notation for instances. I might put this into the slides in the future, but I think the notation we're using in the book is something like the following. If you have phi, then we write C/X is an instance of a universally quantified sentence, or an existentially one, so for all x. 5, where basically what's going on is you are replacing every instance of the bound variable x in the universal thing with a C. So this little notation here is just saying it's the formula phi with C for every instance of x. C replaces every instance of x in this thing. Cool. So this one's super chill. You do colon, line number, and you write it for all elimination. In Carnot, this will be capital A, capital E. Because remember, you write the for all thing, you start writing a capital A. Cool. And so this is a good rule because the universally quantified thing does semantically entail any of its instances. So, any questions about this? It's going to be, more concrete when we do examples, of course, right now. It's very abstract, it's very schematic because it's a rule schema. All right, so the intro rule is not valid. The easiest one you could think of, if you had some instance AC, you could not in general go to the universally quantified thing for all chi, A of chi. This just doesn't follow semantically. So this C, the script C, is a name for a specific object, and what we need to do in order to universally quantify is we need an arbitrary object. Remember, the way that we normally get to a universal claim is we say something like, consider an arbitrary blah, blah, blah. And then you reason to some claim, and then you say, oh, well, since my thing was arbitrary, the claim holds in general. So we want to model that style of reasoning in our proof system. So if it's the case that A script C is true for whatever C could am, then A of chi would be satisfied by every object, and that just is the truth condition for the universal quantifier. Truth condition is that the formula A of chi is satisfied by everything. No matter what in our domain of discourse we sub in for chi, it satisfies formula A. So, we often do this kind of thing. So if you have the following argument, all heroes admire Greta, and only people who wear capes admire Greta, and then we conclude all heroes wear capes, we can reason in the following way, to prove this. So basically, this is a valid argument. We want to give a proof of this thing. And so what we do is we consider an arbitrary person. So let Carl be any hero. Since all the heroes admire Greta, Carl has to admire Greta. And since only people who wear capes admire Greta, well, Carl has to wear a cape. But Carl's just any hero. So Carl was an arbitrary dude who was a hero. And so we get to conclude all the heroes wear capes. So this is basically what we're going to do in our proof system, this style of reasoning. So what we do basically is, we had the simple rule, which was bad. We're going to have something that looks structurally the same. We're going to avoid the badness of it by having these restrictions, provided that both claims hold. So the key thing to remember is you do end up, having something of this form, but you need the constant C to be special. You need the constant C to be such that it doesn't appear in any premise or assumption that you're in the scope of, basically. So when you have this AC, if you're going to apply this rule, AC can't be in the scope of anything that has that constant C in it, or whatever other constant you're working with. So the other thing that's key is you have to, this A chi, the thing that you're referring to, it has to have every instance of C in AC replaced by chi. So it's not like you could just replace some of the C's with chi's. You'd have to replace all of the C's with the same variable chi, whatever variable chi is. Could be an X, a Y, a Z, W. And so basically, another way of stating that, this is maybe the easier way to remember it, it's the way it's written down your sheet, is you can't have a constant occur in the universally quantified sentence. So there's really just two things you have to remember. You can't have the constant, whichever one you're using, be in an undischarged assumption that this sentence AC is in the scope of. So basically, it's like you can have the constant appear outside, where you're working, but not if this sentence is in the scope of anything, any premise or assumption that has that constant. That's the first thing. And then the second thing is just you can't have the constant appear in the universally quantified sentence. And if you satisfy both those restrictions, then you're good. And this is a sound rule. Questions about this? Also really abstract, will become more clear with examples. Cool. All right. Oh yeah, okay, this is just a simple example, which is probably in Carnap, but we could look at it here structurally to ground what we're saying. So if we wanted to prove that every A is a B, then this is, this is not a tautology. We imagine there's some other stuff going on. But imagine you could get if AC then BC. So basically, assume AC for conditional intro. Now imagine you could do some stuff such that on some later line L you could get BC. Clearly you would need some premises for this. You can't just in general go from AC to BC. You can in general go from AC to DC because that is very important for the history of rock and roll. So this is very different. So now we get if AC then BC. Remember, whenever you cite a subproof, I think our batteries are dying. Oh, goodness. But I have backup batteries. Come prepared to class. But not with Band-Aids. So if any of you cut yourselves by accident, I don't have Band-Aids. I'm sorry for that. Let's see. Oh, yeah, well, I have to replace batteries. Yeah. Maybe I won't. All right, I'll wait for that when we get to the chrono stuff. Until then, I will gesticulate wildly. I know some people have sticks, right? I hope at some point in my life I can have one of those pointer stick things. I feel like that seems kind of fun, and then you seem like an old fogey, right? So clearly we could get if AC then BC from this kind of thing. We'd cite our subproof K-L, and then we would be able to introduce the universal. So we're using this rule for all introduction, capital AI, and you cite the line with the instance, and then you basically replace every instance of the constant C with the variable you're introducing, in this case x, and you just check, okay, is this sentence, the instance, is it in the scope of any sentence that has a C? And at least written here, it's not. We don't exactly know what's up top, but assuming that there's no C's up there, it's fine to have the C's in the subproof. We've discharged the subproof. So those C's aren't messing us up. We just need to be the case that above line K, any premise that this line is in the scope of doesn't have an instance of constant C. And assuming that's good, and then seeing how there's no C's here, this is a legit rule, legit application of this rule. So, cool. All right, so this was our argument with Heroes and Greta, so we can do this on Carnap. So, you guys have your laptops with you or whatever. Get to the Carnap practice problems, which, if you're on the Canvas page, you can click directly on practice problems for week 10. I think they're also linked in the problem set. I was all clever. I set everything up, and then I forgot to hit. You have to hit a green button up here, and I hadn't hit that button. So I was having so much fun at this conference that I really hadn't logged on to my computer at all. So I didn't check this thing until I got back last night, and I was like, oh shit, this was supposed to be, visible, right? I had a great time at this conference. Saw all my philosophy of science friends, and we were partying hard. It was like I was at conference talks from like 9 until 6, and then you're out until pretty late, and then you do it all over again. And it was like, but it was totally. I think the limit of how much philosophical information one can take in a 4-day span. Yeah, but that's what we're doing this for, right? All right. So this is our thing. So PP 10.2. So yeah, I'll let you guys, try to do something on this. Get your hands dirty, and I will, I think, replace the batteries on this. Everything. We have Tritech, Packard. Oh, great. Yeah, I feel like this triple A seems pretty big. A little thicker. Let's see if the skinny triple A's work. Boom. Yeah, it's funny, I think waking up at like 8 a.m. like 4 days in a row has gotten me as close as I've come to being actually alive in this class. Like, most days, I'm trying to be energetic and stuff, but really deep down in my actual psychology, I'm like you guys. I'm like, oh my god, it's my third class. Can't handle this. All right, so yeah, let's make some progress on this. So there's a couple ways to do it. The key proof idea here is just to notice that if you're building up a universal, the way universals come from is from an instance. So the thing to recognize in proof strategy is this last sentence is going to come from something, colon, some line, universal introduction. Well, to apply this rule, you just look at your sheet and you're like, universal introduction, you need an instance. So you're going to have to derive an instance of this thing. So you're going to need some constant for the x. We can use c for our beloved Carl or our beloved Chad. So basically you're confident before you've done anything that the penultimate line is going to be an instance of your universal. So if you don't make that realization, you're going to be stuck basically. So your hand is forced here, and now we're back in sentential logic land. And so here you call upon your facility with sentential natural deduction. You think, oh, how do I get an if-then? You have to build it up. And so now we're confident somewhere in this argument we're going to have a subproof with conditional introduction. So back to your sheet, you have the S&D rules. You're going to have a conditional introduction proof. So that'll be in there. When I have universals, kind of like with conjunctions, remember you could always just strip off the conjuncts and just think, well, I'm going to have these on some line, and then I can appeal to them. I kind of, with the universals, sometimes, at least if there's only one constant you're playing with, I'm like immediately, let's instantiate these universals, and then we'll just have those sentences. So basically, I see everything is such that if it's a hero, then that thing admires Greta. I think we're talking about some arbitrary Chad. Let's just instantiate these. So on line 3, we'll do if HC, so if Chad's a hero, then Chad admires Greta, and we cite the line to the universal, and we write universal elimination. And then same thing for the second premise. It's a little bigger for you guys. So second premise, everybody's such that if they admire Greta, then they wear a cape. We're saying Chad is such that if Chad admires Greta, then Chad wears a cape. 2A. So you see how that rule is really easy, universal elimination. And the key thing is just, you have to put in Chad for every instance of X. So there's an X there and X there, so they have to become the same constant, since they're bound by the same variable, same universal quantifier. So now we get those things, and now at this point, there's not really much we can do because we don't have any premises for these conditionals. So at this point, basically, you have to start your subproof. Remember, to start a subproof, you tab in once. My recommendation is just press tab once and write the antecedent. Write the antecedent of your conditional. And so write colon AS, and you can write a little note for yourself, assume for conditional introduction. Now, if we have HC, of course, we can get ACG by conditional elimination. So ACG from lines 3, 5, conditional elimination. And now if we have ACG from line 4, if ACG then CC, we can get CC. So CC from 4, 6, conditional elimination. Remember, the key thing is just whenever you're in the subproof, if you start a new line in the subproof and you're one level in, just make sure you remember to press tab once so that you stay within the scope line of your HC. All right. So now from assuming HC, we got CC, and that's what we want for our conditional. So we cite the entire subgroup using hyphens. So colon 5-7, or the lines in our subgroup over here. And then we write conditional intro. Wait, no, conditional intro. Cool. And we got that. And then if we've done everything right, then when we type this little line number, it will turn green. So we hit 8. Yeah, good shit. So that's our argument in our natural reduction system. And it really is completely parallel to how we had reasoned with our boy Carl, or whatever. Where was Carl? Yeah. So we reasoned this way with let Carl gain 0, and then we went through these steps, and this natural language argument is exactly what our proof system is schematizing, is mirroring. So again, it's in this sense at least that our system is natural, because it's pretty parallel to certain forms of mathematical logical thinking. Cool. So this is another way to do it. So in this way of solving the problem of giving the derivation, you start immediately with the assumed HC for conditional intro, and then you universally eliminate the first premise, and then down here you universally eliminate the second, and then you get your if HC then CC. So probably from just a general proof advice strategy, yeah, it is often, if you're going to be doing a subproof, often it is best to do basically everything you have to in the subproof. It makes it easier to obey these restrictions. This bit of advice about do shit within the subproof is really, I think, most important if you're doing existential elimination. So as we'll see in some of the examples, when you have to do existential elimination and you have other stuff going on, you basically don't want to start your existential elimination as soon as possible. It just makes it easier to obey these restrictions. And we'll see some examples where that's important. I think on the homework problems, there's at least one problem where, yeah, that seems pretty important. Cool. Any questions about the universal rules? Stuff seemed reasonably clear. Cool. All right. Cool. So now we do the rules for existential. And again, we have two rules, intro and elimination. In this case, the intro rule is the easy one. So, they're flipped. For the universal quantifier, the elimination rules chill. For the existential, the intro rule is the chill rule. So basically we're saying if we have, a specific object that satisfies some formula, script A, X, then we know that at least one object in our domain of discourse satisfies this formula. So the following rule is a good one. If on line J you have an instance, AC, you can infer the existential quantified version of that instance where you've taken the C's, the constant C's, and replaced them by X's. And I guess, yeah, the key thing here, based on the way we recursively define sentences, yeah, there's one restriction, which I guess I didn't put this on the slide. But this restriction is on the sheet, provided that the variable chi does not already occur in phi of whatever with these constant C's. And in this case, so yeah, one thing that's cool here is you don't need the variable chi to replace every instance of C. So you could just replace some of them. So if you had, for instance, can't remember if we'll see an example where this sort of thing matters, but sometimes it makes a difference. So if we had a sentence, this would be the key of PC and MC B, then this was on line M. there's an x such that px and mcb, and you could leave this as a c if you wanted to. So whereas with the universal intro, it's like you have to replace every instance of c with the x. Here, you could pick and choose. You could replace both these c's with an x. You could replace this c with an x, or just this one. And these various existentials will be true. There is an x such that pc and mxb, and also there's an x such that px and mxb. So each one of these guys could be justified by line m with our existential introduction of any one of these three. That's basically what this restriction is saying, provided that the variable doesn't already occur here. And the reason we have that restriction is just the way we recursively define sentences, or really, I guess, well-formed formulae of quantifier logic. We had a restriction. You could only tack on a quantifier if the variable you're binding doesn't already occur in the previous well-formed formula that you are applying the quantifier to. There's other ways of setting this stuff up where you wouldn't have that restriction, but this keeps it clean. So, cool. Any questions about that? About the intro rule? All right. So then we do the elimination rule, and this is strap on your seatbelts for this. So, imagine again we were just going to try to identify the simplest thing to do. At first glance, we would say, oh, okay. We have something, there's a chi, such that chi satisfies formula script A, whatever that is, and then we would just instantiate it for C. But this, in general, does not follow semantically, because here we're saying there's at least one thing that satisfies formula A. Here we're saying, like, Chad satisfies formula A. Well, Chad might not be that thing. It might be some other thing that satisfies A. So when we know this sentence on line K, we know at least one object satisfies the sentence script A, but we don't know which one or ones. So instead, what we have to do is introduce a temporary name that stands for any one of the objects that satisfy this thing, A chi, and then reason accordingly. And so basically, this kind of like introduce a temporary name, we're kind of doing like a hypothetical presupposition. We're saying like, well, imagine for the sake of argument that Chad is the one. Chad's the object that has this property. Imagine that's the case. What can we get reasoning from that? Anything you can get reasoning from Chad or Chad's arbitrary is something you can get reasoning from the genuinely arbitrary object. But when we do this, imagine for the sake of argument, we're basically saying something like, start a subproof, because we'll now, initially going to be in the scope of a new assumption that will then discharge. Cool. So when we have an existential, we'll just pretend that the meta variable chi has some specific name, script C, and then we'll reason from the instantiated thing, AC. We're really, I guess, what I should be writing here, maybe not. There's so many notations for this, but what I ought to be writing to be consistent with our lovely book, which I modified for the sake of this notation, is A of X, or chi for C. So the formula, script A, whatever it is, where you've taken the instances of chi and you have replaced them with a C. That's basically what we need by this thing. So I'll probably change this in the slides. So here's like, an example to see that this is what we do naturally when doing some arguments. So we might have two premises. There are heroes who wear capes, or again, this just means there's at least one hero who wears a cape. And we also have anyone who wears a cape is known as Greta. So for all the people, if they wear a cape, then they admire Greta, and then we could conclude that some heroes admire Greta. What we might do is we say, okay, well, we know there's at least one hero who wears a cape. Let Kate be an arbitrary one of those heroes. So then Kate wears a cape. Now, since we also know that anyone who wears a cape admires Greta, we know, well, Kate admires Greta. And so, of course, since Kate's a hero who admires Greta, where Kate was just an arbitrary thing who was wearing a cape, well, then we know that some heroes have to admire Greta, even if our domain of discourse, as a matter of fact, has no Kate. We're basically just saying, like, let Kate be the thing, whatever the thing is in our domain of discourse that does satisfy this first assumption, namely is a hero who wears a cape. So this natural language argument is what we'll do in our proof system. And it's going to look kind of complicated because of the subproof assumption and these restrictions. So the key thing, the restrictions. Watch yourself. So if we know that some object satisfies A of chi, then we hypothetically assume that C is one of them, and then we can prove, if we can prove that some sentence B follows from this assumption where C doesn't occur in B. That's a key thing. Constant C cannot occur in this sentence B. Then we could conclude that the sentence script B follows already from the existentially quantified sentence that we have. So this, basically these points give us the rule. From the existential, you start a subproof where you assume an instance of this. So you've replaced at least some of the chi's with C. So you assume for existential elimination. Then you get some sentence B, where in this sentence B, the constant C does not occur anywhere. This is the thing that's really going to throw you. And one way to remember this is the B here has to be the same as the B here. So it's kind of similar in a way to the disjunction elimination rule. So if you look at disjunction elimination, you see that in either of the subproofs, you end with omega. So you went from the first disjunct to omega, from the second disjunct to omega, and then when you have omega within the subproofs of both, then you pop out of the subproof and you write omega again. This is kind of similar. When you have B within the scope of the subproof, then you pop out and write B again. So one thing that you're probably going to forget to do is you're going to write the correct thing here, but forget to have it written up above. So you just have to remember, you're going to write the same sentence twice. Maybe it's the little laser thing's really bad, I don't know. You're going to have the same sentence twice, one within the scope line and one not in the scope line. So key pattern here, I'm trying to avoid you falling into a rule following paradox. Focus here. Notice that you have two B's. Okay, and then there's a more complicated citation pattern. Because we have a subproof, you have to cite two things. You have to cite the line that has the existential, and then you have to cite the entire subproof, M-N. And then you write the rule, existential elimination. So this is the complicated one. And the easiest way to remember the restrictions is just to say, provided that the constant C does not occur anywhere else outside of the subproof. And what that basically means is, provided that this constant C is not in any earlier sentence. Now it's like the mnemonic is a bit stronger than what you really need, but typically it's going to hold as well. So as a weaker claim with these three restrictions. So and it's just easier to remember. So basically, provided there's no C's anywhere else above, and you could always do that. You have an infinite number of constants, so you could always choose a constant that just has not appeared yet. And it's an arbitrary constant, it's the whole point, so you might as well. And then, if C doesn't occur anywhere else outside the subproof, well then C doesn't occur in B. Because notice this B is outside the subproof. So if C doesn't occur in this B, C does not occur in this B, because they're the same B. What does it mean for them to be the same B? That is a rule following paradox, basically. What does it mean for this thing to be the same as that thing? That's exactly what's in question when we ask someone if they're following a rule. So, because C can't occur here, what this basically means is in a lot of cases of this rule, the thing you infer is going to be a existentially or universally quantified sentence, so that it doesn't have this free constant C occurring. Cool. So yeah, so C special, C must not appear outside the subgroup. We're really, again, this is technically a little bit stronger than what's necessary. The thing that's really necessary is these 3 restrictions written on the sheet, 1, 2, and 3. But if you do satisfy this, if C doesn't appear outside the subgroup, then 1, 2, and 3 follow automatically. And so my advice to you guys is just, yeah, always use a constant that's never appeared before, because then you're that much less likely to get into trouble. Cool. So here's our example. There are heroes who wear capes. Anyone who wears a cape admires Greta, and so some heroes admire Greta. This is our schematization. There's at least one X, such that X is a hero, and X wears a cape. For everybody, if they wear a cape, then X admires Greta. So we infer there is something that's a hero and that admires Greta. So our goal is to do this in the kernel thing. So I think this is, what number? Alright, so this is number 5. So our goal is to derive this sentence from these first 2 premises. So, I'm trying to think, this one's a lot easier. Maybe it's just illustrate again. Yeah, you know, maybe let's do 10.4 first, and then we'll do 10.5. So in 10.4, we have a very trivial claim. If something's a B, then something is a B. Great. And we're really just getting comfortable with the syntax of our rule. So yeah, so try to fill in what should go into PP 10.4. Just to make sure we're on the same page. Me personally, I'm on page 247. I don't know what page you're on. Do you guys hit green checkboxes? Let's see if I can get a green checkbox. Oops. Okay, so this thing is 2, an existential intro. So it's like, this is the thing that's just like, it's going to seem counterintuitive, but you have to do it. We're trying to get an existential thing, so when we start our assume for existential elimination, basically you have to get the thing that you want to conclude. You have to get it within the subproof. So we first have to get within the subproof, there's at least one thing that's a B. Then you get to repeat that, but now outside the subproof, and you cite 2 things. You cite the existential that you eliminated on line 1, then you cite the whole subproof. Since subproof you need a hyphen, even though in this case it's only 2 lines, you still need the hyphen. 2 hyphen 3, and then you write existential elimination. So, it's just, you know, complicated syntax. Any questions just on the syntax? Alright, so let's do 10.5. I'll give you guys a minute to try your hand at heroes and their capes. There was a talk I saw one time by an anthropologist that was called Demons and Their Bullshit. It was a pretty out there talk. It was not received well by the philosophers. It was like an interdisciplinary talk. This guy got reamed out. Yeah, I felt kind of bad. I feel like I could defend him now, actually. I understand more what he was saying.
questions, Kyle?
I'll read our homely reminder. PS 10, Saturday, 7 p.m. But yeah, since you guys are here, if you're really in a jam, feel free to get in touch. And I will be lenient in your cases. Anybody get green check mark on this? I'll start working on it as well. So here, the key thing to start is just to recognize we have an existential, so probably we're going to have to do existential elimination. And if you think you're going to have to do existential elimination, my advice to you is just make that your first step. Have your first step be assume an instance of this existential and start a subproof. So pick a constant that hasn't yet appeared. So here, the only constant that's appeared is g. So you don't want to use g. You can use any other constant, just don't use g. So we tab in, and let's stick with C. Our beloved Chad, in this case Kate, our hero. So HC and C, little c. This is assume for existential elimination. This group's in type of, you need a capital AS. Bam. There's some other way to introduce assumption that is a little less annoying. I came across it by accident, and then I was like, shit, I should have been telling people this the whole time, because there's just a little bit, but now we're locked into colon AS, I think, so we're gonna stay the course on that. All right, so again, and this is just it's a weird thing to say, because like in your heart, you really feel like what you're doing right now is already eliminating the existential. You feel like, I'm already doing it, but you have to remember, no, this is an assumption. This is, colon AS, because you're just assuming, hey, what if C? What if little c is my at least one thing? That's a hero, and where's a kid? And now the rest of the proof, basically, we're in the scope of this assumption. And so you just got to keep every new line enter, press tab once, so you stay directly underneath this thing. All right, so now we can universally instantiate, and you think, well, I got little c, I probably want to reason in terms of little c. So when I universally instantiate, probably I'm going to instantiate with little c. So everything is such that if it wears a cape, then it admires Greta. In particular, little c is such that if it wears a cape, then it admires Greta. I feel like little c sounds like a children's story character. Little c went to the bookstore today. All right, so we have this stuff. And, you can always start from the bottom as well, and you think, what's going to be at the bottom if we're working with an existential elimination is going to be the same thing as the final line. So the last line of our subproof is just going to be the thing we want. There is something such that HX and AXG, and this is going to come from some instance of existential introduction, which is the rule that is chill. To introduce an existential. So we know that's going to be the last line. And so you're like, okay, if I'm going to introduce an existential, what does my rule tell me? My rule tells me I need an instance of that existential. So we're going to need an instance of there is something such that hx and axg, and we're reasoning with little c, so our instance is probably going to involve the constant little c. So it's probably going to be hc and acg. And so from our proof strategy thing, what we've noticed basically is, okay, the thing to get at this point is hc and little acg. So this is stuff you could, working from the bottom, you could write these as your last 3 lines before you know really anything else about this proof. And working from the top, the thing to realize is just, yeah, you're probably going to want to start with existential elimination. And now, once we're in here, we don't have any quantifiers. This is all just intentional logic. So here, you're just calling upon your proficiency with SMD. So you think, okay, if I need HC and ACG, and I have HC and CC, and I have this conditional, well, great. If I get CC, then I can eliminate this conditional to get ACG, and I can get my HC by eliminating the conjunction. Then I'll have both of my conjuncts. On one line I'll have HC, on another line I'll have ACG, and so I can cite those 2 lines and introduce the conjunction. So again, and it's it's important before you just start clicking things to be able to articulate your plan verbally or mentally in your head, because otherwise you might just go in circles, which is unproductive unless you're getting paid to go in circles, and that means that you are a philosopher. I make money to go in circles. That's my job. My job is to get somewhere. If you got somewhere in philosophy, then they'd have to stop paying us, right? We can't solve our problems. So, cite line 3, existential elimination. Let's get the other one. Also line 3, existential elimination. Looks like, did I screw something up? Oh yeah, I didn't write justification for this. So line 4 comes from line 2, universal elimination. And now with my CC on line 6 and my conditional on line 4, I can get the consequent ACG from 4, 6, conditional elimination. Now I have on line 5 HC and on line 7 ACG, and so I can write conjunction introduction. Now I have an instance of my existential that I want on line 8, so I cite that. And technically I should check my provided that my variable does not occur already. And we're like, great, yep, my variable x does not occur on line 8. And I've decided to replace both of the c's with the same variable x. So that's legit. And now when I go to do my existential elimination rule, finally, I just have to check that these 3 conditions hold. And the easiest thing is just to say, does the constant c appear anywhere outside the subproof? No, because the only lines outside the subproof are lines 1, 2, and 10. 10 doesn't have it. Lines 1, 2 don't have little c. And so I'm good, because I satisfy this even stronger condition. And so, of course, you could check that I've satisfied the 3 slightly weaker conditions, little Roman 1, 2, and 3. So the key thing to remember is just you can't have your constant appear in the last line of your subproof. And that the last line of your subproof has to be exactly the same as the thing that you are going to write when you pop out of the subproof. Those are the things that you're very liable to forget. And then you cite 2 things. You cite the existential that we started our assumption with, by fake eliminating. It's kind of like when you start the assumption, you fake eliminate that existential. That's basically what lets you write line 3. So we thank line 1 for letting us do that, and then you cite the whole subproof using a hyphen, so 3-9, and then you finally write your rule, existential elimination, and you're good. So, any questions about this? You guys all get green? Playing for the green? Good. So, let's see, where are we in slide land? We probably just move to more examples. Or I'll start Wolfgang paradox. Ho ho ho. Yeah. All right. So this is what we did on Carnap. So when I go to post the slides and stuff on Wednesday, you guys can always practice, these problems and just see, can I do this on my own? Can I do this without anyone guiding me through it? That's a good test of your comprehension. Cool. So, yeah, let's do another practice problem, and then maybe I'll tee you guys up for rule finding paradox. And basically what we'll do on Wednesday is I'll probably put some tips into the slides. I'll try to articulate just some strategies that work naturally, and then you'll have them written down. We'll do more practice, and we'll probably do at least some of the homework problems. I think at least one homework problem. I have a bunch of practice problems at the end, some of which I think are modeled on homework problems. Examples in lecture. So we'll probably do these examples in lecture on Wednesday. So if you're bored, I say don't do 21 through 26, because we'll probably do those in lecture. And some of these are analogs of the homework problems. So that's always good, right? Like birds, lives like birds. I have no idea what I'm doing when I write this stuff. That's great. Okay. I'm sure like next year I'm gonna see a lot of this stuff and be like, what was I thinking? Okay, so yeah, let's do 10.6. I'm assuming that this is an existential one, and so that's what we want to practice. So yeah, try to set this one up. Try to get a strategy. I'll do the same thing. I'll try to at least get a strategy first. Cool, yeah, this one looks pretty convoluted, we might say. So here's at least where I'm at with strategy. So we copied the premise, we copied the conclusion. We're confident that we are going, since we have an existential, we're confident we're going to do existential elimination. We want to build up an existential, so we're confident that, we want to build up a disjunction. So if you want to build up a disjunction, you're confident that somewhere you're probably going to have or intro. And that's telling you, well, if I get one disjunct, then I can get, the other disjunct. But I think that'll work. We will see. And then we're looking at the thing we're going to fake instantiate. And so we start a subproof, pick some constant C, and now we're thinking, oh, okay, this is a disjunction. If you have a disjunction, you're probably going to do disjunction elimination. So basic thought here is something like, well, from AC, I can get, there is something that's an A, and then I could introduce a disjunction and get, the other one. And then from B, I could get, there's something at B, I could introduce a disjunction on the left, and I could get this thing. So in either case, I can get this thing. So I guess really, yeah, this is going to be coming from or elimination. So in either case, I can get this thing, and then I can do my existential elimination rule. So I'll let you guys try to fill that in as I fill it in. So now I'm two layers deep in my subgroup, so I'm tabbing twice. Have you guys done the AC part? The AC subgroup? Okay, so turn this back on the model. Okay, so we've assumed AC for OR elimination. We're going to exploit this disjunction. So now I'm 2 tabs in at this point. I'm under the assumption of these guys. And now we can existentially introduce, that's the chill one. I can get there is something that's an A, so at least one thing that's an A. And now remember with disjunction introduction, you can add any disjunct, anything. So from the fact that at least one thing is an A, of course at least one thing is an A, or at least one thing is a B. Even though in this subgroup I haven't said anything about keys. That's fine, because it's a disjunction. And now, remember the key thing is, when I go to do my second subgroup of OR, I need to break it, and so I press enter to start a new line, and the breaks have to be 1 layer less deep. So if your subgroup is two layers deep, the breaks, the hyphens, have to be 1 tab in. So that's it. Just don't forget that fact with nested subgroups. So the hyphens are 1 tab in, and then you press enter again, and then you're back to 2 tabs for the second disjunct BC. And then this subgroup is going to be completely parallel to this one, just working from B's rather than A's. So 2 tabs in, I can existentially introduce, there's at least one thing that is a B, cite line 7, existential intro. Now I can say, of course, then there's at least one thing that's an A, or there's at least one thing that's a B from line 8 in OR introduction. So here I chose to introduce A on the left because you want to have an OR elimination, you want to have the same sentence coming from either case. So that's really crucial that we introduce the thing on the left. And now in both of my OR elimination subproofs, I have the sentence I want. And remember, I knew I wanted this sentence just for my backwards reasoning, starting from the bottom. That's my goal. Remember, OR elimination, you cite 3 things. You cite the line of the disjunction, line 2, and you cite both subproofs 3-5. You skip over the hyphen line, cite line 7-9, OR elimination. And now in our last thing, we just recopy that sentence, but now we're tabbed in, and we cite the existential we used on line 1. We cite the entire subproof, 2-10, and then you write existential eliminations. Yeah, we got it. Cool, good shit. I hadn't done that problem in a long time, so I'm glad that worked. Cool, awesome. So yeah, so we'll do more examples next time. We'll talk about rule following. Rule following is basically the following puzzle, which is if I asked you to keep writing 2s, I just want you to write 2, 2, 2, 2, 2, 2, 2, 2, 2. I want you to keep doing that. What is to say that when you get to the 1000th 2, you shouldn't start writing a 3? What's to say you shouldn't do that? So the puzzle is to give an answer to that question that doesn't beg the question. So you can't say to me, well, you asked me to keep writing 2s, and so of course at the 1000th number I have to write it to, because that's exactly what's in question. What's in question is, what have I asked you to do? What is the nature of following the rule? So, think about that. But cool, awesome. Thanks, guys. See you on Wednesday. And I'll probably have office hours Wednesday, normal time, and Friday, normal time. But if you have any questions right now, feel free to talk to me. On Saturday at 7 p.m. If you guys need like a day extension, just feel free to shoot me an email. I think my initial intention was I was gonna grade all this stuff Saturday night, but then got invited to the party. So I don't actually know if I'll do grading Saturday night. We'll see. Might do grading very, very late Saturday night. So we'll see how late this party goes, right? I feel like if I'm back before 12:30, I might do some. I kind of like, do I do all the grading sober? Yeah, I'm completely sober the whole time. We're very focused on the possible mistakes you guys have made. It's kind of fun grading in the Carnap system because what I love about it is I always have a strong urge to give you guys comments on things, but Carnap doesn't let me give you comments. So Carnap saves me from myself, and I'm only allowed to give you points, and I like that because even if I wanted to say, hey, it's on line 7, you missed something, I can't say it. So thanks, Carnap. So what we're going to do today is go over the rules again. We'll do some stuff about substitution, but we might go through this fast because as I was making these slides last night, I realized, are these really that helpful pedagogically? And I don't know. And we'll go over some tips, just general structural tips, and then I think the main goal for the day will really be to do some practice problems, these examples in lecture, which are, I think, modeled on, if my past self is reliable, then I made these examples to be models of 5 homework problems, I think. And then I'm hoping that I'll leave time to do 3 of the harder actual homework problems, especially 10.8 and 10.10. So, and then you guys should be set up for success. Cool. So these are our rules. We have 2 rules for the universal quantifier for all. So the chill one for this rule is the elimination rule, where what you notice is when you have something that's universally quantified and it's got some variable that's bound by the quantifier, you can take all of those bound instances, all of the chi's bound by this for all chi, and replace them with the same constant c. And it's crucial here that you replace every single instance of the bound chi with c. You have to, every single chi has to be replaced with a c. You don't get to pick and choose. So some notation we'll talk about for this shorthand is really this thing, phi of the c's is phi of c for chi, which means you've replaced c for chi. So that's our elimination rule, which is the chill one. And then the introduction rule has some restrictions. One of the restrictions is like kind of trivial, and I feel like you wouldn't really mess this up. The key restriction is that the constant c doesn't occur in any undischarged assumption. That's the one, if you're going to mess one up, it's going to be that condition. So what this says is if you have some sentence phi, that's a function of a bunch of stuff but has some constant c in it, then if you don't have c occurring in any undischarged assumptions, then you can introduce a universal. You again replace every single one of the c's with the same variable chi, which is bound by a single universal quantifier. And so one illustration of how you might go wrong on this is a kind of common mistake. If you have FA, here this second line is in the scope of an undischarged assumption. So this second line is in the scope of this f a, where a, is our constant script c in this case. So this would be an illegal instance of for all introduction. So in some of the homework problems, you guys might be tempted to do this kind of thing. You just want to check yourself before you write yourself. So you want to check. Whenever you do one of the rules that has a restriction, you just want to say, even if you're really confident, even if you're like, yeah, I'm like mad baller with, natural deduction, you want to say, whoa, 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 provided that what? And then you want to double check that. Any questions on the two universal rules? Universally the best rules. For all the rules, these are our favorite rules. All right, so then we do the existential rules, and in this case, the chill one is the intro rule for the existential quantifier. So if you have some sentence phi that has some constant script c occurring in it, you can replace some of those occurrences of c, not necessarily all. So here's the one rule where you don't have to replace every single constant c with chi. It's the only rule. The other ones, it's always like a one-to-one map between the constants and the variables. But in this one, it doesn't have to be. Could be. And so then you get to replace some of the c's up to all of them with the chi's, bind them by an existential. And here are the restrictions that chi doesn't occur already in this thing. And the rationale for this is really just coming from our recursive definition of sentences. So really, when we're doing these proofs, we're really only interested in working with sentences, things that have a truth value. And so if you did have a chi in this phi thing, it would have to be bound already in order for the phi to be a sentence, not just a well-formed formula. So then you wouldn't be able to bind it again. So it's kind of a trivial restriction in a way. I feel like you're not really going to encounter this kind of scenario anyway. So there's not much to worry about. Okay, so that's the chill one. And then the hardcore rule, which is the one you're most liable to screw up, is existential elimination. And when you have an existential, whenever you're in a problem and you see there's an existential, you should think to yourself, I'm probably going to use this monster rule. And the way to use it is at some point in your derivation, and my advice to you, one of the slides, is start this subproof ASAP. If you're confident you're going to do an existential elimination, start it as soon as you can. Try to do as much of your work in the proof within the subproof. It just makes obeying this restriction a lot easier. You're less likely to fall foul of the restriction. So what you do is you instantiate an instance of the existential, and you write :as. So here, you're not actually justifying this for rule. You're starting a subproof, so you're assuming something. Then you do some work, you get a psi, and then right after that, you pop out and write the psi. So I realized, as I was putting this, on the rule sheet, I have a ... after, I have a ... in between here, and I realized you actually shouldn't have a ... I think Carnap will be finicky. And so when you use this rule, when you get this psi within the scope of your subproof, I think in Carnap the next line is going to have to be psi. I don't think Carnap's going to let you do other stuff and then later write the psi, because Carnap is a little finicky in this regard. And then you cite two things. You cite the line to the existential, and you hyphen cite the subproof. And the key thing here is that in psi, you can't have the constant c occurring. That's the key thing. And this says, provided c doesn't occur anywhere else outside the subproof. Here, this psi is outside the subproof. This psi is the same as that psi. So if you can't have a c in here, you can't have a c in there. And that's the thing you're most likely to screw up. You're going to be tempted to have this thing have some c's in it and then write a different thing here that doesn't have c's, and you can't do that. So it's illegal. All right. Any questions on these rules? All right. Cool. So there's some stuff we can say about substitution instances. I'll try to blow past this because, again, I'm not really sure how pedagogically eliminating this is. We'll see. Maybe you'll really like it. So we have this notation, phi of c for chi. It's a sentence you get from the universal by dropping the quantifier and putting c in place of every chi and phi. And you don't touch any of the other variables. And likewise, this phi of c for chi could come from an existential, where again, you've drop the existential quantifier and you put C in place of every kind of phi. And so some equivalent notation, which is used in the initial version of this book, which might make it more manifest. It's all the chi's are going to C's. So you might like this notation better. I think it looks kind of clunky. So I got rid of this notation in our book, but if you have strong feelings pedagogically and you think this notation is obviously better than 5C for chi, let me know. I'll be curious. I could imagine that some people would mix this up and think, oh, which one am I replacing? Which one? Whereas here you have a manifest asymmetry. It's the chi's are going to C's. So, choice of notation in the history of mathematics and science is very crucial. Even though these things are, in some sense, trivial notational variants, there's still a sense in which this could be a better mnemonic, but it just looks really ugly. So who writes boxes around their symbols, right? You've never seen that before. I've never seen that before. So we banished it. All right, so some examples. So if you have everything as an H, then some instances of this is, you're just replacing the Y with a constant, that's chill. You have an existential, there is something such that A, which could be Alfred, helps that thing. So there's somebody that Alfred helps, is what this is saying. So some instance here, this Z could itself be Alfred. So this would be Alfred helps Alfred. Could be Alfred helps, Beatrice, or Alfred helps somebody else. So these would all be substitution instances of this existential. If we have, there's some Z such as HZ and FZZ, then remember in the substitution instances you have to replace every occurrence of Z with a constant. So we could do HA and FAA or HC and FCC, but we couldn't do the following ones. So the following would be illegal. You couldn't have HA and FAZ because you left this Z unreplaced. Here, HY and FAA, you left this Y. Here I guess the problem is you have to pick a single thing you're going to replace the Z with. So here we replace this Z with a Y and this Z with an A. So that doesn't work. And same thing for here, HA and FAB. Cool. So yeah, some things that, I don't know, you could just get tripped up from these definitions. So this well-formed formula for all x gx or for all x fx, is this thing universally quantified? Raise your hand if you think yeah. Raise your hand if you think hell no. Yeah, got some hell no's. Raise your hand if you're not sure. Yes, I'm not sure. So this thing is not universally quantified. It is a disjunction. So the main connective here is the or, so it's not a universally quantified sentence. If it were, then the main connective would have to be a universal quantifier. So if somebody ever asked you, you're on the street and this is what all cool kids these days talk about. Someone's like, yo, this sentence, write down an instance of this disjunction. You're gonna say, bro, you crazy, because there are no instances of this sentence. It's a disjunction. So it's not a quantified sentence, only quantified sentences can have instances. So you can't, for instance, apply universal introduction, universal elimination to this disjunction. You can't universally eliminate these things. If you wanted to work with this in a proof, you'd probably have to start disjunction elimination. You would then have a subproof that begins with this, and then you could universally eliminate everything's a G, and then you have another subproof that starts with everything's an F, and you could again universally eliminate this guy on its own. Any questions about this? Cool. We love this stuff. All right, so finding formulas that have a given instance. So our goal here is to figure out some well-formed formulas that a given well-formed formula is an instance of. So the question is, if you have FA, what could FA be an instance of? So here are some examples. It's an instance of everything's an F. There's something that's an F. Every Z is an F, etc. FAB, this is an instance of Everything is F'd by Alfred. Everything F's Beatrice. That's, how we might feel. There's somebody that Alfred F's, and there's somebody that F's Beatrice. So and I realize now that when I edit these slides for next year, I should use a different letter than F, because that doesn't really sound very nice, does it? So, yeah. So the key thing here is just, you can see we have two names A and B. You have a choice of which one of these you want to replace with a variable. So, here we've taken the B and we've replaced that one with a variable. Here we've taken the A and replaced a variable. Now FAA, this one has some interesting cases as well. You could replace both of the A's with the variable everything F's itself. Also a true statement, right? This is Alfred F's everything. So here we left one of the A's. So yeah, and here we have everything F's Alfred. So the key thing here is you have some flexibility. So FA is an instance of all of these different things. So basically, the thought process here is sometimes in a proof, you're going to have one of these instances, and part of the challenge will be to come up, what is the right quantified sentence to use in the proof, the right quantified sentence to use for universal intro or for existential introduction to go on in the proof. So, cool. All right, so we have this notion of partial substitution as well, and it's really just relevant for the existential introduction rule, where we noted that the variable chi can replace some or all occurrences of C. So it's really just for this one rule that you could, if you wanted to, introduce some special notation. This is the substitution instance of chi replacing at least some of the constant script C, but not necessarily all of them. So you get to decide which occurrences of C to replace with chi and which C's to leave in place. And it's really just useful for this one rule. So again, maybe it seems kind of wild to, care that much about this notation. It mattered a bit in our satisfaction semantics in chapter 9, which you probably didn't read. Then this notation was again helpful, but like, it's yeah. So this is just to illustrate some of the flexibility you have with existential introduction, which we talked about briefly on Monday, but here are some more examples. So here's our rule written with this notation. There's some chi such that phi, you replace at least some of the chi's for C's, provided again the chi doesn't already occur in the initial phi thing. So here we've replaced both the constants D with the same down variable x. On the second line, we've replaced just the first D, and we said there's something that R is D. I don't know, what's a good predicate for R? Rafflecopters. Can that be a verb? There's something that rafflecopters D. I don't know. What's D? D is Diego. We love Diego. So in this one, we do, the other order. There's something that Diego rafflecopters, and now on the last line, we take this existential and we view line 4 as an instance of this other existential, where now you always add the quantifiers to the left. Quantifiers always get added to the left. And so here we have, there's at least one thing y, such that there's at least something z, such that y rafflecopters z. So this is also an existential instance. So, cool. Great. So now we're like, basically our question here, was any of this worth it? And I'm really not sure. I was making these slides last night, and what happened? So I got my COVID booster yesterday finally, and I always forget. I do have pretty bad reaction to the COVID boosters, but it sets in like, I don't know, 10 hours after the shot. So around 10 o'clock, I'm like, whoa, I'm starting to feel it. Around 11, I'm like shutting down. I'm like, shit, I need to finish these slides, And I'm like, whoa. And I'm kind of like, why did I even do all this stuff, you know? Like, because I don't even know if these slides are really like that helpful. But I was like, you know, you're like, you committed to something, so you have to finish it. That's how I felt. And then I started shaking uncontrollably. That's what happens with me in the COVID booster. So, and then a part of me, so at midnight, right? At midnight, I'm shaking uncontrollably, and I'm like, well, I hope I can teach tomorrow because I'm feeling better now. So I sleep off the COVID booster thing. But the other unknown was so my brother and sister-in-law just had a baby, and my sister-in-law is a doctor. She's a child's poop doctor. There's an official name for that, but you know, gastroenterologist. She's a pediatric gastroenterologist. She's a kid's shit doctor. But, we don't have to glorify this. It is what it is. And so she's really medically kind of controlling, and so I'm gonna visit them in December, and they're making our entire family get the whooping cough vaccine update, so the Tdap. And with the Tdap, you can have a really severe swelling reaction. So I got both these yesterday, and I was like, well shit, one of my arms could just completely swell up. So that didn't happen. So I think I'm in the clear. On the Tdap. So yeah. So now actually I got the COVID in my left arm. Thinking that the Tdap arm would be the one that went to shit, and it was the COVID arm. It's the one that was much more sore. So this is all a long way to say I'm not really sure if it was really worth talking about any of this. But if you like this notation, then you can rewrite our rule sheets, and rather than having these long ... things, you can just have this more precise notation, where here we're explicitly noting we've replaced every single instance of chi with C, and here we've replaced every single instance of C with chi, because these are full substitution instances. And it's really one benefit, I guess, of this notation is in my beloved logic book. Oh yeah, this was a whole other thing yesterday too, because I was looking at the logic book, which I love, and I realized that my restriction on universal introduction is different than the logic books, and I was like, shit, did I just lie to you guys, and did I have a mistake? And then I was really puzzling over it, and I realized there's not a mistake, it's just this difference in notation, where basically the logic book writes a substitution instance up here, and so then they have to say, by the way, you can't have the constant C occur in the instance. You can't have the constant C here. Whereas our notation takes care of that, because our notation is telling us you have to replace every instance of chi with C, so of course the variable chi can't occur in here. Because the variable chi can't occur here. Whereas the logic book has to say that as a separate thing. So that's cool. And then with these rules here, this is a full substitution instance. You have to replace every single chi with C when you do the starting assumption for existential elimination. And over here is the one case where you can have a partial substitution instance. That's the one case where you get to choose how many of the instances of C you want to replace with chi. You can do some of them, or you can do all of them. And so really, this notation is a long way to just eliminate one additional restriction node on this rule, basically. So, I don't know. Let me know in the comments if you think this was working, right? That's what we're saying. So we got some tips, but I think let's do some practice, and then maybe we'll come back to the tips. Because the tips always seem kind of abstract unless you're, have some concrete examples. So we'll start with, this is the current practice problem. So if you're on the Canvas page, our beloved Canvas page in our week 10 module, there's practice problems for week 10. You can click on that bad boy. And then if you scroll down toward the bottom, you'll get these examples in the chart. So give you guys some time to get started on this. The thing though, I sometimes forget this, but remember to write in your starting assumptions, justify them with PR. definitely do still feel a little messed up though from the COVID thing. I feel like I'm skating. We're only 30 minutes into this bad boy, right? So. This is what I imagine I'm gonna have to do when I'm an old man anyway. I'm gonna have to sit my ass down. I'm gonna have a cane. I'm gonna lean my cane against the wall and I'm gonna sit down. Hopefully we'll have a better website than Carnap by then or something. I guess this thing's too high. Oh yeah, well that's why it's called a laptop, right? Yeah. Love it. I guess I should have my rule sheet. It's become just take really wild to get out of. You guys all have rule sheets, right? You guys got one? Cool. You guys all have your midterms back? All of you are. Because yeah, I keep bringing the midterm folder and then I think I only remember half the time to actually ask people if they got the midterms back. Alright, got you guys all in a good pile. You can grab your name tag. Freaking bullshit. That's what our goal is here. Alright, so this one's super chill. We're looking at it and we're thinking our last line is going to be this existential. So of course, we're going to have to apply existential introduction to get this thing. So we're confident that our last thing is going to be EI on the preceding line. And so basically we're just asking ourselves, what is a relevant instance of this existential statement that we can get? What's a relevant instance we can build? And we can build FB ampersand GB from and introduction on applied to lines 1 and 2. And then we have our instance and we look at see if there's restrictions. So provided that chi does not occur already in the sentence 5, and we're like, yeah, there's no chi in FB and GB, so we can replace all of these b's with x's, and this is the one case where we don't have to, but we're trying to get this thing, there's something that's an f and a g. So it looks like this should work. Knock on wood. Cool, and we got it. So this one's super chill. Questions about this? Awesome. All right, let's do another one. I haven't looked at these problems in a long time. I think I wrote these in 2019. So we're gonna hope that my COVID booster brain can handle this stuff, right? Otherwise, you guys can handle it. So you can tell me. You can tell me what's needed. All right. So again, before you plow in, you want to try to get a strategy. Walk yourself through it. That's what I'm going to do. Silently to myself. In a certain kind of spiritual ritual, you might say, where our goal is HA. Raise your hand if you think you see the strategy that's manifest to you, what to do. Raise your hand if it's not manifest to you. Cool. I'm just trying to get a sense of where we're at. So, so we're trying to model this read, and this is a creative process. So kind of like when I see this stuff, I think to myself, we want HA, here's something that looks like HA, HX. And so I know, okay, if I universally instantiate, then I can get an instance of this universal with A's. Because this universal applies to anything in the domain, so of course it holds for A. So then I know, okay, I can get FA if and only GA, if that thing, then HA. And then I know I have the antecedent of that conditional, FA if and only if GA, and so I know I can do conditional elimination to get HA. So even before writing anything, we can see exactly what we're going to do, and then we just write it out. Does that help it seem more manifest what we're going to do, or does it still seem mysterious how we will proceed? Cool. All right. So double check our rule, universal elimination, and we see, oh great, there's no restrictions on this one. That's dope. One of the few times in life where there's no restrictions. So GA, we get our parentheses, HA, and I missed the parentheses at the beginning. So what I just wrote on line 3 is an instance of line 1. So I cite line 1 and I write for all elimination. So I eliminated that universal. And now I have the I have the antecedent of the conditional. So I can write the consequent, and I cite 2 lines, the antecedent and the conditional, and I write conditional elimination. Another 4-liner. Yeah. Good stuff. Cool. Any questions on this one? All right. Let's do the next one, and we'll see if it gets harder. So again, before you launch in, try to talk yourself through a strategy. Does anybody want to suggest a strategy, a way to proceed? Or exciting adventure. This round we have some real choices to make. So I guess we look at these and we think, all right, probably going to do existential elimination because we have an existential. Probably going to do universal elimination because we have a universal. And then pro tip to you guys, which is in the slides, whenever you think you're going to do existential elimination, start that bad boy immediately. So I see this and I think I'm going to existentially eliminate and get an instance of the existential DA. So again, you're going to have a temptation to say, oh, I just existentially eliminated, so I should write EE. And it's like, no, the rule is complicated. What you've just done is you've written an instance, but this is an assumption for existential elimination. So, and this was the cool thing that I couldn't remember last time that I stumbled upon. Rather than write :AS, you can write : no space / and then it renders on the right as the little thing. So you see if I wrote :AS instead, my little note to myself goes away. But if I write :A / my little note gets rendered. So isn't that so cool? Yeah. So I might change the code for the book so that it uses this in the future. But you guys are :AS people at this point. So, but I really like this :A/. Yeah. I like to see my little note to myself because sometimes I forget. In some of the problems, you go many subgroups in. Problem problem 8 on the problem set, you go 3 subproofs in. So a lot of the problem, you're three layers deep. And you might forget what you sometimes assume the same thing, but for different rules. And so you might forget what you assumed a sentence for. Yeah, sounds like fun, right? We love logic, yeah. We gotta get t-shirts made. I took logic and now I'm reasonable. I don't know. Okay, so we got DA. So, you should be able to walk yourself through strategy. I'm thinking, we got DA, we can instantiate this universal with an A, and we can get if DA, then SAA. And then I can eliminate that conditional, and I can get SAA. Then I can combine those two things, and I can have DA ampersand SAA. And then, with them combined, I can introduce the existential. That will be the penultimate line of my proof, where still within the subproof, I will introduce this existential that I want. There's at least one thing such that D and it S's itself. And then I just have to rewrite that line outside the subproof, and that'll be the final line of the proof. So that's, we're just gonna think that. Cool. So let's universally instantiate within our subproof. If DA, then SAA. And this is on line 1, for all instantiation, for all elimination. See, that's it. I hate that too, because I naturally think about this as instantiating a universal, and instantiating starts with I, but we have to remember we're eliminating the universal. Instantiating the universal is eliminating the universal, so we have to write AE. Alright, and then we have SAA from conditional elimination, 3 for conditional elimination. Then we combine these bad boys, DA ampersand SAA from line 3, comma 5. Conjunction, introduction. Now we can introduce the existential that we want. So this is the thing we want, but notice that we're within the subproof. So we tab 1 layer in, line 6, existential intro. Check, are there any restrictions you have to follow, provided that chi does not occur already in the instance, and yeah, there's no x on line 6. No x on line 6, so we're good to go. Now I have the thing I want, but it's within the subproof. So I just take it, and now I pop out of the subproof, and now I apply existential elimination. And I can do this because there's no constant A appearing on line 7. So my psi in this case is the thing on line 7, and there's no constant A in there. So when I rewrite psi, there won't be a constant A outside the subproof. So I see, yeah, okay, there's no constant A appearing anywhere outside the subproof, and so I clearly meet this restriction, and I cite my existential line 2, and then I hyphen cite my subproof, 3 hyphen 7, and I write existential elimination, and I leave my little bonus line. Yeah. So really, it's like the strategy here is you could instead on line 3, you could have started by instantiating the universal, eliminating the universal, and having for all elimination. Now you will have an A outside your subproof, and so you just have to, it's like you still would actually meet these conditions. You would meet the weaker 3 provided that conditions, because you wouldn't have the constant C in an undischarged assumption, you wouldn't have C already in the existential, and you wouldn't have C already in psi. But if you just want to follow the easy restriction to remember, the easy one is, provided C doesn't occur anywhere else outside the subproof, then that's kind of your rationale for wanting to start existential elimination ASAP. But this would work. You could do this instead. Let's just verify this would still work. Change our line numbers. So this is 3, that's still fine. And then this is 4, 5. And then this is still line 2, and now it's 4. Very simple. So it still works, but there are more complicated problems where you can actually get in trouble. So that's why I recommend the hot tip of start your existential elimination ASAP. Cool. All right, this one complicated, so we like that. I do sincerely hope that these are in fact analogs of Muhammad problems. I was going to verify that last night before I physically collapsed. Here we are. They're at least practice problems, right? And we endorse practice. Cool. So yeah, try to talk yourself through strategy. Initial strategy on this one, it should be really similar to what we just did. So it's a good test if you're tracking, you know, what's going on. So what's the first thing we're going to do? Follow our pro tip. And we're going to do some cold call. Daniel, closest to me, what do you think is the first step to do?
I'm not exactly sure.
Cool. So whenever we have an existential, my advice to you guys is, and you don't have to do this, but the advice is tab in immediately for a subproof and write an instance of that existential. So pick a constant. So we can pick a constant that hasn't appeared anywhere else. So A doesn't appear, so we can pick A, and we write an instance, JA and SA, and then we write, this is an assumption for existential elimination. Cool. We have that. I guess Daniel, furthest away from me. What should we do next? Da-da-da. So we have another thing. I mean, we have a couple things we could do. Do you have a favorite thing that we can do? I'll take that as a no. Let's do Camila. What do you have a recommendation?
I would think you have to get rid of like the existential for all. No.
Okay, yeah, totally. Yeah. So we wanna instantiate the universal, and I guess with an I, what I'm gonna ask you guys to do in 10.25, let's use the same constant. We could use a different one. We could write like LED, but let's write LAA, and we will cite that line and write AE. Cool. So now we have this stuff. Gerardo, what should we do next?
I separated the conjunction.
Cool. Yeah, so we get JA from line 3, conjunction elimination, and we can get SA. And notice how every time I press enter, I press tab once to stay within subgroup. So SA from 3 and elimination. So now we have all of our little pieces. What should we do next, Michelle?
Existential then.
Yeah. We're just going to existential each of lines 4, 5, and 6. And we're just going to make sure we use the right variables. So from line 4, we'll use Z. So EZ, L, ZZ. And remember, there's a temptation to put the LZZ in parentheses, but technically this is not a well-formed formula, because LZZ is an atomic well-formed formula, and so those never get placed in parentheses. So that one, and this was line 4, existential intro. Daniel, closest to me, what should we write next?
You can just do the rest of them for J, Z.
Mm-hmm.
Yeah.
Yeah. So we can do for line 5 for JA, we're going to use X. So capital EX, JX. And we got that one, and it's line 5, existential intro. Daniel, furthest away, bring it home. What's the next one?
There also exists the X such that, there exists Y such that S Y.
Yep, super, yeah. So EY, SY, and this comes from line 6, existential intro. So now we have all our little pieces, and we just systematically do conjunction introduction. And again, you might have a temptation to just do one instance of conjunction introduction, but remember you can only introduce one ampersand at a time. So we're going to have to first introduce this guy. So this is lines 8 and 9, 8 comma 9, and intro. And then we'll put that in parentheses and introduce our other thing, the Z, CZ. And so this is coming from lines 7 and 10 and intro. Cool. So now we have the thing we want, and the thing we want is within the subproof, and we notice the key thing is the thing we want doesn't have any instance of the constant A. So because there's no instance of the constant A here, we can take this and we can write it outside the subproof and justify it finally with existential elimination. So it just, it just feels kind of weird because you might think, how this thing I just wrote, I mean, this came from an introduction, but the whole thing's coming from existential elimination. The whole thing's coming from, we basically assumed an arbitrary thing A was this at least one thing is a J in this. So now we cite our existential on line 1, and we hyphen cite the whole subproof, 3 hyphen 11. 11, and we write E. Nice. All right, cool. So then, little question for you guys is basically just copy paste your proof from 24 into 25 and modify it so that you instead have, there's at least one thing that is a J and an S and L's itself. So here, we concluded these things could be different. There's at least one thing that's a J, at least one thing an S, and at least one thing that could be different that L's itself. Here our goal is to just have a single bound variable. So, and since we chose A for everything, it should be really easy to modify this proof. Cold calling's fun. I'm sure if I do too much cold calling, you guys are gonna be like, I don't want to come to class anymore. This is too stressful. You have to be confident we're in a safe space and that nobody's judging us. We've all made it. You guys are at MIT, right? It's like you have nothing to prove. So you should feel completely confident in yourselves. At least that's what my therapist tells me, right? So yeah, it seems to me that we just want to build an instance of this conjunction before, and then when we have the instance of this existential, then we will introduce the existential. So put JA and SA together from 5, 6 and intro, and then take that. I'm kind of curious if does Carnap require us to have parentheses, or will it let us get by without parentheses? Let's find out. 7, 4, and intro. All right, cool. So yeah, so Carnap is not a stickler for parentheses on the symmetric binary relations. So that's nice. So now we have this instance, and now we can existentially instantiate on line 8, existential intro. And now outside the subproof, we'll rewrite that thing, and again we'll cite the existential that started it all, and 2-9 essential elimination. And probably have to leave this stuff. Oh, I see. This should be. Here's the typo sound. No, it's not.
3 to 9. Not 2 to 9.
Oh, 3 to 9. Cool. Thanks, Michelle. Yeah. Nice. I love getting these little green marks. It's so satisfying to know immediately that you've achieved your goal. I wish in all other aspects of life we could get a green check mark as soon as we, it'd be so cool if I could sit down at my computer, I'm writing, and I've had a philosophical idea, and then my writing, file's like, great job, this is a good one. Cool. Any questions about this? And this was indeed 2 lines shorter. The person who put this document together knew what they were doing, it seems. So there's one more practice problem, but I say just to make sure we don't run out of time, let's go to the actual homework problems and try to do at least 3 of these. Because even just to get the last 3 started is a bit tricky. So we have a little hint, which is the use indirect proof. Don't forget to rewrite your premise. And this is, I'm in the instructor's version. That was another thing last night. As my body was collapsing, I thought to myself, shit, we're doing the homework problems. I need to make an instructor's version and upload that so I have it. So I managed to do that before passing out. So I think I have a proof checker for everything. I think you guys have proof checker for like at least 5 problems, and then the other 5 are syntax checks. Cool. All right. So 10.8 is indeed kind of a monster. So we've been told we're going to do indirect proof. So we're confident from our little hint that we will assume the unnegated version, the non-negated version, assume this for negation introduction. So basically our goal is to, within this subproof, get a contradiction, then we'll be able to ultimately pop out of the subproof and introduce the negation. Now you might think, why are we doing this proof strategy? There's just really not much you can do from the starting assumptions. Like you can get an instance of this thing, PA, then not QA, and you can get as many instances as you want, but that's it. I mean, you can't, and it's like, what are you gonna do if A is a P, then A is not a Q? What are you gonna do with that? It's garbage, it's worthless. It will be useful within the context of a wider setting. But on its own, you're kind of stuck. So whenever you feel like you're really stuck, you should think, okay, indirect proof is probably going to be, a thing. So 1, and this will be for all information. So we're in here. And now we have an existential. And with an existential, you can do existential elimination. So this is the key thing. You can't existentially eliminate on a negation of an existential. But when you have the existential itself, you can do existential elimination. And to start that, you have to tab in again. So now we're two layers deep, write an instance of the existential PA and QA. And this is from line 3, existential introduction. elimination, sorry. I keep thinking instances and stuff, but it looks like, oh wait, what did I add in again? No, you don't have that, okay. Oh no, I do, yeah. This is, yeah, see, this is what I mean. So easy to script. So we tab in twice because now we're starting another subproof. We're assuming this for exponential elimination. See, I fell prey to the same mistake that you're liable to. So this is an assumption. Another one is PA and QA. Now this is where basically we'll go through this in a way that's not going to work, but is a good proof strategy, and then you'll see it's not going to work, and we'll have to back this train up and modify some stuff. But at this point, our goal is to get a contradiction, and we're thinking, well, I can get PA, I can get QA. If I have PA, then from my instance of my universal, if PA, then not QA. So I can eliminate that conditional and I can get not QA. So I'm confident I can get a contradiction, because I'm confident I can get not QA and QA within the scope of a single subproof. And it's, the problem is, we'll see, so we'll write this down and we'll see that we gotta modify some stuff. So I get PA from 4 conjunction elimination, I get QA from 4 conjunction elimination, and now from line 2 and from line 5 and conditional elimination, I can get not QA. So now I have QA, not QA, and I have my contradiction, but I don't have my contradiction directly within the scope of this existential. I have it nested deeper within a subgroup. And so I can't actually pop out at this point and write the thing I want. I can't write, at least I don't think I can. I mean, let's try it, but I don't. So I don't think I can pop out and write this thing and say, oh, I've introduced my conditional. Yeah, it's like, and here's where the notes are helpful. I can't pop out of this second subproof until I'm going to apply existential elimination. So the way to pop out of this subproof is going to have to be existential elimination. But here I got A's running around. I have nothing that doesn't have A's, and I can't pop out of existential elimination until I have some sentence that doesn't have any of these constant A's. So this is the right idea, but it's just not going to work. And so this is where you have to be a little clever, and you have to think, when I'm doing negation intro, often the sentence that plays the role of psi, not psi, is the sentence I've assumed. So here, I've assumed there is something that is a P and a Q, and this sentence itself could play the role of the psi and the not psi that negates itself. So do is we will start a third subgroup where I'm going to reassume, just make sure I get my tabs right. So 1, 2, 3 layers deep. I'm going to assume this thing again, but now I'm going to assume it for, I guess, yeah, also negation intro. So that's kind of funny, right? So again, it's like, who the hell is going to think of this? This is why you guys are smart to come to class today. Because I think these other people in class, I think they're cocky. I think they think this is going to be pretty easy shit. And I'm going to be pretty surprised if people figure, a lot of people figure this out, right? I think this is not obvious that this is the thing to do. So, I figured this out over the summer, right, as I was digging around with these problems, but I've done this a lot, so. All right, so now we're 3 layers deep, and now we can do this stuff. We can do this stuff with our PAs and Qs. Mind your P's and Qs, right? So just gotta make sure that we're gonna be 3 layers deep. So 1, 2, 3. Okay, so now we can get PA, which is coming, I guess, yeah, still from line 4. And we can get QA, also still from line 4. And now we can get not QA from lines 2 and, I guess, 6. 6. And now I have a psi and a not psi under this thing that I assume for negation intro. So now I can pop out of this thing and I'll be back at my second sublayer where I get to introduce my negation. So I cite the subgroup. This was lines 5 hyphen 8. And this was negation introduction. Woo! Clutch. All right. So looking at our scope line, so this thing is underneath the PA and QA, which I assume for existential elimination, and this thing doesn't have any constant A appearing. So it looks like this is a thing that I could then rewrite popping out of the subgroup, now 1 layer deep, as the thing that I've done existential elimination to. And so what's the existential that I eliminated? It was this one on line 3. So line 3, and then my subgroup for the existential elimination is from line 4 hyphen 9. So you can see how when it comes to keeping track of this monstrosity, I do naturally look at the rendering on the right. I look at the rendering and I check to see, okay, this is where I started the existential elimination, line 4. It was my second subgroup, and I ended it on line 9. And so when I pop out, I'm still 1 layer deep, but on line 10, I'm now just under the initial thing that I assume for negation introduction. Are you guys with me? Yeah. A lot going on, right? So this is the key thing. Now I have some sentence psi and not psi, and they're both within the same subgroup. So now I have my thing I can do for negation intro, and Carnap's a little annoying where it really makes you, and I want to, when I email my boy, Graham Leach Krause, I'm going to notice as well that it's just a little annoying. You have to rewrite this thing, so you have to reiterate, cite line 3, reiterate, rule R, because you need the psi and the not psi to be adjacent to each other within the subgroup. Carnap forces you to do that. Obviously, if you guys in your proofs, you don't do that, I'm going to be, if they're not adjacent to each other, I'm not going to take points off for that. But one thing I would take points off in this case, because from the form of the rule, negation, introduction, it is manifest that both the psi and the not psi have to be within the subgroup under the assumption. So that's just required schematically. So it's very clear in this case that you have to carry this thing down. So now I have my psi and my not psi, they're not in order, but that's cool. And so from this thing that I assumed for negation intro, I got a contradiction. And so I can, in fact, introduce the negation. And now I completely pop out of the subgroup layer. I'm now not in any subgroup layer at all. I'm just within the scope of my initial assumptions. And so I cite the entire subgroup that started from line 3 hyphen 11, and I write negation intro. And I delete my bonus lines. Yeah, awesome. Cool. So this works, and I was risky on line 2 that I wrote this existential, this universal elimination all on its own. My advice to you guys is to do this kind of thing within your subgroup structure, I guess, for the existential elimination. You can see, when we finally do existential elimination on line 10, and we ask ourselves these 3 conditions, does the constant A occur in an undischarged assumption? No, it doesn't, because here is A on line 2, but this thing on line 2 is not an assumption. It's just, it doesn't have the little horizontal under it. Yeah, Daniel?
Why do we have to make the second same assumption again?
Yeah, so this was kind of like, if you didn't assume this thing for negation intro, and if you just had the QA and the not QA, you wouldn't have anything to finish this existential elimination with, because remember, you can't hop out of the existential elimination until you have some psi that doesn't have the constant in it. And it's not like you couldn't introduce the not there existing up here from this negation intro because that's like it's like a subproof higher. So, did you get it to work without assuming this?
How would I know if I got to work?
Oh yeah, that's a good point. Yeah. I can try again to see if I can get it to work. I don't think it would. Let me try. Yeah, I think what I'll do is I'll let you guys get started on the next one. I'll stick around with this and see if we can get it to go. So yeah, start on 10.9, which is a tricky one to start as well, I think. Yeah, it looks like in my notes myself, so I was working on this in August. I distinctly remember I really did legit just think about totally quitting on this problem and not having it on the problem set because it was so hard for me to figure out what to do that I was like, maybe it seems cruel, but I've given you a hint. So a hint and some tasting notes, we might say, because a good natural reduction proof is like a good glass of wine. You have to age it and then savor it. This stuff sucks, right? We don't really enjoy this. We're doing this because we're getting class credit. And you guys, this is a humanities, class for you guys. So fancy that. All right, let me see if I can get this to work without this other assumption. Yeah, I think the problem, guys, is that, so if I did try to introduce my negation right here, just from the QA and the not QA, I just don't follow the syntactic form of negation intro. Because remember, whenever you apply negation intro, when you apply the rule, you pop out of the subproof. And here, my negation intro is at subproof layer 1. When I write this, I'm still at subproof layer 1 as well. I'm not back to subproof layer 0. I can't be because I'm still within the scope of the thing I assumed for existential elimination. So kind of the moral here is you can only pop out of one subproof layer at a time, and you have to work in the reverse order that you assume on. So given that I assume this for negation intro and then assume something else for existential elimination, I know I'm going to have to apply the existential elimination before I apply this negation intro. And there's just nothing that I can apply existential elimination to here because I have these P's and Q's running around. Maybe this is one faster thing I can do actually, come to think of it. So yeah, so maybe Daniel's instincts are good. So yeah, what if we do this? PA and but then I won't have my contradiction. Oh no, I think did we use no, I don't think it's gonna work. I take it back. Yeah, because it's like I could pop out of the existential but there is something that's a P and a Q. But that's not gonna contradict anything above those. I know me on. So yeah. We love problem 10.8. Alright, try to remember how we set this bad boy up. Feel bad, we're probably not going to get to the role-playing paradox. So I guess we should vote. Who's in favor of staying on homework? Who's in favor of role-playing paradox? Oh, you guys prefer? All right, well, cool. Well, then let's just plow through this. I'll just tell you guys how to set these up, and then we'll talk about role-playing. Okay, so you notice you can't really do anything with this premise because it's not an existential, it's the negation of an existential. So you can't really do much. What you do notice, you want to get a universal of an if-then. So remember, you can build up if-thens. You can build up if-thens by starting a subproof, assume, in this case, an instance of the conditional, so assume PA for conditional intro. The basic thought here is that if I can get the conditional if PA then not QA, then modulo my restrictions, I can instantiate that. I can universally instantiate it. So my sub goal is to get if PA then not QA. So now I want to, within this subproof, I want to get not QA. I'm kind of stuck, so I'm like, let's assume a negation of that. So let's assume the unnegated thing. So assume QA or negation intro. So I'm 2 layers deep, and now I need to get a contradiction. And what I notice is I can get PA and QA on conjunction intro, so 2 counts 3, conjunction intro. And now I can introduce an existential. I have an instance of there is something, at least one thing, that is a P and a Q, namely A. So line 4 is existential intro. And now I notice that this thing contradicts my starting premise. So I basically, to get anywhere, I just built the unnegated version of my starting premise so that I could use this in the negation intro. And then, so I just reiterate this thing from line 1. Now I have, in the Q thing, I have a thing and its negation. And so, of course, I can pop out of this negation introduction rule, write not Q, and then I have the thing I wanted from PA, I got not Q, not QA, and then I could write if PA then not QA, and then I could universally introduce. So I think you guys have proof checker on this, so we'll leave it here and we'll go to the next one. Is the strategy clear? Cool. All right, this was the hard part, just to set it up. Once you have this, then the rest of it is chill. All right, so 10. Okay, so 10, you see there's no assumptions. There's no premises. No premises, so this thing is a tautology. It is a logical truth. So notice the main connective is conditional. So we're definitely, our last step here is going to be conditional introduction. And the sentence is telling you the structure of the proof has to be, you assume the antecedent. So since it's a tautology, we know we have to start a subproof immediately with no premises. So I have to tab in once, and I assume, not premise, but assume this thing for conditional intro. And now my goal is to get this thing. I think, all right, I'm probably pretty stuck. I guess I could immediately do an existential, do something with existential elimination. So maybe that is the thing to immediately do, is write down an instance of this. So BA, and assume this for existential elimination. And now I'm going to assume the unnegated thing of what I want. So this is another, so again, 3 layers deep. And assume this for negation intro. 3 layers in. Now I can instantiate this, and I can instantiate it with A, so BA, colon, this is line 3, that's universal elimination. And now I have my BA from line 2 that I can reiterate. So now I got my contradiction, so now I can pop out of this 3rd subproof and write this thing not BX. And so this was lines 3-5, negation intro. Cool. And now this thing doesn't have the constant A appearing in it, so this can be the thing that I derive with existential elimination. So now, so I am now just one layer deep. Yeah, I'm going to pop out my second subgroup I did for existential elimination, rewrite this, cite the existential I eliminated, and my second subgroup 2-6, right, existential elimination. And now we're like, great. I got from my antecedent, I derived my consequent that I wanted, and so I got the whole thing, and I can pop out of any subgroups, and I can write lines 1-7 conditional intro. Awesome, dope shit, cool. So we got that. All right, so let's do a roll call. I'll leave this up so you guys can write. I was going to have some beautiful quotations from Wittgenstein's Philosophical Investigations, which is one of the sources of this puzzle, this role-defined paradox. So we previously talked about Wittgenstein from World War I, where he was in the trenches and doing this quasi-metaphysics of the structure of the world as the logical structure of language. This is the later Wittgenstein, World War II, where still very anti-philosophical, but more mature in a way, less hubristic. You know, under less impression that one could completely destroy philosophy. And much of the book, the Investigations, is concerned with the nature of sameness. The nature of sameness is really connected to following a rule. Because when one follows a rule, they're being asked to, in some sense, do the same thing over and over again. So there's many ways that you could set up the puzzle. I think this is the case where it's so frustrating in a way, because it seems like it should be very simple what to say. So, you know, you guys are my students. You know, instructors can ask students to do things in an intellectual setting. So imagine I ask each of you to write 2 after 2 over and over again. So I just say, you know, keep writing 2s. That's it. So the rule in this case is to write 2s. You could do other scenarios with like add 1. You know, if I was like start at 1 and just add 1, then you'd write 1, 2, 3, 4, 5, 6, 7, and you keep adding 1, blah, blah, blah. Now imagine I ask you to do this, and at the like 1,000th instance, you start writing 3, 30, 30, and so on. And at the 2,000th instance, you start writing 4s. And so I watch you do this, and I'm like, whoa, dude, like, I said write 2s. And you're like, I'm following the rule. I'm telling, you know, you said keep writing 2s, I'm doing that. And to really get in the grip of like what's at issue here, imagine that, you know, there is some finite number of instances of any rule that anyone has ever followed out. So if I asked you to just keep writing 2s, there would be a point at which you had written the greatest number of 2s in a row as anybody in the world ever had. And so at that point, you wouldn't, you know, you wouldn't be able to say, oh, I'm doing what so-and-so had done before. You would reach a point that no one had ever come to before. Now, you might say to me, well, you know, isn't the fact that this is wrong, isn't it obvious because I intended you to just keep writing 2s? Well, what's at issue is what did I intend for you to do? And if nobody had ever, if, you know, instead of 1,000, you know, make it just some large finite number that no one had ever made to before, like, you know, Google or something. Clearly, when I asked you to just keep writing 2s, I couldn't run through all of those instances. I couldn't have made it that far because we're just stipulating nobody's ever made it that far before. So of course I couldn't have made it that far either. And so there's no way in which I could have intended for you at any, you know, far out place to write a 2, because we stipulated nobody's ever made it that far before. So the puzzle is, on what basis do I get to say to you when you start doing this that you're wrong? On what basis do I get to say that you are following the rule incorrectly? And you have to answer that question in a non-question begging way. You have to appeal to something that doesn't itself just presuppose what's in question. You guys have any thoughts on this? Does anyone feel like they're in the grip of a puzzle? Or do you think Harris is dumb? It's better to think that it's dumb, honestly, because it's I mean, you know, like most philosophical puzzles, nothing fruitful comes from thinking about this. It's not like you really solve anything. If you're in the grip of it, then it's really just disturbing. Because you start to worry about the grounds for everything that we're asked to do. Seemingly everything we do, everything you mean, falls prey to a Wolfram paradox. You know, it's like, right now I might say to you guys, have a good rest of the week. But like, what do I mean by that? Because the meaning of this word is determined partly by its previous instances, but we frequently just go beyond what has ever come before. So who's to say that when I say to you guys, hey, have a nice week, I don't actually mean, I hope you fall in a ditch. You know? It's the same puzzle. Cool. So yeah, maybe next week, anybody's here next week, I might put some beautiful quotes from the investigations into the slides. Oh yeah, and I have office hours now, and on Friday. And of course, if you guys have any questions, feel free to get in touch, and feel free to look at these tips in the slides if you need, if you're finding you need guidance on the problems. It's nominally due Saturday at 11 p.m. If for whatever reason that causes you personal hardship, feel free to get in touch with me. I think probably on Wednesday we'll do probably 4 of the harder ones. It's like 8 of them have auto checking on. It's only the last 4 that don't. So maybe we'll just like do those in class, and then I feel like you guys should be good to go. So, and that'll be my thank you for coming Thanksgiving week. Which it's always interesting, right? So we're doing identity. Basically, we're going to add a distinguished predicate to quantifier logic that will let us say of 2 things that they are the same. And so that really means there's a bunch of other stuff we could say about multiple quantifiers, some examples and like ambiguity. We might on Wednesday do some of this stuff, donkey sentences. Donkey sentences are, don't be a jackass, learn your donkey sentences, we might say. So we might discuss stuff like that, but a lot of it is just kind of intuitive, and I feel like you probably don't really need it talked through explicitly, if at all. So that's why we'll jump ahead to the identity. All right. So we have, a formula for script A could be anything, and it has some free variable x. This is expressing some property. And if you have 2 free variables, then you're expressing a relation. And likewise, if you have three free variables. Now, when you bind these free variables with quantifiers, then you get a sentence. You get something that could be true or false. And what this schematic form says is this thing is true, provided that every pair of objects, alpha and beta, stand in the relation expressed by script beta. So in other words, provided that every pair of objects, alpha and beta, are in the extension of beta. Remember that this property beta, it will have an extension, which is just a set of ordered pairs. And so if it's the case that every pair of objects, alpha, beta, are in that thing, in the extension, then you have a relation. It's a bang. So similarly, if you bind it with 2 existentials, you get a sentence, and this would be true provided there's at least 1 pair of objects, alpha, beta, in your domain of discourse. Remember that all of this is relative to a domain of discourse, and provided there was at least 1 pair that was in the extension of script B, then it'd be true. And so you can see, of course, we could also have an existential and a universal, or we could have a universal and then an existential, and those would have different truth conditions. And so that's basically what we're going to walk through briefly here before we get to the identity. So imagine that we let A, just regular A, stand for admires. So AXY is the relation of X admiring Y. Then if we looked at the sentence, every x and every y are such that x admires y, then if this was true, then that would mean that every pair in your domain of discourse stood in the relation of admiring, from alpha to beta. And so this would just be a sentence schematization of everyone admires everyone. So if you guys on Carnap had, a little sentence and it was like schematized, everyone admires everyone, this is what you would write. You'd write for all x, for all y, a, x1. And in particular, what this includes is the scenario where every person admires themselves, because those people are in there. Alpha and beta don't have to be distinct. So, many of these ordered pairs are just going to be, if we let, people, I'll be little j, and we'll have little m for Manny, little g for Gerardo. In the extension of A, if we have everyone admires everyone, we'd have j comma j, and we'd have m comma m, and so on. You would never have any other things after j, because I don't admire any of you. No, I'm just kidding. So if you j comma all the other things too. But the important thing is the self-admiration is in there, unless you say otherwise. So we have all the pairs alpha comma alpha in the extension. And so this sentence is true if and only if all of these pairs satisfy not if, you'd also need the alpha comma beta ones too, of course. So everyone admires themselves and not just everyone else. So if you wanted to symbolize everyone admires everyone else, then you would need the identity predicate. So that's one thing we'll do today. Because basically you'll have to be able to say, for all the x's, for all the y's, if x is not equal to y, then x admires y. And so we'll use identity to do that. Similarly, if we have the sentence, there's at least one x and there's at least one y, such that x admires y, this is true provided there's at least one pair alpha beta in the extension of A, and so provided at least one person admires at least one person, but this doesn't have to be a different person. This is the key thing. It could be true if there was just one person admiring themselves. As a matter of fact, because we practice radical self-acceptance in this classroom, I do admire myself. And so I would be a truth maker for this sentence, there's at least one person that admires at least one person. And so provided any one of you admires yourself, you would also be a truth maker for this sentence. So if you want to symbolize something like someone admires someone else, then again you would need the identity predicate. And you'd have to say, there's at least one x, and there's at least one y, such that x is not the same as y, and x admires y. And that x is not the same as is basically a negated identity. And so that's what we'll be using. You'll probably use the negation of the identity more often than the identity, because again, as we'll see, the identity it's kind of a trivial predicate in a way, because it's like everything bears identity to itself and nothing else. So it's just, every object in your domain of discourse gets this special little gold star property that says me. This is the me property, and everyone has their own me property. Okay, so we can also, of course, mix and match the quantifiers, and so really, I think this is probably going to have like 4 things. So this is saying, for all x, there's a y, such that x admires y. So this is saying, everyone admires someone. For everyone, there is at least one person they admire. So everyone admires someone, possibly themselves. Now, if you instead swap the order of the universal and the existential, but keep the x-y relation the same, now we're saying, for all the people, there is somebody who admires them. So this is saying everyone is admired by at least one person. So that's what this schematizes. Everyone is admired by someone. So notice that by switching the order here, we get something like, I really don't know. It's good that Michelle's not here in a way, because I'm so bad with linguistics. I'm sure that she'd be like, oh, this is the relevant part of speech, blah, blah, blah. I don't know. I mean, here it's like, yeah, here, you know, you're admiring someone, someone's the object of the admiration. Here you're being admired by someone. So this someone is the person doing the admiring. And this everyone is really, in some sense, the object of the verb to admire. I don't do linguistics. So I did get drinks with 2 linguists on Saturday, but we talked about the role of linguistics in interpreting constitutional law. So it's not that they helped me understand any kinds of sentences like this. Allegedly, we need more linguists in the courts to get around these ambiguities in the law. So what if we instead do, there's at least one x such that for all y, axy. What do we think this will say? Yeah, we got people coming in droves. This is great. You know, I thought Thanksgiving week was going to be really sad. You guys got me all pumped up, and then Wednesday is going to be a shit show, right? Wednesday is going to be Gerardo. Are you guys going to be here Wednesday? Oh, yeah, okay. That's great. Anybody else going to be here Wednesday? No. Yeah. Oh, man. Okay. Cool. Yeah, maybe. Yeah, Henry is maybe. That's great. So we'll take maybes. Yeah, yeah. All right. If someone want to take a stab at what this means. Or again, capital A is admire.
There exists at least one person that admires everyone.
Yep, yeah, there's at least one person who admires everybody. Can we think of somebody like this? I don't know, maybe if we're thinking that Joe Biden is really trying to play the middle America and be a consensus candidate, then Joe Biden on the trail might say, you know, I admire every American because in this great nation, we all stand or fall together. So someone admires everyone, including themselves, and I hope Joe Biden admires himself, you know. Let's go, Brandon. All right, there's at least one y such that for all x, axy. So now we flip these. So again, we're going to have this, you know, by someone thing. Only I guess it'll be a by everyone. So we're saying there's at least one person who's admired by everybody. So this is someone of, you know, universally admired. Who is universally admired? Maybe Gandhi. I don't know. You know, it's hard to think of someone who's admired by everyone, including himself. So each of these is distinct, and so the key thing for you guys is when you do your problem sets, sometimes you will have to have multiple quantifiers right next to each other. Just keep in mind that these things are not in general commutative. That in general, the order, at least if you have a universal and an existential, the order you put them in can really change the meaning of the sentence. These 4 sentences mean completely different things. And so you got to keep this stuff straight. But it's very natural. There's nothing really here to memorize. You just look at these and you think through it. And if you have the skill of schematizing, then you know you'll never make a mistake like this. So, any questions on alternating quantifiers? Cool. All right. So this is a cool example. So for anybody who's done some math, if not, you can space out. But there's a distinction in analysis between pointwise continuity and uniform continuity. And with these quantifier orders, you can really make this precise. And so when you're saying something's pointwise continuous, you're saying for all the epsilons and for all of my x and y's, you know, that my function takes in, there's at least one delta, you know, for a given x and y, such that if the distance between x and y is less than delta, then the distance between their evaluations by the function are less than epsilon. So in the pointwise continuity, you can have a different delta for every pair of x and y's. Whereas with uniform continuity, you now take there exists a delta operator and you move it before the x and y that the function acts on. So here you're saying for all the epsilons, there's at least one delta such that for any x and y, if x and y are less than that delta, then the evaluation of the function distance between those 2 points is less than epsilon. So here, the delta is a lot more, you know, it's a lot more special because this at least one delta, this relation is going to hold for any of these x's and y's. And so you think, well, that's really different, you know, so like big difference between pointwise continuity and uniform continuity. This example is going to be on the final. No, I'm just kidding. It's not a math class, so if this is not illuminating, then you will summarily forget it. All right, so a bit about multiple determiners, and this is a little language thing. So again, it's great. Michelle's not here, so I'm playing it clean. Nobody can call me out, unless any one of you knows linguistics, in which case please speak and inform us. So determiners, what are they? It's a good question. I went to Wikipedia, and this is what Wikipedia told me. So determiners include, for our purposes, quantifiers and also indefinite or definite articles. Possessives and demonstratives as well, but we don't really have, concrete language for them so much in our quantifier logic. So some examples of determiners are many and some. These are quantifiers. A is an indefinite article. The is a definite article. We have possessives, his and their, and demonstratives, this and that. So this is a demonstrative, and that is also a demonstrative. We use demonstratives all the time. We love demonstratives. So determiner phrases, they just take a determiner and they put it with a noun. And sometimes you modify the noun with an adjective, and that's how you get a determiner phrase. So something like all heroes, or a cape, or some woman, or the donkey. So these are examples that in some sense figure in the slides. So the donkey, we may return to the donkey on Wednesday, or maybe today if really blowing through stuff. You never know, right? So the issue here is, well, what if you have a sentence that is more than one determiner phrase? How would you systematically schematize this? And so you would just handle each of the determiners separately, and whenever you handle one determiner phrase, you're basically just replacing it with like a variable, and then now it's figuring in some other determiner phrase that you would handle the variable. So you're basically identifying some kind of recursive structure. So, and then when you have it down to one determiner, then you just do what we were doing for single quantifiers. And then you get formulas that they express these properties and relations. They themselves have quantifiers, and so you have multiple quantifiers. So this is very abstract, and to be honest, this is an attempt at trying to systematize what we naturally do, but in all my life when I've done this stuff, I've never had this little, direction sheet in mind. So it might help you, it might not. I feel like if this kind of thing doesn't come naturally to you, then you might want to study this, and maybe it would help you out. If ultimately these kinds of problems, you just look at them and you fiddle with them and then they fall into place, well then great, I feel like it's not even worth trying to formalize your reasoning. But this is an attempt. So here's some examples, and you'll get to see, does this make sense or not? So we have a sentence, all heroes wear a cape. We have two of these determiners. So what we're saying is all heroes satisfy the property of X wears the cape. So we're going to handle this determiner phrase, all the heroes, and we're going to just treat this right now kind of like as a variable. And we're going to say, for all the x's, if x is a hero, then x has this property. X wears a cape. And so this is just what we've been doing, since we introduced quantifier logic, so this is chill. This is like all heroes blah. For all x, if x is a hero, then blah, x blah. And then you handle x wears a cape, and you think, okay, how do I get that? You're saying there is some y, so here we're using a mixed domain in this case where we have people and we have articles of clothing. And E is the property of being a cape, and capital R is the property of X wearing Y. So here we're saying there is at least one thing such that Y is a cape and X wears that thing. X wears the cape. And so then you just put this stuff together, and so to schematize all heroes wear a cape, you're just saying for all X, if X is a hero, then there's at least one thing Y such that Y is a cape and X wears Y. So, and we just followed the advice that was on the previous slide, but you might not even remember what the advice was on the previous slide. So this might just seem sufficiently natural that you're like, we're good. And one thing to note, harkening back to some material that we noted briefly, is the one case where a quantifier can be pulled through a conditional is if the quantifier is in the consequent. So this is the little mnemonic here was quantifiers in the consequent commute across conditional. So the little mnemonic here is consequent, commute, conditional. Got lots of C's. So you can pull this existential across if you want to, and you could rewrite this as, for all the x's, there's at least one y, such that if x is a hero, then y is a cape, and x where's y. There's probably some other little finicky restriction about what's in the antecedent, and presumably the thing in the antecedent can't have any instances of y, but I think that's going to be trivially satisfied based on our, well, I guess it wouldn't be, yeah, so it wouldn't necessarily. So it is important. This little rule applies provided that there wasn't already a bound instance of y here. Because, that would be, then you'd have two different y's playing two different functional roles, so you would mess stuff up if you pulled the variance of the y across that conditional. So yeah, so you could write it this way instead, and now this really isn't our alternating quantifier form that we've just been talking about. Any questions about this? Cool. So here's another example. All heroes who wear a cape admire Greta, our hero Greta, who's trying to save the climate, save us from destroying the climate. And Greta, we gotta get Greta a cape with, Mother Earth on it, right? That's what Greta needs. All things that satisfy X is the hero who wears a cape, admire Greta. So we've just done all heroes who wear a cape, and now we're just throwing in this further thing. For everything that has this property, X is the hero who wears a cape, they admire Greta. So if X, basically for all the X's, if X is a thing with this property, then X admires Greta, or Greta's the little G. So to get X is a hero who wears a cape, we just have X is a hero, and there's at least one thing such that that thing's a cape, and X wears that thing. And so here we're just saying, for all the X's, if X is a hero, and there's at least one thing Y, such that Y is a cape, and X wears that thing, then X admires Greta. And very important that this X here is in the scope of the universal quantifier. So we have this leftmost parenthesis closed right there, so that the X is bound by this universal. And again, if you wanted to, you could pull out the there exists a Y here, because, oh no, shit, you couldn't in this one. Yeah, you couldn't, so this is, yeah, so this is actually a good example of yeah, I think you basically have to write it this way. If you tried to pull out this existential, it would become a universal, and I think something else weird happens, so I say just don't do that shit. Don't, yeah. So if you naturally have to put a quantifier in the antecedent of a conditional, just leave it there. Don't try to play with it, unless you want. In one of these slides, there's a rule on how this stuff converts, and I know at least you flip it. I can't remember if you have to do something else as well. Maybe it's just that you flip it to a universal, but nobody's asking you to write these sentences with the quantifiers alternating next to each other, so why make it more complicated than it has to be? All right. So sometimes the word any is existential, and so this can throw you. And also sometimes, as we'll see, a or one is universal. We'll do some examples of that. So, and this is where, you really can make mistakes. I myself sometimes make some mistakes, but we accept the mistakes we make, as we say. Perfectionism is the enemy of the good, and so we must be happy when we make mistakes as an opportunity for growth. kind of just accepting the limitations of our finite minds. Oh wait, I shouldn't show you the answer first, right? So every cape is worn by hero. So here, this any is functioning as a universal. Any cape is worn by hero. We're saying something like, for all the things, if it's a cape, then there's at least one Y such that Y is a hero, and Y wears that thing. Any cape is worn by hero. So it's got the idea here is something like, you give me at least one hero, that hero would wear any cape. That hero would be willing to wear any cape. So for all the capes, this at least one hero, would wear any of them. So no hero wears any cape. Here we're saying for all the x's, if x is a hero, then it's not the case that there is at least one cape that hero would wear. So I think another way, you might prefer to put it this way, I think I naturally, when I have a no blah thing, I think I naturally do a negated existential. So you might find the second way more natural. We're saying it's not the case that there's at least one x such that x is a hero, and there's at least one y such that y is a cape, and x wears y. And if you push this negation through using the quantifier De Morgan's, you would convert this existential to a universal, then you would negate this conjunction, it would become an or, and then you would remember the truth conditions for if then, and you could write it as an if then. So you could work through that, and it all works out. No hero wears every cape. So here we're saying, so it's a no one, so you could do it either way. And so we're basically saying, for all the x's, if x is a hero, then it's not the case that for all the capes, x wears that thing. That's what we're saying. So for all the x's, if x is hero, then it's not the case that for all the y's, where y is a cape, that x will wear that y. So alternatively, you could say it's not the case that there is at least one hero, such that for all the y's, if y is a cape, then x wears y. So either way would be fine. And again, if you wanted to get rid of this conditional here, you could push this negation through, get an existential. Yeah. Okay. Any questions about this? Cool. So now we're into identity. So this is what we're in for. So hopefully now we've given explicit background on these multiple quantifier things, and this will naturally pop up in the identity question. So essentially what we're doing is we have quantifier logic, and quantifier logic handles any predicate that you can think of. We're basically just going to introduce a distinguished predicate, call that the identity predicate, and we're just going to say we can always help ourselves to this predicate whenever we go to construct a model or give an interpretation. So on the left, we have Greta admires everyone, where remember, without identity, this includes the scenario where Greta admires herself. So the little directed arrow is, remember these are ordered pairs that are in the extension of the predicate admires. This is the relation admires. So 1 arrow to 2 means 1 admires 2. The fact that there's no, it's kind of interesting. I feel like maybe this diagram is wrong. Oh, this is Greta admires everyone. Yeah, okay. So Greta's 1 in this case. So Greta is the number 1, also little g. Remember, you can have multiple names for the same thing. And Greta admires 2, and Greta admires 3, and Greta admires 4. In this model, 4, whoever they are sickos, and they don't admire Greta, and they should be banished from the earth, we might say. But the fact that there's no arrow from 4 to 1 means that 4 is not admiring 1 in this model. But Greta's admiring herself. Now, if you want to say Greta admires everyone else, so that you don't have this little self-referential, self-directed arrow from Greta to Greta, then you need this identity predicate. So this is for all x, Greta admires that x, and the order here matters. You need to have the little g on the left. Now, we want to say for all x, if x is not Greta, then greta admires that x. So this is the sentence we're trying to schematize, and so we just need a predicate for is not Greta. And so this is just negation of identity. Greta is identical to Greta, nothing else is identical to Greta. So the way we'll write this is, it's a little kind of strange notation, you'll just have to get used to it. Twiddle x equals g, this is x is not Greta. So probably the more natural thing you would write, and if Carnap was better, we would write this as well, but you know, we work with the Carnap that we have, right? So naturally you would write something like, for all the x's, if x does not equal g, then Greta admires that x. But we, in Carnap land, we do not have this symbol. So that symbol is not available to us. So we have to write basically this thing that just means thinking about x equals g, saying something like it's not the case that x is equal to g. And so that's the same as saying x is not equal to g. Alternatively, you can think about it as you're saying not x is equal to g. Well, if not x is equal to g, then x can't be equal to g. But it's just kind of weird, you know, I don't really know, like, this is a negation symbol, right? What does it mean to negate a variable? So I would just think about this as some kind of syntactic convention that we've chosen because in Carnap we don't have a not equal sign. So you write that, and we'll talk about some of the restrictions on writing this stuff, common mistakes that you guys might fall prey to. So here's our identity predicate, equal sign, we know and we love it. So you write it between these arguments, you know, specifically these variables or these terms. You don't use parentheses, so there's never any parentheses around the x equals g thing. And you don't have to mention it in the symbolization, we're just, you know, we're given to it. We're given to it by the glorious nature of each of us as a unique individual. We bring identity to the table. So this is a logic class where we're doing identity politics. And yeah, so it's distinguished. So you can't, unlike many of these predicates, right, like P in one model could mean a totally different thing in some other model, identity will always mean the same thing. Now, what does it mean to always mean the same thing? Well, that's kind of a question about identity, and it's a rule-following paradox. And none of us solve the rule-following paradox. If you solve the rule-following paradox, let me know. You could win $1 million. We should have like a, you know, there's the Clay Millennial Prizes for these hard math problems. We should do some of those for hard philosophy problems. And you might think, well, there's some issues here, right? Who would adjudicate when you solve the problem? The philosophers. But the philosophers often don't agree when a problem's been solved. That's, you know, the nature of philosophy is people disagree about what it means to solve a philosophical problem. So no one would ever get the money, right? It would just sit there. So yeah, in the identity thing, the extension of equal, it's just all the pairs alpha alpha where, again, I mean, it's just like, yeah, it's a hard, we're in kind of a circle. Like I want to say all the pairs alpha alpha where alpha is equal to alpha, but that's exactly what's in question here, is what does it take or what does it mean for alpha to be equal to alpha? Somehow we know what this means and we do this, so that's great. But to really, you know, to justify what we're doing in a non-circular manner, I don't know if we can. You might just think this is part of, you know, the human condition. We've learned how to do this. So A is equal to B is true if and only if these two names, A and B, refer to the same object. So remember, the domain of discourse is actual objects. It's like things, and then we have names for those things. We have constants, and the constants refer to objects in the domain of discourse. So it's a very Platonic picture we have going on. So x is equal to y, these are variables now. This is satisfied by all and only the pairs alpha alpha, where we put in for x the same thing as we put in for y. Now not x is equal to y is satisfied by any pair alpha beta, provided that alpha and beta are different objects. So this is our formal definition of the satisfaction conditions of this not equal to relation. So it's playing the intuitive role of a not equal sign. We write it like this because I don't know, man. We need more symbols on the keyboard. So, any questions about the identity predicate? Very intuitive, very simple, but also puzzling in a way. I might, if we're really killing time, on Wednesday I might bring in some beautiful Wittgenstein quotes about identity and the puzzles arising about sameness. So we'll see if we work on this slide. We might not, other things might arise in our lives that would take us away from such beautiful quotations. So these are some mistakes you might fall prey to. So these are things you're not allowed to do, although they might seem like natural extensions. We just, we make some conventional syntactic choices and we try to keep things clean and constrained, and so we are just going to say you're not allowed to write this, and the real cash value of you're not allowed to write this is Carnap is not going to tolerate this bullshit, so don't plug this into Carnap. So x is equal to not y is not grammatical. You can only put the little twiddle in front of the formula. Y is not by itself a formula. Y is just a term. So you also, sadly, can't do not parentheses x equal to y. This thing's also not a formula. You might think, why isn't this thing a formula? Well, this is really our reason. But again, this is the kind of common mistake we're making all the time, myself included, is remember that the atomic, so the QL atomics, these include the SL atomics, which are just our atomic sentence letters like A and B and C, etc., with no little terms after them, and also includes the one-place predicates, so like PX and PA, and two-place predicates, so like SXY, SAY. So these things are all atomic sentences, or not necessarily sentences, they're atomic well-formed formulas. Atomic well-formed formulas of QL. And remember, just like in sentential logic, we never put parentheses around atomics. The parentheses only popped up when you added binary quantifiers. Here, these one-place, two-place, three-place, etc. Atomic well-formed formulas, they don't have parentheses around them. Basically, x equals y is if we could, instead of equals, we could say I'm going to use capital I, and then this thing would be IXY, is what this thing would be. And so you would never put parentheses around something like this. And so just like here, this is an atomic well-formed formula that you just can't put parentheses around it. It goes against our rules. Somebody was like, maybe something cool is happening in this class, and then they heard whatever the hell I was saying. F no, I'm out of here, you guys can leave it, and you're not trapped, right? You're here because you want to be, and I appreciate that. So, all right, so Carnap will not tolerate this. So try not to make mistakes. Obviously, if you make a mistake like this, me or your gentle human will be grading, and I will, probably look kind of funny. Cool. So something else and everything else. I think these are just other examples of things that are sometimes a little confusing. So just try to remember that even when we have these two variables and they're different variables, we're saying there's at least some x and there's at least some y, such that x admires y. This doesn't entail that someone is admiring someone else, because this can be true even if there's just one thing in your domain of discourse that admires itself. So it just means someone admires someone. Someone admires someone is a totally different sentence than someone admires someone else. To get the else in there, you gotta use this identity predicate. So if you want to add in the someone else, you gotta say, by the way, x does not equal y. It's not the case that x is equal to y. So you gotta throw that in there, and now we've symbolized someone admires someone else. There's at least one x, and there's at least one y, such that the x and y are distinct, and x admires y. So similarly, if you just write for all the x's, for all the y's, x admires y, this says everyone admires everyone, including themselves. So if you want to say everyone admires everyone else, then you again have to add in it's not the case these things are equal. And then you get to say, for all the x's, for all the y's, if x and y are distinct, then x admires y. And so this is saying everyone admires everyone else. This excludes the case where x admires x. Questions about this? Cool. Let's see. Okay, so in between, so distinguishing something else versus everything else, you can see here in this example, here we have a conjunction, here we have a conditional. Again, you could try to write down some rules about what we're doing here to formalize this. I again think it's probably, it's going to click and you're going to get it, you're not going to make mistakes. If it doesn't click, I think you should just keep doing practice problems until it clicks, because the odds of you remembering whatever the hell advice is on the slide are probably less than, you just learning how to get it to make sense, right? But here we go. So we're trying to distinguish these two things. Everyone admires someone else versus someone admires everyone else. And the basic thought here is, okay, well, here the existential is closer to this connective, and so it's a conjunction. Here the universal is closer to the connective here, and so it's an if-then. Maybe the mnemonic here, it's not really a mnemonic. If it were, it'd be a terrible mnemonic. Is just remember that the horseshoe, the if-then symbol, appears more often when you're talking about universals, because the basic thing that we're using horseshoe for with these universal quantifiers is to say things like every f is a g, and this gets schematized as, for all the x's, if x is an f, then x is g. So you're more likely to have a horseshoe if your conditional, the universal quantifier is the closer one to that connective. Okay, so in a mixed domain, we're basically just, here we were implicitly talking about people. We didn't have to say that these things were people because we implicitly took our domain of discourse to be people. Now imagine we had a domain of discourse that didn't just have people in it, it also had other things like jackasses. And I assume, not all jackasses are people. Some jackasses are just donkeys after all. I think in our running examples, we're gonna have clothing in a lot of them. And so domain of discourse, that is articles of clothing, there's a lot of moral statements that are controversial. I think one that is not controversial is that my slippers are not people. We're not yet in the era where my slippers are not people. So, I can step on them all I want, and I'm not doing anything morally bad. So if we were in a domain like that, we'd have to explicitly say whether or not anything was a person. So if we want to, schematize everyone admires someone else, we're now going to have to say, for all the x, if x is a person, then there's at least one y such that y is a person, and x is not equal y, and x admires y. So this is the same sentence, everyone admires someone else, as here, everyone admires someone else. And here we're in a domain that just has people, and here we're in a domain that has things other than people, and so we have a person predicate. And so you notice it has the same form as this one, it's just more complicated. We still have the universal up front for all the x's, but now we're saying, just like here, every f is a g, we're saying for all the x's, if x is a person, then there's some y such that y is a person, and we want to say that someone else, so we have to get in there that they're different, and then we have to say x admires y. So it's just more convoluted. And many of the homework problems will be convoluted in a similar way. So, but natural, so you just think through what this stuff means. So someone admires everyone else. Here we're saying there's at least some x such that x is a person. So we tack that on, x is a person, and for all the y's, if y is a person, and again, if these things are distinct, objects, then X admires Y. So again, it's the same structure as the simpler case, but just with people predicates thrown in. Any questions about this? Cool. Okay, other than and except. So someone other than Greta is a hero. How would we schematize this? Someone other than Greta is a hero. So we basically want to say there's at least one hero, but we want to say whoever is the at least one hero is not Greta. So we're saying something like there is at least one X such that X is not Greta and that X is a hero. That's what we're saying. So there's at least some X such that it's not the case that X is equal to Greta and X is the hero, and notice there's no extra parentheses around this equal thing. So we're following our syntax. Everyone other than Greta is a hero. This is a false statement because Greta is a hero, you know. But if we want to schematize this, then we're saying for all the X's, if X is not the same as Greta, then X is a hero. And this is the same as saying everyone except Greta is a hero. So for all the X's, if X is distinct from Greta, then X is hero. So someone other than gets this treatment, and when it comes to everyone other than and everyone except, these are schematized in the same way. That's the cache value of this slide. Questions about this? Cool. All right, so basically what we're doing is we're just running through a large swath of natural language English phrases that probably have fancy names in linguistics that now we can schematize with quantifier logic plus identity. So there's probably a way in which, you know, if any of you are like flashcard people, this is stuff you could write down on flashcards for these various expressions. You could have, you know, flashcard for each expression. I don't know if it'll really come to that. I mean, a lot of it's just so natural that you might feel like you don't have to memorize anything. You know, definitely before the final, come to class, I'll let you know if there's anything to watch out for. But yeah, in principle, you know, if you were going to make a cheat sheet for the final, then on the cheat sheet, yeah, it would make sense, I guess, to write down these various expressions, have them there, you know, for quick reference. So, because there is a sense in which it's not like you can like plug and chug per se, but it's kind of like this stuff is giving you the truth conditions for these various kinds of sentences, and then if you had in front of you an explicit statement of the truth conditions, then you would look at a new sentence and you'd say, oh, okay, this sentence has these little words in them, so it must mean blah, blah, blah. So I schematize it this way. That's the strategy. Okay, so no one other than Greta is a hero. And we're thinking, what's different about you know, this and the other stuff? So we get someone other than Greta, we get everyone other than Greta. Here we're saying no one other than Greta is a hero. So we're at least saying that if somebody's not Greta, then they're not a hero. We're at least saying that. And so, yeah, one way you could put that is, it's not the case that there is somebody such that they're a hero and they're distinct from Greta. And so alternatively, for all the people, if X is a hero, then X is equal to Greta. That also means no one other than Greta is a hero. So again, you could do the little quantifier conversion trick. And you could convert this to a universal, negate this conjunction, and then at the disjunction, and you remember the truth conditions for conditional, and these will be the same. So this actually is something that I think I have a hard time remembering the difference between these. So this possibly actually could go when I go on your cheat sheet. So only Greta's a hero. This has additional content. So when we say no one other than Greta's a hero, we're making this weaker claim that it's not the case there's somebody that's a hero and is distinct from Greta. Whereas when we say only Greta is a hero, we're saying the thing we said before, no one other than Greta is a hero, and now we're making an additional claim. We're also saying, and Greta is a hero. So the singular only has more content, more logical content than no one other than Greta is a hero. Now, I mean, like, I don't know, you might disagree with this. Like, you might think this is like a linguistics thing at this point. We're kind of in like, what are people's intuitions about natural language? And there's probably some empirical fact of the matter if we survey people. And, you know, we show them this sentence and ask them to write down its truth conditions, and this sentence to write down the truth conditions, whether or not people would, by like majority, disagree. But this is a logic class where you play little logic games, and so, you know, it's kind of, I guess, it's neat to think we could have a distinction in language like this, and so we'll take this seriously. In a similar way that we treated unless, where we looked at unless and we thought, unless I don't understand English, this just doesn't seem like the right translation of unless, but we rolled with it, right? So we're gonna roll with this as there's a distinction here. So when we say the singular only, we have to tack on and also. Yeah, man.
Would it also be valid for the first phrase to say, for all X, if X is not Greta, therefore they're not a hero?
Yeah, let's see. So things get subtle, so we have to be careful. So we're considering for all the X's, if X is not the same as Greta, then X is not a hero?
Yeah.
Okay. So yeah, this would be exactly the same because this just is the contrapositive of the conditional in the thing written on the slide. So this is the contrapositive of if X is a hero, then X is equal to Greta. And so you can always do substitution of logical equivalence within a quantifier expression. So we don't have a derivation system that'll let you do that, but at least when in your own thinking, you can always take anything that's a QL well-formed formula, and you can replace it with any QL well-formed formula that, by the lights of sentential logic, would be logically equivalent. Yeah. So, totally also good. Yeah. Cool. And then, yeah, so another way you could write this as well is with a biconditional. So, I mean, maybe you guys might end up preferring this. I think I myself am probably not going to write these biconditional things, but, you know, maybe this is what the cool hip young people do. So for all the X's, X is a hero if and only if X is equal to Greta. And so this builds in the content that, by the way, Greta's a hero because, of course, in our domain, we're assuming that there is Greta. We've named little g, so there's Greta. So when we say this universal is true, what we mean by that is it's satisfied by everything in our domain. In particular, it has to be satisfied by little g. So when we plug in, you know, so consider g for x, then our expression here that we would evaluate would be hg if and only if g is equal to g. And so g is equal to g, this is true. And so if this if and only if is going to be true, then this thing over here would have to be true as well, and that would just be saying that little g is in the extension of the predicate g. So in the set of things that are, in the extension of h. So in the set of things that are heroes, little g is in that extension. And so that's why the biconditional on its own builds in this additional Greta is a hero. So only Greta is a hero. Any questions about this? I think this sort of thing will matter on some of the homework questions, and so we'll probably do some examples like that and see it in action. And we'll hope I have my shit together, don't screw up, right? Some of these too, I mean, it'd be a little tricky, right? Like, you know, I think this is hard to remember that, yeah, no one other than Greta is a hero is slightly different than only Greta is a hero. Right. But you know, it's still not biology class, right? It's not like we're like memorizing like the heart tissue structure, whatever the hell. So what's the Krebs cycle? You know, you're not memorizing the Krebs cycle, so great. I had to do bioengineering, and I had to memorize the 23 amino acids. Like, whoa, you know, you're probably going to do this, Henry. You don't have to memorize amino acids. Have fun, you know? Yeah. You got to keep your livers healthy, guys, so that they can make amino acids for you. You know, the liver just does it. So why do I need to memorize it? You know, the liver's doing the work, not me. Take your vitamins. All right. So uniqueness. So this is a fun one, and this one is natural. So I feel like there's nothing really that strenuous to remember here. So when we say this thing without any identities, we're just saying there's at least one hero. But if you want to say there's exactly one hero, then we have to do a bit more work, but it's intuitive. So we're saying that there's at least one hero, and we're also saying for anybody else, if they are not this thing, then they're not a hero. Or alternatively, you're saying for anything else, if they are a hero, then they're this thing. So there is some X such that X is a hero, and we're going to tack on this restriction that there's no other heroes. It's not the case that there is something Y such that Y is distinct from X, and Y is a hero. So we've just taken our intuitive truth conditions. There's at least one hero. There are no others. This is there's at least one hero. And this is it's not the case that there's some distinct hero. It's not the case that there is some Y such that Y is distinct from X, and Y is also a hero. So alternatively, you could write as universal. There's at least one X such that X is a hero. And for all the Y's, if Y is a hero, then X is equal to Y. So basically, it's like you're thinking we have our domain of discourse, and we're going to plug in names for these objects. If you're running through and some other name refers to a hero, well, then that name just has to refer to the same thing that X refers to. It has to be the same object. So, and again, if you wanted to be cool and fancy, you could use your biconditional, and you could say there's at least some X such that for all Y's, Y is a hero. This is, it seems a little weird with the Y. Yeah, but I guess this is, there's at least one X such that for all Y's, Y is a hero if and only if X is equal to G. It seems interesting to have a Y here and an X there. There's at least one X such that for all the Y's, Y is a hero if and only if. I don't know about this one. Don't write this one down. I feel like this seems a little messed up. Because, intuitively, we don't have this natural restriction that Y and X have to be the same thing. That there's only one hero. So I wrote this, but I don't know.
Is the G Greta? What the?
Oh yeah. Shit. Yeah, this was a bad copy paste. Okay. Hey. Yeah, this should be X equals Y, right? Great. Thanks, Owen. Okay. Yeah. So there's at least some X such that for all Y's, Y is a hero if and only if X is equal to Y. So I'm gonna. That's an important one. I'm gonna text myself a note to fix that. All right. Slide 11.C.8. Yeah, the thing that's a little weird with the biconditionals is, and it does give me a little bit of pause because, Carnap's a logic engine. Carnap doesn't view these, it doesn't view the biconditional sentence as equivalent to the non-biconditional ones. I don't know why. I think they are equivalent. I can't think of counter models. I can't think of models where you could make this one true and this one false, assuming you fix that with Y. But Carnap does, so like in the Carnap thing, I have to enter them as separate answers, which is interesting. So I don't know. But I think, if it turns out they're not logically equivalent, I feel like by the lights of ordinary language, like what we're doing, schematizing, if this one is a good schematization of there's exactly one hero, then so should this once this is y. X is y. Okay. All right, so numerical quantification. So this is also really powerful thing with our quantifier logic, which basically lets you formalize a lot of math. So this is kind of like for if you were interested in like foundations of arithmetic, this is the part at which we really have the expressive power to do foundations of arithmetic. We can count, essentially, in quantifier logic. So it is kind of funny to think it's like, we all count, right? And we all say these words, and it takes you 11 weeks into a logic class to get to the point where if you wanted to, you could formalize the counting. You know, it's kind of hilarious. But, you know, one thing that I've learned consistently in school is things are not what they seem. Most subjects are way more complex than first glance, at least like at the foundations. Like to really get to the bottom of something is, I mean, you often don't. If you're trying to get to the bottom of something, often you're doing philosophy, and so you're doomed. You are condemned. You're not going to get there, right? But you know, sometimes you make progress. Like, yeah, I think there's senses in which people who got obsessed with foundations of math, they made a real kind of progress in cleaning up, you know, gaps in logical reasoning that otherwise you might have made. So the foundations of physics people, they might figure out quantum gravity, and then maybe we'd have cooler cell phones. I don't know. Maybe we'd have holograms. You never know. Cool. All right. So we're gonna try to formalize stuff like n many, at least n, exactly 1, at least 2, things like that. So if we say something like 3 heroes wear capes, we're going to use our identity predicate to basically force it to be the case there have to be at least 3 cape-wearing heroes. Now, this is, again, we run into a kind of ambiguity in our language where there'd be some empirical question about what is the dominant way these terms are used by a given population of language users. So sometimes, perhaps 3 heroes wear capes means exactly 3 heroes wear capes. And other times, 3 heroes wear capes probably means at least 3 heroes. Now at this point, we're just gonna make a convention like we always do. Logic is highly conventional to some extent. So we're just going to assume that phrases like 3 heroes or, you know, n blanks is standing for at least. So we're gonna stipulate this. That's how we're gonna translate this stuff. So, and here's some motivation. So, if one of you guys to me is like, you have $2, and I say, yes, I have $2, you can't, you know, should you assume that I have exactly $2? If you say that, well, I think no, you know, like, I'm kind of flush right now, I'm doing all right. So, but I do have $2, I got a lot more than $2, you know, but don't tell that to the people on the hardest streets of Boston. It's coming from my pocket. So, yeah, I feel very safe in Boston. So yeah, so if you have $2, I say, yes, I have $2, but this is true even if I have way more than $2. It's even true, I mean, what makes it kind of weird with this example is like, you might ask this and mean, actually, like, do you have 2 1s? I mean, that'd probably be more, you know, and I don't have 2 1s right now. So I have $2, but I don't have 2 $1 bills. So, you know, language is subtle, right? But we are not a subtle logic class. We are logic track. So we're going to express these kinds of sentences, at least n people, exactly n people, at most n people, we love people, we can count QL. Thank you. All right, so at least 1 hero is inspiring. Hint, that's not me. I am not the inspirational figure in this story. You are the inspirational figure in this story. Honestly, I was inspired reading I found this funny news story about an MIT grad who did chemical engineering, and he really put his degree to use. He started a rum company, and it was some really funny language too. You get all this like woo-woo branding of like, people have neglected the true meaning of rum. They thought that rum is a party drink. I'm going to show them that rum is something that can be admired on its own. I was like, this is hilarious, and I'm sure this guy got a lot of investors, you know, to like say stuff like this. But you step back and you're kind of like, this is bullshit, you know? The dude's making rum. I'm sure it's good rum, right? But like, come on, you know, like don't say it's more than it is. That's how I really feel about the restaurant Life Alive. Have you guys been to Life Alive? Life Alive website is over the top. I mean, that branding and stuff, it's like, here at Life Alive, we believe that wholesome organic food can reinvent the way that humans experience reality. I mean, it's like that level. And you can go and you can sit in the hand of a Buddha. There's a chair that is a Buddha hand.
They specifically state their restaurant is an urban oasis.
But it's really good food. I mean, it's like totally legit. You can get a thing there for dinner, which is basically ice cream. It's like a fudge, like I don't know, like a fudge brownie protein batter thing. It's like, strong recommend on that. So yeah, anyways, heroes and inspiration. So at least one hero is inspiring. At least two heroes are inspiring. We now have to say that the X and the Y are distinct. This is the key thing. So if you want it to be true, that, given that there's at least two things, you have to explicitly state that the X does not equal to Y. That's not the case. That X is equal to Y. And then, of course, you say X is a hero and X inspires, and you say Y is a hero and Y inspires. So I've been really tedious, and I've put in the proper parentheses, but Carnap is chill with conjunctions and with disjunctions. So in Carnap, you wouldn't need anything but the black parentheses, because these are all commutative, so you could put parentheses in a variety of orders that'd be logically equivalent. So in Carnap, you just need to let it know that everything in here is bound by these quantifiers. All right, so at least three heroes are inspiring. Now you have to say a bit more. So you're again saying, we have these three things, you choose the variables, you say each one of them is a hero and each one inspires, and you have to say they're all distinct. So you have to say it's not the case that X is Y, and it's not the case that Y is Z, and it's not the case that X is Z. You gotta, say these three things, and then you had it that there's at least three heroes that are inspiring. But if you missed one of these, like you just had X is not Y and Y is not Z, then that wouldn't be at least three heroes are inspiring. You could make that true with only two heroes, because you could just let X be Z, let X be Z, and then it'd be true, even if there were just two heroes. So, any questions about at least? So, at least N, there is a general thing you can say, the general schema for at least N that is on this slide, which again, you're not going to remember this. It's just like something that hopefully will make intuitive sense that you could apply the rule. But so, this is part of what we write down. So you first have to say that all these pairs are different from each other. So you have to say the term 1, whatever 1 is referring to, x of 1 is different from x of 2, and x of 1 is different from all the other x of n's up to x of n, and then x of 2 is different from x of 3 all the way up to the x of n's, and then x of n minus 1 is distinct from x of n. And then you have to, of course, say that they each have the property. So you got to say each of these x of 1s has the property A, whatever the property A is. Property A can be really complicated. We already saw here. Here the property A is a conjunction. It's a hero and inspiring. So in general, this property A could be a really convoluted thing. And you have to say that it holds for every single one of these x's. So this big parenthesis closes here at the very end, big parentheses. So this whole expression is bound by these n many existential quantifiers. Cool. So so this is just the thing I said verbally. You have to state that every pair of variables is different. So if you left off that x1 is distinct from x3, then this would really just be saying there's at least two heroes. Even though you got the three quantifiers and you got the three variables running around, if you don't tack on, by the way, x1 is different from x3, then you could let the extension of the heroes be 1 and 2, and you could just let 1 play the role of x of 1 and x of 3, because you didn't tell me that x of 1 was different from x of 3. So this would be an allowed model. Both these things would be true. 1 is not the same as 2, 2 is not the same as 3, I hope. And so this thing would be true, but in a model of only two heroes. So Very important. Gotta say, every pair of variables is different for the a-b-glimpse. So if instead you have a more complex thing of these n, b's, or c's, then you're just complicating this predicate term a. You're just letting a now be this thing, x is a b and x is a c. And so everywhere here, where you have an a, you would have bx and cx. So just do the same thing, just more complicated. Okay, so exactly one. I feel like, in the last 10 minutes, let's do some example. So if you have your laptop, let's pull up the Carnot machine and try to do at least 2 examples. I feel like, we all fade in the last 10 minutes or so anyway, right? So might as well. Let's see. So the Carnot. So I think you can probably get to this stuff if you go to the Canvas page. Got a little links, but yeah, it should be on the Canvas page. And find it in my morass of. Let's see, where is week 11? Week 11. All right, maybe this is harder to find than I thought. Go to the Canvas page myself. Where I put this funny story about rum here. I just thought it was so hilarious. It may be inspirational, right? Maybe you think that's what you're going to do with your MIT degree. Start a liquor company. Make the world a better place. I don't know, it's hard to say, right? So many people suffer from alcoholism that it's I think it's kind of tough to feel totally warm and fuzzy about alcohol. But, as Ben Franklin said, beer is truly a sign that God loves us and wants us to be happy. And Ben Franklin, he knew what he was talking about some things. True polymath. All right, so we have 2 problems, and these are similar to the first homework problem. Same universe of discourse, same predicate schemas. So we have all the currently living people, and we have little b for Barbara. And I don't even know if those. I don't think Barbara figures in our 2 problems here anyway. So we want to schematize this sentence. If one person travels to Portugal and a different person doesn't travel to Europe, then neither of those people will visit each other. So give this a shot. This one's tricky. That's why it's not on your problem set. I thought it was too tricky in a way. We have this, one person and a different person. Try to schematize this. This, I think, is actually a donkey sentence. But that doesn't mean anything to you yet, so. All right. I'll make sure all the relevant people are in the good attendance pile. Let's see. Cool. So, you guys. Send it in. So yeah, again, Quad being here today, and I really appreciate it. If the problem set 11 deadline's an issue, feel free to get in touch, and I will happily grant you some kind of extension to reward you for your good behavior. And you guys all have your interns back. I was up in my office this morning, so I grabbed this thing. I thought I might as well bring it. All right, so the tricky part about this one is, do we use existentials or do we use universals? And there's a supreme temptation to use existentials because we're thinking, oh, one person, one, that's like at least, that's existential. This is one of these generic, if anybody. So this if one person is, we're like, if any one person travels to Portugal. And now again, we have the question, and a different person, we're thinking, is this at least one different person, or is this any different person? And so the way to read this is here the indefinite article A is functioning as an any. So this is also a universal. So this is two universals. And in this case, because I think it's a donkey sentence, whatever that means, you actually, I believe, have to put them both out front. You need both your universals right out front for all x, for all y, and then we're going to go through this stuff. So now we're kind of just at the let's get the content of the sentence, not miss anything. One thing you might miss is this is, the x is traveling to Portugal, and the y is not traveling to Europe. So you have to think, okay, Europe is different than the Portugal predicate. So doesn't travel to Europe is not EY. Now I want to say they're different, so I have to say not x equals y. And now I notice, okay, it's an if-then statement, so I need an antecedent and a consequent, and I'm going to have to bracket those off with parentheses. These parentheses do matter. So this is my antecedent. And then my consequent, they don't visit each other. And again, I need parentheses for the consequent because it's complex. So not visit xy and not visit yx. And then close the whole thing down, and then we say our prayers, and yeah, cool. So, are there questions about this one? Besides the fact that it was true. All right, cool. So yeah, I think we got 3 minutes. We can do this other one. So try to give PP 11.2 a try. We love PP 11.2. If one person visits someone else, then either both travel to Europe or both stay home, like lamos. Don't stay home. Travel to Europe. Europe's a great place. So again, the question here is it existentials or is it universals with this one person and someone else? So raise your hand if you're in favor of existentials. Raise your hand if you're in favor of universals. And the universalists have it. But the existentialists will live to fight it. But now on this problem. So this is again this one person is anybody. If any one person visits someone else, and this visits someone else is anybody. Visits anybody else. So it's this is very tricky with these sneaky universals. So if one person visits someone else, so we have to say vxy, and x is not equal to y. So x visits y, and they're different, and then that's going to be my antecedent, so I need to make sure that it's closed off in parentheses. Now I need my consequent, which is complex, so I got to open parentheses again. Then either both travel to Europe, so this is a conjunction, both traveling to Europe is ex, ampersand ey, and then put that in parentheses, disjunction, or new parentheses, both stay home, hx and hy, capital Hy. Close that, close my consequent, and then close the whole thing. So this third parenthesis here is closing my opening parenthesis from the quantifiers. So everything's bound by the quantifiers. There's no free variables, which is good. Typically, there's not going to be any free variables. So if you write a sentence in this thing and there's a free variable, you've probably made a mistake because we're symbolizing sentences. Those are true or false. And so the QL sentences can't have free variables. So you want to make sure all of your variables are bound. That's like a little structural guide. Cool, perfect match, hey. So cool. So we got this. So yeah, we'll do more examples on Wednesday, and we'll get through, I guess, the key things we'll get through will be finishing numerical quantification, both in neither and the definite description. Something that we love and adore and has a great history in philosophy, the definite description. The author of Waverly Place. This was Russell's example that started definite description. I don't know, we might talk about Russell's example. It's just fun to say. The author of Waverly Place. So Sir Walter Scott. That's it. So the author of Waverly Place is a definite description of the word. Sir Walter Scott. So we can schematize that. Isn't that cool? Yeah. But the linguists now have changed theory. So the linguists tell us that what Russell did in the early 1900s is actually wrong. So that's a bummer, right? But we still teach it in these logic classes, right? I wonder when, if ever, the logic class will catch up with what the linguists are doing. We say to hell with the linguists. They need us.